Thank you very much, ladies and gentlemen. SLGS annual conference, as the name implies, is an annual event of the Sri Lankan Geotechnical Society preceding its annual general meeting. Indeed, we are very excited to note that this year's conference has attracted some of the world's most renowned and unparalleled geotechnical personalities, together with eminent representatives from the industry and the academia. And so with such a diverse and dynamic representation in our audience, I'm sure we can't wait to kickstart formally the one-day learning opportunity with this fantastic forum. To formally welcome all of you for giving us the gift of your presence here, please let me invite Engineer K.L.S. Sahabandhu, President of the Sri Lankan Geotechnical Society, by his welcome speech. Over to you, sir.
Video என்ன
Hello. Hello. Hello.
Yeah, we can hear you. We can
Okay.
hear you.
Yeah, I'm very sorry. We had a technical problem here. I will start my welcome speech. Distinguished resource persons, valued invitees, session chairman, members of the executive committee of the Sri Lankan Geotechnical Society, members of the organization committee of this conference, members of the society, ladies and gentlemen. It is my great pleasure and honor indeed to cordially welcome you all to the annual conference of the Sri Lankan Geotechnical Society on the theme Pile Foundation, Design, Construction and Testing, which is conducted customarily preceding the annual general meeting. SLGS, as you may have learned, was inaugurated nearly 3.5 decades ago under the visionary leadership of Professor A. Tureraja, who returned to his motherland after an outstanding and influencing career at the University of Cambridge, and eventually considered as the father of soil mechanics in Sri Lanka. Since its inception, SLG has been playing an important role in the advancement of the discipline of geotechnical engineering in Sri Lanka as a professional body for practicing engineers and academia active in the field of geotechnical engineering, and with an enhanced seal with the becoming member of the International Society for Soil Mechanics and Geotechnical Engineering, that is ISSMGE. Multifaceted activities of SLGS included conferences, seminars, and workshops conducted by world-renowned experts in the field of resource personnel, geotechnical forum, and evening lecture held monthly, providing opportunities for the Sri Lankan geotechnical engineering fraternity to learn from experiences of the academia and the practitioners from local and overseas origin, and technical visit to project sites of geotechnical relevancy. Moreover, SLG has conducted 3 major international conferences in 2007, 2015, and 2021, with the participation of large number of internationally renowned academia and practitioners in the field of geotechnical engineering. During this tenure, we have conducted a workshop on Eurocode 7 geotechnical designs and 7 geotechnical forum on contemporary topics in geotechnical engineering. As a final event of this tenure, we have planned our annual conference proceedings, the annual general meeting of SLGS as its statutes. Even though a physical event is favored to offer more interaction between resource persons and the participants, due to the current circumstance of the country, the executive committee was kind of forced to opt a virtual platform to conduct the event. We have a great line of eminent resource persons today, selected from academia and industry, who have thorough knowledge of practitioner requirement to share their valuable perspectives under the theme Pile Foundation Design, Construction and Testing. We are grateful to them for joining us on this knowledge sharing journey. It would indeed be thought-provoking conference of topical interest to all of us in the geotechnical engineering fraternity. Ladies and gentlemen, it is my privilege on behalf of the society to welcome and thank Professor Aripoulos from University of Sydney, Australia, Professor Gray Mullins from College of Engineering, University of South Florida, USA, Professor Samant Tilakasiri from Faculty of Engineering, Sri Lanka, Institute of Information Technology, Dr. Asisa Senanayaka, Senior Geotechnical Engineer, Norwegian Geotechnical Institute, NGI, Texas, USA, Dr. Upul Latukorala, Principal Geotechnical Engineer, Gold Association Limited, Canada, and Dr. M. Yogendra Kumar, Principal Engineer, Gold Association Limited, Canada, accepting our invitation as resource persons. With immense gratitude, I welcome all distinguished invitees, including past presidents and SLGS past and present executive committee members, for joining us by gracing this event. Also, I warmly welcome Professor Atul Kulatilaka for accepting our invitation to chair the sessions along with myself. I am grateful to all the members of the organizing and the executive committees, particularly Professor Atul Kulatilaka, Engineer Kirti Senanayaka, Dr. Jayanta Maratunga, Professor Priyanta Jayavikrama, Professor Samant Tilakasiri, Dr. Asiri Karunawardana, Professor Udeni Nawagamuwa, Dr. JSM Fauzi, Mrs. Vatsala Galayena, and Engineer Mahinda Randasiri for being with me together, offering their unceasing support to make this event successfully. I also wish to welcome all the participants who will make this event a remarkable one indeed. It is noteworthy to mention here that ISMMG, which is a pre-eminent professional body, safeguarding the interest of and activities of those actively participating in geotechnical engineering, has recognized this event as an ISMG event and has given due publicity for the conference. Undoubtedly, the conference will be another exciting and informative event by SLGS, and I wish everyone very effective and fruitful conference. Thank you.
Thank you very much, sir. Ladies and gentlemen, with the welcome members of the President, it's now time to move on to the conference proper and to commence the morning session of SLGS Annual Conference 2022. The session will be chaired by Engineer KLS Sahabandhu, President of the Sri Lankan Geotechnical Society, and it's my privilege to further introduce him to the gathering. Engineer Sahabandhu obtained his BSc Engineering Honours degree in Civil Engineering from the University of Peradeniya in 1980 and a postgraduate diploma in Hydraulic Engineering from the University of Moratuwa in 1985. He obtained his master's degree in Structural Engineering from the University of Newcastle upon Tyne, UK in 1988, while winning the Patrick Parsons Prize for the best all-round academic performance in civil engineering. He achieved his charter status by admitting himself to the corporate membership of the Institution of Engineers Sri Lanka and the Institution of Engineers London in 1985. Engineer Sahabandhu is an honorary fellow of the Society of Structural Engineers Sri Lanka and a fellow of the Institution of Engineers Sri Lanka. He is also a member of many other professional institutions, including the International Society for Soil Mechanics and Geotechnical Engineering, the Institution of Civil Engineers London, and the Association of Consulting Engineers Sri Lanka, and the Sri Lanka National Committee on Large Dams. Engineer Sahabandhu has rendered his service to the country through the Central Engineering Consultancy Bureau, which is the largest consultancy organization of the country for over 39 years, and retired as the General Manager of CECB in June 2019. After the retirement, he served as the Senior Consultant for the Ministry of Megapolis and Western Development for over 2 years, and presently he is serving as the head of the Engineering Consultancy Division and Additional Project Director in Structural Engineering at the Urban Development Authority of Sri Lanka. He is a recipient of the Award of Eminence, a once-in-lifetime recognition given to an individual by the Construction Industry Development Authority of Sri Lanka, And similarly, Chartered Engineer Award by the Institution of Engineers Sri Lanka for his significant contribution to the engineering profession and the construction industry of Sri Lanka. With that brief, I would now like to call upon Engineer Sahabantu, President of the Sri Lankan Geotechnical Society, to take charge of the virtual platform. Over to you, sir.
Thank you, Dr. Fauzi, for your very kind introduction. Our conference, the first session, the morning session, we have 3 presentations by Professor Gray Mullins and Professor Ari Poulos and Professor Samanthi Lekasiri. And Professor Gray Mullins' presentation will last for 2 hours and other 2 will be 1 hour each. Now, each presentation, we would like to give about 10 minutes or 15 minutes time to answer questions raised by the audience. Now, you can put your questions into the chat box and the author will answer your question depending on the relevancy to the subject. Also, I want to state here, we had a very difficult situation with Professor Gray Mullins' presentation because he is living in Florida, and as you are aware, the Florida is subject to severe natural disaster because they are facing the hurricane, and luckily Professor Mullins realized it and he has sent the whole presentation in recorded format. And because of that, the quality and also certain things may not be 100% perfect, but I request you to apologize the situation. This is a unforeseen situation Professor and the society facing. I am very grateful to Professor to take the prompt action to avoid the cancellation of this lecture due to the climatic disaster conditions, but he took special effort to record his presentation and send it to share with us. Now with that, I will request to the play is recording, and its topic will be on thermal integrity, profiling of board piles, theory, testing, and analysis. It may have 3 sessions. I'm sure we can cover all 3 sessions during this 2-year period. Okay, you can start the recording.
Good morning. This is Gray Mullins with University of South Florida. Sorry I have to record this in advance, but we have a hurricane bearing down on Tampa Bay, so I thought this would be the wise thing to do about the time I'm supposed to give you a presentation. That's when the hurricane's supposed to hit. So again, we're here to talk about thermal integrity profiling of deep foundations. It's going to be broken up into several sessions, 4 sessions in all. I hope we have enough time to get through them all. And this one is just going to give you the background and some of the why we do it types of information. So again, the outline of the presentation, we're going to give you a little bit of a background. We'll go into what type of results, what we should expect from thermal integrity profiling, the type of equipment we're going to use, the procedure for testing, data analysis, case studies, and those make up most of the modules that'll come after this. A field demonstration, obviously we're not going to be doing, but that would be typical after a morning session of learning how to do the testing, what the testing's about. I'm going to condense this as much as I can to get into 2 hours, what I normally might do in 4 hours, but again, we'll go as far as we can. When we run out of time, you can look at the presentations later if you need to. So what are we doing here? For concrete, it's real typical to be able to quickly use visual inspection above ground, be able to tell if something is not quite right. In this case here, you're looking at a drilled shaft that was cast all the way out of the ground and above ground through some temporary formwork. and concreting was delayed. And so when the trucks finally did arrive, the initial set of the previous truck had already kicked off. And so the green concrete was then disturbed by the new concrete. Again, most people would have thought, no problem. There's no slurry. We're not underground. We shouldn't be dealing with any kind of problem here. But as you can see here, the brown or the discolored concrete on the left was easily just chipped away to reveal what you see on the right. So again, visual inspection, pretty common. Below ground, it's fairly limited. We would only be able to see perhaps that which would have been exposed for footing construction or to proceed to the next stage, moving up into the foundation. But and so when you look at footing that has been exhumed here a little bit just prior to footing construction, you see the drill shaft on the left is intact, and on the right it is not. So visual inspection might say left good, right bad. Definitely the one on the right is bad, but the one on the left is also bad. Very, very poorly constructed. And you'll notice that it also has access tubes, and those are the little tubes tied into the cage. I don't know if you can see my arrow or my cursor there, but there are this 6 foot diameter. So we have 6 tubes. And one of the most popular ways of testing is cross-hole sonic logging. Cross-hole sonic logging essentially is bouncing sound waves between these tubes. And so anywhere between the tubes, you can see the quality of the concrete. For all intents and purposes, we like to assume that anything inside the polygon is being tested, and it's a reasonably good assumption. Anything outside the polygon, unfortunately, is not being tested. So there are other methods that come in and test it. One of them is gamma-gamma logging. Gamma-gamma logging is uses cesium-137 radiation, and uses backscatter detection devices. And so it has a plume of radiation that can detect about what you're seeing there. About a 3 to 4 inch radius around the tubes can be detected. Now that's only if you're using plastic tubes. If you use steel access tubes, then you can't have that kind of plume. The plume is greatly reduced when you look into using steel. So California is one of the states that uses gamma-gamma logging quite a bit. Sometimes it's called gamma density logging. So it could be GGL or it could be GDL. But you see that it has the ability to look outside the cage a little bit, but if the test is not set up correctly, sometimes the plume can be too large, and then you start to detect the soil outside of the shaft, and that's not good either. So they have to rein that in so that it only detects within the cover and not the soil around it. So my point is, it has a fairly limited ability to detect the entire cross section. This is an example of the types of anomalies that you might see in a drill shaft, and this kind of has the whole thing. Everything looks pretty good at the top, all the way down to what we call mattressing. It's actually a relatively new term where concrete flow is not quite sufficient to get out into the cover region. You look at it a little bit more closely, even at the bottom. This, I would also say, it's a twofold problem. I think they had concreting problems. I think they had problem with controlling their slurry, and hence they had a whole host of problems here. This shaft was rejected on the basis of concrete volume. So there was a theoretical volume. They didn't meet the theoretical volume, so therefore it was rejected. Today, you would see a shaft like this down here at the bottom. You would see access tubes coming out of the top or the bottom. If I back up one, you see that there are no access tubes coming out of this, only conduit for the lightings, the light mast. And so all these dimensions all then tie back into durability. If you've got all of this tied in together, then your shaft should be able to resist corrosion resistance down the road. So everything that temperature tells you links back to all the other serviceability aspects of a drilled shaft. If we talk about, this is just a 6-foot shaft, and we're looking at the core temperature. This is the very center of the shaft. Now, we don't take measurements at the very center, but you see that the more cement you have, what you're seeing off the legend there is 860 pounds per cubic yard, roughly, I don't know, you make the conversion to metric, 600 or 430 pounds per cubic yard. And you see the more cement you have in it, the higher your temperature, and vice versa. Hydration times, again, these are all just cement. There's no supplemental materials using fly ash or any of that in this. This is just pure cement. And you can see that the peak temperature often occurs somewhere right around 20 to 24 hours for a 6-foot diameter shaft. If you look at the effects of different types of materials, now these are cage measurements. This is at the edge. I don't know why I have two different versions here, but we've got a slag mix in here, we've got a fly ash mix, and we've got a pure cement mix. And they all have the same rough cementitious content here, but this is only a 4-foot diameter shaft. But you see that, okay, there's your pure cement peaking off at about 24 hours. Fly ash a little bit later, looking at about 30, and then a slag mix, which is typically, maybe 60% replacement, somewhere in the area of about 48 hours. So from a standpoint of thermal integrity profiling, we look at the mix design, we look at the shaft size, and then we try to decide what's the most appropriate time to do our testing. So, and this is not hard and fast by any means, but this gives you an indication. So we're looking at the time. Sorry, I had to take a little break there. If you have a larger diameter shaft, it's going to be hotter longer. It's going to get to its peak temperature later. So what you're kind of seeing here is a smaller diameter shaft, which is in the bottom there, 4-foot diameter. That's 1.2 meters. Again, it's going to come to a peak temperature somewhere right around 20 hours, where the 10-foot diameter is going to come to the peak a little bit later. But we don't want to test too early when you see that temperature rise climbing so quickly. And we don't want to test too late, because if we test too late, then we start looking into other things that affect temperature, like the diffusivity of the surrounding soils. And we don't want the external aspects, the environment, to be affecting. These are closely tied. It turns out the more cement you have in there, the more chloride the concrete can resist with regards to when the onset of corrosion would occur. So there's that chloride threshold that is usually based on the percentage of cement. And so you're seeing kind of like two different things that are happening here. When you increase your cement content, you also slow down the diffusion of chlorides into the concrete. So the concrete is, again, more impervious. But then when you also increase your cement content, you raise the bar where it can tolerate more chloride once it gets there before it starts to corrode. So these are important parameters from a durability standpoint. But naturally, we also know that temperature and strength are related, but it's a very, very bad correlation. I would never use temperature to equal strength. I personally use temperature as a indicator of homogeneity of the entire shaft. So if you see that, like for instance, the strength is increasing with more and more time, and the tube temperature is also increasing at the same time. But with smaller diameter shafts, you expect the temperatures to go down for the exact same strength. So again, temperature and strength are not a hard and fast relationship. The size of the shaft does affect the temperature, and mix affects the temperature. So again, more cement, more temperature, more shaft size, more temperature that you're going to see at the access tube. So again, just kind of keeping this all together, all these things are somewhat related. So if you have a given cement content, you can go in and say that, you know, I know where my diffusion is going to be, I know roughly what my strength is going to be, and I know what temperature I should be able to anticipate when it comes to these kinds of parameters. What shaft size should I expect, and so on. So again, all these things are somewhat linked together. It's a background concept. It's not the mechanism that we use to analyze. So what do we see, or what should we see from thermal integrity profiling? It's one of those things that tests the entire volume of the concrete. It's very difficult to hide an anomaly, even though it's in the core, away from the cage. We take all our measurements at the cage. It's pretty hard to find it. So to hide an anomaly without the tube temperature seeing it. So it tests the entire volume of concrete. Because the cage can move left and right, that means the temperature of the cage is going to change. We can estimate the shape of, again, of the shaft based on temperature as well. It'll show us if there's cross-sectional changes. And again, because we can get cage alignment, we can also get concrete cover and hence even quality of the concrete. Now, quality of the concrete is a little more difficult. We'd have to be comparing multiple shafts on a given project and say, why are these shafts colder than the other ones? And then you start seeing that there's changes in the delivery quality of the concrete. If you take a slice right through a drilled shaft, you'll see a temperature distribution that looks something like this. And what's somewhat interesting about it is that the shaft might be confined to only this center region. There's no scale across the bottom, so don't look at the numbers across the bottom. But the elevated temperature in the shaft will cause the soil temperature to go up as well. So, you know, if we slice through these, we kind of think that we know we're going to get a kind of a bell-shaped shaft. Now, we take our temperature measurements right at the location of the cage where we can put access tubes or something like that. And what's significant about that is that if you kind of look straight down under the location of these, you see that the tubes align themselves with the steepest part of this temperature gradient, if you will. And so subtle movements left and right of the cage will impact our temperature measurements. And that gives us a great insight of what's going on inside the shaft. Okay, so let's look at a few and just say, what should I be looking at? What do I see from a thermal profile? If we know that the shaft is going to radiate heat, again, radially, and it's going to dissipate it into the air and into the soil below, everything in the center portion of the shaft can only lose its heat radially because it can't go up and down. All that concrete's trying to get rid of it as well, except for when you get close to the ends. When you get close to the ends, you start seeing multiple modes of heat dissipation. And so we get a temperature that, like I say, rolls off. There's a temperature change as it gets closer into the ground and or into the ground at the bottom or closer to the air at top. Now, what you're seeing up here at the very, very top is that's just the air temperature of the tube when you lower a probe down in there, and then you see it gradually get warmer, stays fairly constant. And this is actually a pretty uniform shaped shaft. And then at the bottom, again, we see that dissipation of temperature longitudinally. So if I look at, we're just going to look at a bunch of these things here. I see this is a 4-foot diameter shaft. It has 4 tubes in it. And again, that is kind of common. 1 tube or one measurement location per foot of shaft, or 0.3 meters, something like that. So if you have a 1.2 meter, 4 foot diameter shaft, you're going to have 4 tubes. We like to also say, don't use any fewer than 4 tubes, because 4 tubes gives you so much information about left, right, north, south, east, west movements of the cage. So let's take a look at what are we seeing here. We see that the temperatures, especially from 20 feet down, all the temperatures from all 4 are exactly the same, and they're the same as the average temperature. So that's kind of interesting. That means that there's no movement to speak of. At the very, very top, there is a little bit of variation in the temperatures, and which is quite unusual. And maybe I'll talk about this a little bit later. The water table is probably right here, right around 17, 18 feet. And this is common construction practice. I hate it. I wish they wouldn't do it. There's probably a surface casing here down to maybe about 12 feet. So you see there's a little warmer temperature here, and they'll excavate through the surface casing and keep excavating. They say, oh, it's still dry, I don't need slurry. And as soon as they do hit the water table, you start seeing it slough into the excavation. And then they quickly add slurry to maintain stability of the hole. It's a bad practice, but it happens all the time, and it shows up here as where that sloughing occurs. We get a little bit of a dimple in the temperature, a rise in temperature, because the cross section gets larger. It's warmer at the top, 110 degrees here. Down here, closer to the bottom, it's probably only 103 or 104 degrees. But again, this is casing, larger, hotter, tool size down here, smaller, colder, a little bit of a dimple there. And again, very little cage movement left and right. Now, let's just look at this one area here at 10 feet. You see the, I don't even know what color that is, light green and purple here on both sides of these things. They are on opposite sides of the cage. When we look at the tube layout, 1, 2, 3, 4, that's as you look down from the top, tubes 1, 2, 3, and 4. Tube 1 is usually designated to be the northernmost tube. But what's interesting here is that where 2 gets warmer, 4 gets colder. And again, that's pretty normal. As the cage moves towards the edge, it's going to get colder, and that would be tube 4. So this cage is moved in the direction of tube 4, closer to the sides. So very clean top and bottom roll-off signature. And as a whole, I'd say very good shaft here. There's your, again, the dimple for that, and clean roll-off conditions there. So how does it detect cage alignment? We just talked about it briefly, but if we know that the temperature distribution across the shaft forms this somewhat bell-shaped bell-shaped curve, if it's perfectly centered, the cage on the left side and the cage on the right side will read the exact same temperature. As soon as the cage moves a little bit, and in this case, it's moving a little bit to the right, the one on the right side, getting closer to the side walls of the excavation, is getting colder, and then the other one's getting closer to the core, and so it's getting warmer. Those are usually equal and opposite offsets. So let's see, we got an example here, exact same type of thing here, but this is a 10-tube condition. And so there's lots of things going on here, and you can probably start seeing some of the key features that we've talked about before. But again, we're talking about the temperature moving to one side, and I actually cherry picked this data set here where opposite sides of this things were, in fact, one side was moving towards the shaft, the other one was getting hotter. So again, the one that's getting hotter is moving towards the center, and the one that's getting colder on the opposite side of the cage is moving the opposite direction. If we look at this, look at all tubes, and I've done kind of an unusual thing here. We don't usually do this today. This was done, I don't know, 10, 15 years ago, but if you plot all the temperatures on a radial temperature plot, so where, again, we're increasing in temperature as we go away. So this is 170 degrees, 150 degrees, 125 degrees. So I'm sorry, it's hottest in the center and coldest as it moves to the edge. You start seeing that where one side gets colder, the other side gets warmer. Now, it's not a perfect circle here that's formed by these new tube locations, but it gives you a sense of how the entire cage is moving in one direction, and it affects all tube temperatures, not just one temperature. So again, we see those two, the highs and the lows, were in fact the opposite sides of the shaft. So what do you see here? You should see some eccentricity stuff going on here. You're seeing, again, tubes 2 and 4 equal and opposite from the average. The average is being shown here as red. And red, in this case here, the average of all tubes should reflect the actual shape of the shaft, where the movement of the cage left and right is reflected by the eccentricity or these offset temperatures you see. You also see that green and blue here are also equal and opposite away from the average. And again, that was numbers 1 and 3. So again, equal and opposite, you should always be able to see something like that just as give you an idea what's going on. You also see fairly typical temperature reductions at the top and the bottom. Another case here, interestingly, is you see exact same color combinations, different shaft, but you see in the green and yellow are opposite of the purple and blue. And so you say, here's purple and blue, here is green and yellow. So this cage here is moving in kind of a diagonal direction, where the 3 and 4 would typically be south and west. So this thing is moving to the southwest, and it's touching on somewhere between 3 and 4 is where it's getting closer to the cage walls or the shaft walls. So converting it to radius is kind of an interesting concept. And depending on where you are in the world, different types of inspection are done. Now, typically, now this is a terrible image here, but this is literally a field log, where if we know we have a certain size shaft, and we put in 1 truck worth of concrete, it should rise a theoretical value proportional to or computed from the radius of the shaft or the diameter of the shaft. So there's always a theoretical rise in concrete that we would expect anytime we add more concrete. The depth should reduce, and we're measuring it down. So this is a weighted tape that we use to measure down, find the bottom, put in a truck, find the bottom, put in another truck, find the height of the rising concrete. And you'll see that they track 1 for 1 up to about this point. And then all of a sudden, you're using a lot more concrete than they thought before. And even the slope of the line here has shifted off to the right, which means that I'm using more and more concrete per foot than I expected. So concrete and again, it's based on So in this particular case, each one of these dots, by the way, is a truck. So this is a fairly large shaft. It had, I don't know, 20 or some odd trucks in it. And so if I plot the effect diameter or the calculated diameter, compare it to the, say that I should have had that blue dot there. These are very, very close, but there is one region here where they used a lot more concrete than anticipated. Now this dot here and this dot here, I just say that there's been no correction for filling the tremie, and there's a few other things that they had to do. So that first truck ends up using a lot more concrete than actual. So this dot here, not so believable. This dot up here, not so believable. But the rest of them are pretty believable. And what was interesting, and this is the first time we recognized this, is that when we look at the average temperature, now I've taken all my tubes, this is a 7-foot diameter shaft, so it had 7 tubes. I take the average of all 7 tubes, and I see the average shape, average temperature gives me the shape of the shaft. And we see an amazing correlation between surface casing, subtle little bulges in the shaft are shown up by subtle bulges in the temperature. And then of course, in this one area where it becomes much more dramatic, we see again, kind of a one-to-one relationship there. This then opened up our eyes to realize that temperature to radius could be plotted. When you had a truck like this, it's kind of interesting because you can plot the radius measured from each truck versus the temperature, and you can come up with a kind of a correlation, a temperature to radius conversion. And if I apply that then to all 7 of those shafts, first off, I see that the red dots, those were the exact same dots you saw before, they match nicely along the average temperature. And I've used that correlation, again, this conversion here, I've used that to determine what each tube radius would be. What is the local radius at that angle if I come from the center of the cage and I shoot out in the direction of tubes 1, 2, 3, all the way up to 7? This would be the radius of the cage at that location. Now, there's quite a bit of a disparity here in tube 7. I suspect that's not quite believable, but again, data is data. You plot what you have. If you compare this to the cage location, you recognize that this is variations from left to right. This is real radius differences. So this thing is going from maybe a 36-inch radius all the way up to a 50-inch radius, depending on which side of the cage you're on. And so this is telling me the cage is literally touching the sidewall, which means I have no cover there. The blue line gives me what the average shaft size should have been. That should have been my 7-foot shaft, or a radius 42 inches. So again, that's kind of the way this works. And if we do plot all these together, let's see if it'll do what we want. Doesn't look like it. This is actually supposed to be that was supposed to be a video. So there's a big question, and I've seen some reports out there that didn't really kind of understand what was going on, but their point is that I can't tell what's going on at the end because the temperature drops off anyway. How can I tell the difference between a normal end changes and an anomaly near the tip? And the way we handle that is by computing what the tip shape should be. At time 0, when I first apply this temperature, there is no change in temperature. The temperature would be constant all the way to the bottom. Now, this is kind of a bad slide because it would never be 100 degrees at time 0. But at time 0, straight over temperature below that. And in our parts of the country, it's 73 degrees. But then with time, it softens. And so what we'll do is we will predict this. I'm not really sure what I'm showing here. Looks like my slide has messed up here. We can predict this shape here with a hyperbolic tangent equivalent here, and you're starting to see this red dot in here. Let's see what happens. I'll put a few more dots in here. You gotta love that. So these should be curves. And so what we're doing here is that these curves change with time. And so when we fit the curve and we know what the theoretical curve should have been, and we compare our measured temperature to that, and we're able to get it. We'll go over this again later. The shape of the shaft in particular. Okay, so we do this all the time now. We take the temperatures on the left, we correct the top and the bottom for their normal hyperbolic temperature dissipation, and we're able to produce the effective radius that you see on the right. Almost all test types or equipment types talk about a zone of influence. And so the question might be, what would be the zone of influence of, or what is the level of detection from thermal testing or from temperature measurements? And it's really not a range, or it's more of a size of the anomaly that is really the question to ask. What size anomaly can I see? If it's a tiny anomaly, the size of, let's say, a baseball, and I think that's not too far from cricket, so, but I don't know what I'm talking about there. So you take a small ball and you put it inside a 10-foot diameter shaft, you won't see it. You won't see the temperature change. But some of the quick numbers, O'Neill back in the mid 80s and into the 90s speculated that a 10% cross-section change from some kind of anomaly should start to raise some eyebrows. You know, you should start getting worried at about 10%. It turns out that if you have a very, very large anomaly, you can see it throughout the entire shaft. The far side of the shaft, you'll see it. Every tube will be able to see it. Small anomalies are only picked up by the closest tube. But if it's a 10% anomaly, like O'Neill talked about, it's literally impossible to hide it. It's just too big for it not to be found by one, if not multiple wires. Here's a kind of a weird example here where we tied sandbags to the side of a shaft. And this is a very difficult thing to do, to be perfectly honest. It sounds like it's easy, you know, tie bags to the side of it. But if those airbags contain, those sandbags contain air, and it's not saturated soil, then that is not representative of your native soil. So you have to be very careful about strategically trying to figure out what is a good anomaly. It has to be 100% saturated if you're in saturated soils. The soil type has to be the native soil type. You can't change soil types in your sandbag. So it turns out to be kind of a difficult thing to do. In this particular case, we tied sandbags to the outside in two forms, one where we had bags on either side, and then we had bags only on one side. And we use steel tubes and we use plastic tubes. We're kind of playing around with a bunch of different stuff here. This is very, very early on. And I think I'm only looking at tubes 1, 3, and 5 here. So again, 1, 3, and 5 is this configuration here. So you see tube 1 should see the lower one. I believe this is the lower one. Yes, bottom anomaly. And number 1 shouldn't really see these anomalies, but let's go ahead and see if 1 sees it. If we come down to that first anomaly, 1 does see a reduction in temperature, but it doesn't see it very crisply. But then 3, which is again, this red tube here, it sees it very clearly. So it's kind of a projection. The closer you are to it, the more defined your temperature change is going to be. And the farther away you are, it's more of a broad band effect. Now the black in this case is it's the average temperature of this particular shaft. And it pretty well gets the average shape from the standpoint of, I've got about a 10% reduction here, I've got a 10% reduction here, and it does roughly pick it up. This was done way long ago, 22, 25 years ago, before we got the quality of testing equipment we have today. I would love to be able to redo this test with today's equipment. So let's talk a little bit about the equipment type that are being used. We've got 2 ASTM methods. One's method A, method B. Method A is a probe where we lower it down into the access tubes, the same access tubes that you can use for GGL or for CSL. And you run it over a depth wheel. The wheel keeps track of where your probe is. And so you're able to get a temperature versus position profile. We run 1 test somewhere right around peak temperature. You don't want to run it too early. You don't want to run it too late. You want to be somewhere in that sweet spot at the highest temperature. And then there's the method B, where we tie thermal wires to the cage instead of putting in access tubes. You can still use access tubes, but you tie them in, they're permanent, they're not reusable. And then you just hook it up to a data logger and take data every 15 minutes or 5 minutes, whatever you want. And it's able to capture the peak without you having to have previous knowledge of what the actual temperature would be. You do need to have a data collector for each wire, and it is throwaway. The wires are throwaway, but you get a lot more information from this. The increment of data is usually about on 1 foot increments, whereas the probe method, you can get it down to 1/10 of a foot with no problem. So you'll get more data from the probe at a given time, but the thermal wire method gives you more data over time because you have so many different times. Again, the equipment, if you look at the method A, it does use some kind of an infrared sensor. This is the same type of technology that they're now using to shoot infrared beam into a baby's ear to detect the temperature. It's the same kind of technology. We use 4 of these probes or sensors inside this probe, so they read out in radial directions. It does pass over some kind of a depth wheel here. And then, of course, all this gets picked up by a miniature computer. And again, here's a kind of a look of the equipment being used. Again, the depth wheel, the miniature computer, and the probe all get linked together through a thermal access port. The TAPP, PP means it's thermal access port for probes. The other method uses wires, again, that are embedded into the concrete. They're throwaway, and you need to have 1 of those tap boxes. These are just TAP, not TAPP. 1 tap box per wire. So you can see here, I think I've got 4, looks like 4 or 5 wires on this shaft here. So kind of closing out quickly, again, this is just a brief overview of where we're headed, I suppose. Temperature measurements are, it's insane how much information you can get from them. And it does give you the ability to look at the entire volume of concrete. It's easy to see cage alignment. It shows where the shaft changes in shape. You saw that 27 concrete trucks, and 4 or 5 of the trucks were in an overpour area. And so it shows necks and bulges. If you have an inclusion, of course, the shaft might look good, but it could have inclusions inside it. And because of all this, we're able to give you an idea of how much protection you're getting in your concrete cover. And again, we talked about quality of concrete, but we'll get back to that in a later presentation. Okay, so that's it for section 1.
Okay, this is session 2, just talking about the testing procedures, and we won't spend a ton of time on this because we're not going to be doing any testing today. But again, the thermal integrity profiling is covered under ASTM D7949, and specifically it talks about 2 methods, and we mentioned this previously, method A and method B. Method A uses the thermal probe. We lower it down into access tubes. Again, these access tubes were essentially developed for cross-hole sonic logging in the mid-90s. And because of that ability to start looking inside the shaft, that gave it the ability for gamma density logging or gamma logging, and also for thermal integrity profiling. And then, of course, there's method B, which just ties sensors inside the cage. There are some advantages and disadvantages, of course. Method A, the probe is completely reusable. So you have 1 fixed cost and you can do hundreds and hundreds of tests. I think I may have conducted upwards of 1,000 tests with 1 unit. And you are able to look at your data immediately. So you get, as soon as you've collected your data from all your tubes, you look at it, you see the quality of your data, and you know what you've got. Disadvantages is that if you wanted to know what the time versus temperature relationship is and try to find that peak temperature, for instance, that would take numerous scans. You'd have to come back to the site, rerun your tests over and over again until you found that particular time. And it's also kind of a scheduling issue. You have to have a little knowledge of the cementitious properties and when it's going to get to its peak temperature. So you need to stay within a 1 or a 2 day window around the peak temperature, depending on the size of the shaft. The larger the shaft, the larger the window, and vice versa. And of course, method B, method B kind of sidesteps that problem because there are no scheduling issues. You're recording constantly. So your time versus temperature is very easy to obtain. Disadvantages: wires are not reusable. They're throwaway and they have a cost associated with them. There's the possibility that a data logger battery might go down. The connections might be breached somehow unwittingly, and you wouldn't know until you went back to collect your data collectors and realized that you had no data. So data verification is not occurring. You might know that it's working at the time that you plug it in, but who knows what happens a day later or an hour later. Of collectors, not that there are types of information that extending well above ground level out of the cage, and this is typical. Depending on, you have to give access to the testing firm to be able to get in there and look at it. Usually have 1 tube per foot of diameter, and for thermal, the tubes can be steel or plastic, PVC. If you're using gamma logging, you would like them to be PVC. If you're doing cross-hole sonic logging, you don't want them to be PVC, you want them to be steel. So again, the thermal doesn't really care. It's fine for both. We talked about when to test. We'd like to test in a window around the peak. And this is kind of important. If you think about, like here, this 11-foot shaft, it has a very broad peak up here, and this is in hours. I don't know how this is actually correct. I'm a little suspicious of these data points, but whatever, there's a very large window over which you get the same temperature. And that's important. If you've got 10 or 15 or 20 trucks coming in there, the first truck obviously is going to be older than the last truck. And so its hydration time is going to be advanced relative to the last truck. So you want to pick a time where all the trucks have essentially come to the same temperature. So that's, that's kind of important. Larger diameter shafts, of course, will be hotter. And depending on your mix, of course, that could be extended as well. But whatever, this gives us kind of the ability to calculate what would be a good time to go do your testing. And for instance, if you had on the right-hand side, we have slag replacement. So if you're up to a 60% slag replacement, which is fairly typical, and you had a 4-foot diameter shaft, you might be able to test that. The earliest you would want to test that is at maybe 15 hours. And the latest that you'd want to test that is about 49 hours. So you got about a 16 to 50 hours is your window that you'd like to be able to test that. And that's pretty broad. Usually you can get a team out there in time to do that. If it's a slag mix, slag mixes usually run between 20 and 30% replacement. And so that gives you a kind of a tighter window. You want to get out there between maybe 13 and 40 hours. Most of the time, you want to get this thing between 24 and 48 hours. That's really the magic number. 24 to 48 hours is when you want to test. Of course, 36 is right in the bit. It has to be a daylight time. Method A is sensitive to this, of course, because you have to schedule people to get out there. The method also requires that you dry the tubes. The tubes are oftentimes filled with water for cross-hole sonic logging, and cross-hole sonic logging needs that acoustic bonding, that coupling, to be able to send the sound waves throughout the concrete. But for thermal, we don't want that. So we might have to dewater the tubes. When you dewater the tubes, that's kind of an interesting process. We'll talk about that a little bit. The probe itself, because it could be cold, It could act as a heat sink. If it's plastic or steel, it has a different time frame required. You don't want anything that you put in the hole to attract or change the temperature of your system. So you warm the probe using either the warm water that's in the tubes to start with, or in some other fashion. You have to record your tube layout. You want to know where are the tubes? Is tube 1 north, or is it a little bit northeast of north, or something like that? You'd like to have an idea of the layout of your tube. You need a depth wheel. You're going to put that up on your first tube that you're going to test. And then you're going to set the tube, your probe, at a specified location, usually where the window of the infrared sensor is right at the top of the tube, or at some known distance from the top of the tube. Click the start or set top button, and then run your test. And when you get to the bottom, you mash it and you click a done button, whatever. This is all software related kind of procedural issues here. Again, you've seen these pictures before. You have some depth wheel that gets put onto the device. You have a miniature computer. You have some kind of a USB connection between the thermal access port for probe and the computer. And then, of course, both your depth wheel, which is a depth encoder, and the thermal probe all tie together through the thermal access port. This is very, very specific to a given era of software, and I understand that they're going to change, but in general, it's going to be about the same. Yes, smash the button to start the computer. This particular software does have kind of a splash screen that's going to come up, and then almost always follows by a driver white page, meaning that the drivers are being installed, and as long as this white page or white screen is being shown, you should not put in your USB, because it will not recognize the USB unless this has been finished. Once it's finished, it'll go to a regular opening screen. This is essentially your desktop where you've got your software. You can go in and hit the start the thermal USB tap button, and you'll be able to start your test. You can also plug in your USB at this time. So again, you need to be able to connect the USB to the device and over to the thermal access port. All these things have to all be plugged in. As you can see, they come in from all sides. The thermal access port is just essentially hung on the side of the shaft. The software itself, the data collection software, once you do hit that button on your opening screen, you're going to get some kind of a screen here. This particular version of the software says just click it once with it's a stylus, regular pen type. You can use your finger as well. It's because it is a touch screen. And you have to go through the initialization. This should look familiar to anybody that's done cross-hole sonic logging of any kind. You want to give some kind of a project ID. What shaft is it? If you have calibration values, if you're using different kinds of wheels, they have different calibration constants on them. Where are you always going to set your probe relative to the top of tube, or is it going to be right at the tube, or are you going to be a foot below the top of tube when you start? These are the types of input parameters, tube spacing, tube length. You always want to drop a tape measure into every single tube to be sure that the tube A is clear to the bottom of the shaft, and that you have an anticipated length of data from which you're going to be collecting. And then the distance above the concrete, we call that the tube stick-up height. That's not helpful information, but you need to know what length of data to subtract from the rest of your data to make it useful. I told you that most tubes are filled with water. This is a point of contention. Many feel that the water helps the tubes from becoming debonded at the time of concreting, when it goes through the highest temperature portions of it. If the tubes are full of water, then it won't debond. If they're not full of water, they might debond. This, again, different entities have come to different conclusions on there. If it's full of water, then you need to get rid of the water before you do a method A type test. And so the method that we use is to slip a tube all the way to the bottom seal it with some kind of a ferrule type fitting, and then apply compressed air over the water. And that keeps you from having to pump water. You can't pump water more than 1 atmosphere, otherwise it will boil. So this allows you to push the water out instead of pull the water out. The other thing that's kind of nice about it is by the time you get to the bottom, once this water level has been drawn all the way down to the bottom, you have a large volume of compressed air in there, and that will try to vent very quickly towards the end, and it will help to purge that last little bit of water that might be in the tubes. And so it'll come up a little bit violently at the same time. But we store that. It doesn't matter what kind of storage containers you have, you just have to have enough storage containers for the amount of volume that you're anticipating. So again, dewatering is just a general phase of it. Again, you have to have enough containers. You can run the math. I don't know if you're using 1.5 inch or 2 inch diameter tubes, but make sure that you have enough containers to store all that material. Before you run a thermal test, though, you want to make sure that a tube that has just been dewatered has a chance to acclimate and come back to the temperature of the concrete. You're essentially pumping in air. The air might be very hot from the compressor, or it might be relatively cold, depending on the difference between the air temperature in the compressor and the concrete temperature. So you want to leave this about 20 minutes to give it a chance to come back to the concrete temperature. Generally speaking, if you have 4 tubes or more, you would start on tube 1, dewater it, and work your way around tube 2, tube 3, tube 4. And then by the time you were ready to test tube 1, that had probably been about 20 minutes. And so you really don't have a wait time. You just want to make sure that you're aware of this. Large diameter shafts and very long shafts mean that you need more storage containers. Or, I'm not a huge fan of this, but it's reasonable. If you've got 10 tubes, for instance, and they're 100 feet long, you might dewater the first 5, run the test on those 5, and then as you move into tubes 6 through 10, just transfer the water from tube 6 over to tube 1, tube 7 over to tube 2, and just move all the water from one tube to another tube instead of having to have dozens and dozens of containers. There's been a lot of concern about whether or not you pump the water out, it comes out at 140 degrees, and then you put it back in after it's cooled down. We usually have not seen any effect of delamination from putting the now cooler water. It's not cold by any means, but cooler water back in there. We've seen no problems with that. However, you should be cognizant of it. If you're pumping out 140 degree water, Fahrenheit, and it's 30 degrees outside, then you're going to have much, much colder water when you put it back in. So we've even taken in, pump it into containers and then put thermal insulation bags around them or something like that, or blankets. So here's an example of the process here. This is, again, a 10-foot diameter shaft. You see the gentleman on the left is setting up the test. The guy in the center there is snaking the tube all the way to the bottom. And again, you have to have enough tube to make sure you get all the way to the bottom. It's nice to have markers on the tube, depth markers, so you're not caught unaware. The fact that you may have only put the tube down halfway and it got caught on a coupler or something like that. So it's good to know what length of tube you have put in the water. This right here is what we call the air head. It's kind of a specialized fitting. If you look at it very closely, the tube runs through the center. It has a compression fitting here. Air is pumped in through the side. And this, I always like these to screw onto the top of your access tubes, but sometimes the contractor damages threads or they just don't have threads at all. So in this case, you see they're using a compression fitting. Again, very reusable. It's just that it's just one more step you have to do to tighten that up to make sure that it doesn't leak. This again is a large diameter shaft. So you see over here, 1, 2, 3, 4, 5 different containers are being used to hold the water. I believe this is in the summer, so it's quite warm. So you can see the compression fitting here. They're pumping water from one side over to another tube. So, and obviously it's not active right now. The compression fitting isn't tightened and everything, but run your test on the first several tubes and then pump the water back over to the rest of the tubes. And it's just an accounting issue. You got to keep track of it. The problem with this is that I'm not in love with the idea that you don't get a chance to look at all the data together, all 10 tubes. You can't look at all the data until all the data is collected. So again, we always do it in a clockwise fashion. So if I test the first 5 and then transfer water, there's a possibility that I would get to the end of the testing and realize I didn't like the quality of my data, and I would have to dewater those tubes again and go back and retest them. So that's the disadvantage of what we call hopscotching water or transferring water from tube to tube. It just doesn't give you the ability to get that sense of quality at the end. We mentioned the tube acclimation. There's multiple ways of doing that. One of them is to put the probe into the last tube you're going to test. Or in this case, they've put the probe right into the container and pump the water into that container. So the probe, while you're dewatering the acclimating from the first tube. So there's different ways that you can get the tube general. These are digital thermocouples, but thermocouples always have a baseline temperature to which they reference, and you're looking at the change in temperature. So again, thermocouples are kind of a funny little animal from the tube works. And these particular applications, by warming the tube, the sample or the probe before you do it, takes care of the whole issue. So again, we talk about calling tube 1 number 1. That's the northmost tube. Again, it may not point right there. If 2 tubes are equally suitable to the north, then you just need to tape it or mark it and note which one is in fact the number 1 tube. Okay. Always measure the length of your tube, measure the stick up. We talked about that. Note the tube elevation relative to some other common points. So if you actually have a elevation of the top of tube, that would be great to have as well. Measure the tube spacing, and sometimes you can actually get the edge spacing from the edge. All of this information can be input after testing, or it can be put in before testing. But here's an example of a northern direction there is to the bottom left of the picture. So we're just going to call that tube number 1. Now, for whatever reason, the reinforcing cage here didn't allow the tubes to be perfectly spaced. So that's why it's important for you to measure these distances. Now, you don't have to do all the crossing measurements like you would have to do for cross-hole sonic logging. This is just geometry. So if you measure your perimeter and then some crossing, 1 or 2 crossing, in this case, you only need 1 between the 1 and the 3 tube. That gives you enough information to finish out. Looking down inside a lot of these shafts, you can actually see the edge of shaft to the reinforcing cage. So you know, take the measurement. Take the measurement. How much cover do I have between my tube that I'm taking my thermal information from to the edge of shaft? If it's available, write it down. Okay, so we're going to set up our system on tube number 1 to start off with. Again, I usually have some kind of contraption there where I can hang the computer and hang the tap box, and all that stuff gets put right onto it. I'm going to drape the wire over the depth wheel, and right when it's at the top location, I have to figure out exactly what I'm going to use as my datum, my reference datum. And what you're seeing there is that we're just putting it right at the bottom of that little slot there. And then when you're doing your computer, you can tell them this is the top of my run, and it's exactly the top of the tube in this particular case. And so again, this is all done by the user with the stylus at the time right before they start the test. So again, the first thing we do, We start with tube 1. So we go to the software, we say, click on this button here and say, I want to work on tube 1 first. Then I'm going to go over here and hit set top. As soon as I hit set top, the computer is going to start thinking, and this done button will light up when it's ready to test. Again, the software may change, different versions, but these are the types of steps that you would have to go through. Once you see that it is ready to go, then you would start lowering your probe. Now, this is different from cross-hole sonic logging. You run the test from top to bottom, not from bottom to up to top. If you do top to bottom, then you're always seeing the virgin temperature conditions. If you do it from bottom up, then as you pull the probe up, you're literally pulling the volume of the probe out and wire, and you're pulling cold air back in. So as we run tests from top down, we're getting the accurate measurements and we're pushing hot air out. So when we're finished though, we would hit the done button and we're able to start comparing a few things. We want to be able to repeat these tube runs. We want to make sure that all the tubes have been done at least twice. I recommend 1, 2, 3, 4, 1, 2, 3, 4, meaning that you can run the test twice, but run them in order. Don't run 1, 1, 2, 2, 3, 3, 4, 4, because that may not have given you the opportunity for the shaft to come back to equilibrium. But we should be able to see that these things all stay within, I believe it's within 1 or 2 degrees Fahrenheit, or maybe it's Celsius on the ASTM. So each tube should be run twice to confirm that you get a reproducible information. Equipment warm-up may show up on one of your first tests. So the first or second profiles may not look like the ones when you come back to it later. And again, you should check all your data before you put your water back in. So again, we want to review the data. This is a screen that we would typically see when we review our data. We would go look at run 1 versus run 2, for instance, and make sure that everything looks right. In this particular case, I see that run 1 is crazy, but runs 2 and 3 look pretty reasonable. So I would throw away run 1. We only use one of the runs. But this is an example of the first tube that you test. It's very typical for the first one to be too cold if somebody hasn't let the probe acclimate. When we were finished and we look at opposite tubes, we talked about this in the first session, that if the cage is eccentric in the shaft, then that would show up as equal and opposites on tubes would measure high and low temperatures. So if this is tube 1, for instance, and this is a 4-tube shaft, then tube 3 should be the cold one. And in case that's what we see here, we see 1 hot, 3 is again cold. Again, looking at 2, not much difference here, but you should get a warm confidence that you've actually done the right thing. Tubes 2 here, tube 3. So if one's cold, the other one's warm. And again, that makes sense. There's no average being plotted here, but again, you should have reasonable looking data. So just kind of a quick recap here then. All these steps, if we've gone through and done everything completely perfectly, then we would just replace the stored water back in there. This keeps the tubes viable for another test. If somebody wants to come back and do a cross-hole sonic logging, you haven't done anything to damage the tube bonding. Procedure B, again, it's a very, very similar, but in the field, we do things a little bit differently. We have to be out there at the time of cage preparation so that we can tie the thermal sensors into the cage. We put 1 string of wire sensors. And again, they're sensors every 1 foot. Typically, you can order them any way you want, but 1 foot is off the shelf kind of availability. And we would put one string in per diameter of shaft, a foot of diameter. Any excess wire at the top of the cage needs to be sealed up in a little bag so it doesn't get hurt during concreting. And as soon as concreting's done, we'll pull those out of the bag, clean off anything that might have gotten onto it, and connect them to a thermal access port. Before you get out there, those access ports need to be fully charged. And we know everybody knows cell phones die quickly, sometimes faster than you want them to. When they get to the end of their life, you need to be aware of how healthy your thermal access port batteries are. And you can change the sampling rate, but again, the default is 15. In the field, there's really nothing to do other than the fact that that thing is charged. And you get there, you plug it in, it immediately starts taking data. So you don't have to do any programming in the field. What am I seeing here? I'm seeing craziness. Okay, turn your eyes sideways, and no idea why it's going in here. That is insane. I wonder why that's like that. If I can pause for a second and fix this. Okay, that's the beauty of recording, I guess. So what we'll typically do, and again, we keep talking about 4 wires, but 4 wires is the minimum. So we have here a 4.5 foot diameter shaft. And what I'll do is I'll take all 4 rolls of wire and just stab a bar through the center of them, and so that I can pull all of them down at once. I put little spacers in here. I see these little PVC tubes along there. I just use those to keep it from dragging the sensors across the bottom of the reinforcing cage. So I tie them all together, and then you can see this rope right here. I pull all wires down all at once. It's actually not too bad. And then they've got these new little toys called a PEX gun, where it just automatically ties it into place. You can use tie wraps, plastic tie wire wraps, and all those things. There's all different ways of attaching it, but you want to attach these things at the same radial position. So it's kind of important. Again, where we have tubes that get tied in, they're kind of like pieces of rebar that get tied into them. We would put them hopefully right on the stirrup, but the important thing is they have to be the exact same radial distance from the center of heat. And that's kind of the principle of this. If you're doing the thermal wires, like we see on the right, then of course they're at the same radial distance, but they're going to be usually adjacent to the main wires. We would never want to tie tubes where some of them are on the bar and some of them are on the stirrups. Again, we want them to be all of them the same radial distance. Crazy computer stuff here. I thought I had this fixed, but again, we're tying that with this device to the cage. Okay, quick fix there. Again, we're attaching these wires. They have to be all the same position and next to or on top of the wires. We usually put them adjacent to the main bar, and then again, use this little tie wire. You can see the wire actually being spit out. It goes around 3 times and then ties it for you. It's kind of interesting. Bundling up all of the wires up at the top there, and then again over here, you can see that the wires are bundled there. Once they get to the top, then that's when we would open them up, pull them out, look at the serial number on each of the wires, and attach them to each of the thermal access ports. And again, we want to make sure that we record which probe it's been attached to at any given time. So kind of following up again on this particular procedure, the final thing is we would just have to come back, and we would give ourselves plenty of time, 72 hours minimum. 36 would be like a fly ash, and 72 hours would be required for a slag mix. But don't come in any sooner. There's no reason. Allow this thing to run as long as it possibly can. Even if the batteries die, you can always charge them up and get your data out later. Okay, so that takes care of session 2. I'm going to talk about data analysis now in session 3. The ASTM, and this is pretty typical of most of the geotechnical testing ASTM standards, they provide how to run the test. They don't provide you how to analyze the data. And so standardization of these test methods is difficult, and usually entities have to take on their own rules. Department of Transportation or something similar, they say you must follow a certain set of guidelines for doing it. And without that, though, it becomes subjective, and different people can come up with different solutions. So what we're going to do here is we're going to go through and try to standardize the procedures that you should be using based on a bunch of experience, a bunch of empirical information, as well as some numerical modeling and theoretical determinations as well. We need to be able to correct for end effects. We know that the shape of the temperature profile at the end is not necessarily the shape of the shaft, so we need to be able to correct for that. Obviously the amount of time that the energy is dissipating will affect this. And we have to look at the fact that we may have different boundary conditions. We might come out of the soil, go into water, come into air, or something along those lines, and that will change the heat dissipation and therefore the internal temperature. So we're going to try to give you some guidelines on how to handle that. We've talked earlier about the fact that we do have heat dissipation into the air that gives us actually convection, which is fairly effective. But conduction is the primary mode in the soil. As we get a bunch of heat generation within the cage, we of course get some kind of temperature dissipation here, darker red being the hottest, and of course cooler being the blue. And then we know that there is a bell curve, some kind of a temperature distribution within there that peaks at the core, which may not be the center of the cage, but is the center of the heat mass itself. When we look at a typical temperature profile, we would expect to see straight profile if the shaft is straight near the center of the body of the shaft. And then as we get to the ends, it will dissipate as we've seen earlier. Anytime we, of course, are taking our measurements at the cage, we are not taking measurements at the core, which is, again, very important. That's probably an emergency get out of town card there for the hurricane, but nevertheless. So we've taken these two temperature measurements as well. Let's see if I can. As the temperature increases, perhaps locally, we get onto a new bell curve. So we have more temperature locally because of this increase in diameter, and that shows up as a bulge in your shaft, which is also a bulge in the temperature profile. And this is what it would look like. This is an example of real conditions. You see the normal end conditions on this profile, and then you see a bulge anywhere between 32 and 42 feet. And you notice that it's not completely a symmetric bulge. It's bigger in the direction of tube 2 and smaller in the directions of looks like 1 and 4. But regardless, for a uniform shape, you can use this eccentricity opposite sides changes pretty well. But as soon as you get a bulge in there, those things don't always, they're not equal and opposite around the average, is my point. Now, if we have a shaft that has the cage moved, what ends up happening, again, one side gets colder, the other one gets warmer, but the average is roughly exactly the same. Or, well, not roughly the same, exactly. Those are fighting words there, but that's the point, is we would expect to see the average to be straight because the shaft is straight, but the cage placement may not actually be. And we see this in data, and we talked about this in some of our other sessions where equal and opposites, if it's just cage movement and not a bulge in the shaft, then we would expect to see equal and opposites. Again, this is another one of those cases where there's a temporary casing near the surface. It runs down to, it looks like at about 28 feet from the probe. It looks like ground surface is at about 8 feet. So it's about 20 feet of temporary casing, which would be straight. And then after it gets out of that, it transitions into a smaller section as we go down. Now, this is a normal transition. This is what I would call a real transition, meaning that the shape actually does change. Temperature transitions don't always mean shape. They can be boundary conditions that cause it as well. But again, what are we talking about here? We're talking about cage eccentricity. That what is called the adiabatic condition, meaning that once we get larger than about, looks like about a 6-foot shaft, once we start getting larger than that, the shaft becomes so massive that there is no dissipation radially that can get rid of the heat, meaning that all shafts, in this case about 7 feet or larger in diameter, come to that adiabatic core temperature where there's no loss of heat and it's trapped there, and that's as hot as it can get. So that actually does occur quite a bit. But now let's take this and go 3D with it. Let's add an axis to this, meaning that those shafts those curves are getting larger because of an increase in shaft radius or diameter. And so this kind of relationship is extremely important for us to understand, that temperature can increase because of size, or it can increase because of position, where were the temperature measurements taken, closer to the core or closer to the edge of the shaft. This is a snapshot. If we look at each one of these bell curves again, these lines here that you're seeing on the left side, that's the position of the cage relative. So if this is a 4-foot diameter shaft, then this would be the cage location, which would probably be about 1.5 feet from the edge. Depends on your cover criteria in your particular area. But you'll see that there's a general increase in the cage temperature as your shaft gets bigger, but it doesn't really increase that much. And the other thing that I find interesting is that the slope, the gradient of these curves do not change significantly either. If you look at the actual location of the cage for a 4-foot diameter, anything hotter than this particular temperature vertically, again, is a change in shaft size. So if we're looking at the average temperature, and the average temperature in this case is greater than about 132 degrees or something, then we're talking about a larger shaft in that location. So let's look again, let's go back to then the 3D plot here, where we have radial position. They would be equal and opposite if it's perfectly centered. The black lines represent the location of the cage. What is this? This is about 2.5, 3 feet. This must be for like a 5-foot shaft or something like that. And if it's perfectly centered, then both the yellow dots are measuring the same temperature. Oh, look, it tells me right here, shaft radius is 6 feet. So, you know, we're just inside 6 inches as our cover where the cage location is occurring. So that's the type of temperature that I would expect to see. But again, this is a snapshot in time. This entire curve started off much, much cooler. And notice this is at 3 hours. And then as it gets warmer and warmer and warmer, I get more and more time, it gets hotter, and my actual temperature to radius relationship is constantly changing. It's evolving over time. So if I take a slice through this thing at the location of my cage, this represents what we would call the T to R relationship, where the independent axis is temperature, and Y is what we kind of want. We want to know what radius does that temperature represent. So this can be then plotted in 2 space, where the temperature to radius relationship is truly represented by a hyperbolic curve. That's the blue curve that you see there. It's a tangent hyperbolic curve, that's the true relationship. But we find that in this region right here, there is a linear portion right around the size of the shaft. This is the average shaft size from concreting logs, and this is my average shaft temperature at the cage for this time, and this is only at 3 hours. So this slope is what we use to do our correlation, a very simplistic representation of the hyperbolic model. And this changes with time. And you can see that the actual slope is decreasing with time up into a point where it gets to a peak, and then it starts to actually go the other way and come back down. Temperature starts to decrease. So at a particular peak, in this case, it's about 0.25 inches per Fahrenheit, or about 5 degrees per inch. So this is pretty typical. And how do we get this relationship? This T to R slope can be immediately approximated by knowing the volume of the concrete that's placed, the length of the shaft, and I turn it into an average radius. That average radius then is equated to or related to an average shaft temperature at the location of the reinforcing cage or the location of the measurement. All measurements from all tubes or wires need to be the same radial distance from on the cage. You've seen this before, where this type of T to R relationship then is able to give us what I call an effective radius. Now, it's important that we differentiate effective radius from real, get out there and measure it with radius, because this is temperature. Temperature can be, it can occur different ways. You can have a very large diameter, but of poor quality concrete that produces a temperature, or I can get that exact same temperature with a very small or a smaller diameter of very good quality concrete with high cementitious. So if your concrete gets watered down or it gets diluted by cuttings or something like that, then of course we do get this problem where you get the same temperature, but it's a much larger size. So again, effective radius is talking about what would an intact concrete look like? What would be the shape or the radius of intact concrete? So it's kind of a small distinction, but it's important that you understand that. Recall that, again, these T to R slopes, they don't actually have to, if you had an enormous amount of information, and I'm not really sure that this is representing that data very well. I'm not really sure where that curve's coming from. If I were to extrapolate that line back there, you would see that it's not actually coming back through zero. We've been using this approximation 0 to the average temperature to get our T to R relationship. And so we technically usually underpredict the severity of change in radius from a change in temperature. That's the mode usually. Now, what's important about this is that there were, in this particular case, and you knew this case already, there were so many different radii in the shaft that had different temperatures that you could actually develop your own multi-point T to R relationship. But we would like to use a single point. Oh, this is the single point. I'm sorry. This goes all the way back to 0 degrees, is way off the page here. So that's what this line is shooting for. This line is shooting all the way back to 0, which is what I call a single point T to R relationship. And that's what we typically do. And notice the slope of it is less than the true hyperbolic, and the true hyperbolic would give you a very, very close approximation of the T to R relationship. But the single point, again, underpredicts the severity of variations in your shaft size. Again, this is kind of to keep the testing firms from, screaming that it's a really bad shaft when it's not. Okay, so the more common occurrence, though, is that we have a very, very straight shaft, and the radius that we get from our concrete, we only have 3 trucks, for instance, they tend to not have a large amount of variation. So when you plot the radius from the trucks versus the actual measured temperature, you realize that there's really no relationship at all. So that's essentially data scatter. So this is where a single point T to R comes in to be very, very helpful. because it generally does represent the hyperbolic linearity of the inflection point, and gives you a convenient way to assess the rest of the shaft that is not at the average temperature. That's the whole benefit. So the different types of analysis, our traditional method is to get our construction logs, or what we call the construction or the concrete yield plots, and determine what is my average shaft radius throughout the entire length of it, and then use that to calibrate its thermal models. We just talked about that. You can do some advanced 3D numerical modeling as well, but unfortunately that's very subjective. It's very subject to the changes in the cement properties, which are sometimes difficult to predict. So let's talk about just a kind of a standard analysis. We want to make sure that we collect data within a reasonable time frame. We talked about what that would be based on staying near the peak. The data has to go full length. It has to go from the top to the bottom, because you're determining an average pile or shaft radius using the full length and all your concrete. If your data does not extend to the full depth, then you don't know the average temperature of the entire pile. You want to make sure that you align the data. The data, maybe if they're on 12-inch increments, maybe they're not completely aligned. Maybe the one wire has a few extra nodes sticking out the top, and so you can't just always start with the top node and assume that's the top of the pile. My point is, all the data left to right, north, south, east, west, across the shaft, all those data points have with each other. From that, then, you can take each of the data points from all sides of the shaft and prepare an average temperature profile. The average temperature profile is where we do all of our corrections. If we can fix the average, then we can determine the T to R and then produce the individual radial plots of each of the different tubes or wires. So we'll get the average, then we'll adjust it based on heat dissipation modeling, compute the T to R constant. That's pretty easy, average temperature, average radius, and apply the T to R to all the individual locations. At that time, then we know how much physically, we actually know how much the cage has moved, because one side says the radius is 19 inches, the other side says the radius is 21 inches, then I know the cage has moved 1 inch in one direction or the other. But sorry, phone call just came in. Difficult to record when you're doing that. Adjusting for the end is that's the tough part. So we talked about the suggested time frame. I showed you these plots before, but I didn't give you the equations before. So what these are based on is that the minimum time, the earliest you want to take the test, is 0.02 times the diameter of the shaft. And then you go into fly ash or slag percentage. And again, that's what D is and all these things. So D is the diameter shaft. Diameter shaft in this case is in feet. So if you're going to use these equations, again, convert from meters to feet. And then the F and the S are percentages. T is in hours. So it'll spit out a time that you can do it. You've seen these curves before, but this is where the equations that are being used for this. There's one little issue though. If you know that your shaft or your contractor or your concrete supplier is maybe coming in from pretty far away, and so the batch plant might be an hour or two away, you may have to increase the amount of time that you put in. Once you've made these calculations, you might want to add on another 8 hours or something if that's what the slump retarder dosage was producing. Again, these, I may not have mentioned this before, but what these equations are doing is it's saying, I'm going to find at what time 90% of the peak occurred before the peak, and then at 80% of the peak temperature afterwards. So it's that little top of the bell curve, or top of the time temperature plot that we're looking at. Again, the importance of full length data. If you have full length data, then you will clearly see the bottom of the shaft. Washington Department of Transportation, they want to always produce the raw temperature profile so they know what's going on before you correct it. So they want both the raw temperature and the corrected temperatures. In this case on the right, you see that there is no roll off at the bottom, yet they're reporting the bottom of shaft, and again, this is just from field records, to be down here, I don't know, at about 50.5 feet or 50. The bottom of shaft's probably at least another foot down from that. So you can start to get an, if the profile is absolutely straight and that's raw data, you're missing a large chunk of the bottom of your shaft information. So they may have over excavated and hung the shaft and conducted separately for the top and for the bottom. And it requires that you know what bottom and what's the asymptotic temperature of the shaft itself. Now this is model data here, so it's pretty perfect. And then going up to the top though, there's an inflection point that occurs in the temperature profile, which is not mathematically halfway between this temperature, which is measured, and the temperature is here. The relationship at the top, the inflection point is generally the top of shaft. So the temperature at the top of shaft is the inflection point, and the hyperbolic equation then runs off into Never Never Land. And this whole region here is unrealistic. It's unreal data. So again, we'll be thinking about that as we move. So this relationship is what we're going to be using to fit this, and then see if this temperature relationship makes sense. If it's not realistic, you shouldn't be using it. You can fit a hyperbolic curve to this and to this, but it may not be realistic. And this is always a concern when you're doing any kind of curve fitting. And this relationship then means that we have a fit equation, and then we have the corrected equation. The fit equation is plus or minus based on if it's the top or the bottom of the pile that you're analyzing. And notice that at the top, here's my inflection point, and that we're going to use mathematically. So there are some asymptotic temperatures, a high temperature, a low temperature. Then there's an imaginary low temperature that's way over here somewhere. We don't look at it. So we want to know the inflection temperature at the top, and we want to know the soil temperature at the bottom. So the plus or minus, again, max and min. Max would be, again, the hot portion of the shaft. Min would be way over here or way down here. Inflection temperature, of course, is this point or this point. And then depending on if you're doing a top analysis, you look at the inflection point. If you're doing a bottom analysis, so let's look at top roll-off parameters. What are the things that we need? We call this T0. That's the temperature at the inflection point. T minimum has no physical meaning. I mentioned that before, but it is essentially this distance or this temperature difference between peak and the inflection to T min, which is over here. The T fit for the top uses the minus of the plus or minus formulation of the T fit equation. And then there's also an interesting point here. what depth does the inflection point occur? And then the alpha, which is an indicator of the transition length. Now, we mentioned earlier that immediately after the shaft is poured, there is no transition length. Everything is all the same temperature. So alpha tends to be time dependent. At the bottom of shaft, the T minimum is given by the local soil temperature. The inflection temperature is exactly half the distance between the max and the min, which is the soil. And again, T max is registered straight from the shaft measurement. Again, Z0 here is the inflection depth. And we find that the inflection depth actually changes with time. It transitions out of the shaft. We'll show you that in a moment. So these are the types of information. Notice the T-fit equation is exactly the same equation as before, but now we're using the plus and not the minus formulation of the equation. Ground temperatures, I know this doesn't help you in Sri Lanka, but these are typical ground temperature profiles for the US. And how do they get this? Well, it's actually the average annual air temperature. So you can get that anywhere. Don't take just day temperatures, don't take just night temperatures. Take the whole year because that's how long it takes. And it takes 2 or 3 years if you were to run a model to find out what your soil temperature is. At depth, the soil temperature is the average annual air temperature of that location. So that's how we would find that. The transition length, which is in the equation, uses the alpha term. Alpha is not the full transition length. Transition length would be where it goes from maybe the inflection point up to constant temperature, but alpha is the one that's kind of the indicator of it, where these two lines, if you did a linear intersection. But notice that early on, when we first place the concrete, we might place it at maybe 81 degrees at 0 hours. There is no transition length at all. It's zero. It's just soil temperature and concrete temperature. Then you give it a little bit of time. Not only does the heat, the temperature, concrete start to hydrate, but we start to transition into the soil as we transfer energy into the soil as well. So mathematically, the inflection point is not now the edge of the heat producer and the heat dissipator. So you got to keep that in the back of your mind when you're doing this analysis. And I have some quick numbers for you to be able to handle. So let's just look at a quick case study. Hopefully this is helpful. It's a 4-foot diameter shaft with a upper oversized partial permanent casing, which is interesting because permanent casing gives you the ability to say, I know absolutely what the diameter should be, although that is a little bit of a falsehood in that you can still, inside a permanent casing, you can still have bad concrete. They use 5 wires here because it's greater than 48 inches. We did some computer modeling to mimic the conditions, and then we did all the looked at all the things both numerically using field data as well as numerical modeling. So we look at the effects of time as well. So here's our raw data. You're seeing a little bit of cage movement down near the bottom. You're seeing that there is a change in temperature, a change in diameter from here to here as it goes from regular soil into a rock condition. You're also seeing that there is a transition here. Now, again, this is my casing, right? So the casing goes from here, bottom of casing, all the way up to here. But right here, you're seeing a huge change in temperature. And that's because it comes out of the ground and goes into the air. There's a transition here. And that didn't have to go into air. It could be anything. And I believe in this case, they had a secondary casing around the interior permanent casing, and the secondary casing was larger and it was oversized again, and it had an air gap between the interior casing and the outer casing. That gave that air gap between the interior casing and this exterior casing, didn't allow it to get larger. The shaft wasn't getting larger, but it acted like styrofoam. It acted like an insulator outside of it. So this region actually got hotter because it couldn't dissipate heat. So there's a transition here from external conditions. That's what made this kind of an unusual circumstance. This is the correct transition that I would expect from oversized casing, 54 inches down to a 48 inch. But we still have to correct the top and the bottom ends. And in this case, we have to do what I call a mid-shaft correction. We have to correct for the change in dissipation field. So when we model this, we looked at some low diffusivity regions at the top. Then we had our regular soil conditions down here, and then we had a step in the shaft from the tool sizes. So all this stuff was able to be modeled reasonably well. And lo and behold, this is the outcome of our modeling. We got the same profile that we got before. But this transition is something that we can correct. We can turn this back into a straight shaft if we understand how this works. So the transition, there are three transitions that are occurring here. One, there's a top roll-off condition where we have to, again, know the maximum temperature, the minimum temperature. In this case, we want the inflection temperature. We don't care about the minimum temperature because it's at the top. We want to know where the transition occurs. And mathematically, in a model, in a numerical model, we know exactly where Z0 is because, again, the model is perfect, let's say. The transition temperatures, the difficult thing about this one is this region right here. There's a transition, a hyperbolic transition from hot to cold. And if we can fit this and it stays inside the normal expected alpha values, notice these alpha values are very close, 1.4, 1.25, 1.28. It's fairly typical for the bottom transition zone to be slightly higher, but again, it doesn't have to be. Once we take that temperature and apply the transition, and this is a fit, remember there's the T fit and there's the T corrected, we can actually plot T corrected and get rid of that transition. Now we've got effective radius that reflects the actual shaft conditions. The inflection point temperature from modeling here, the inflection temperature changes depending on what time you are analyzing it. The longer you go, the closer the inflection temperature gets to become the average air temperature. So early on, you're going to see more variations. The temperature is going to be more subjected to it, and then it's going to level off and get closer to it. So this inflection point temperature should essentially be, it can be anywhere inside the average air temperature or the air temperature for the day before. But in general, I typically pick the average of the day before. Going back and playing a little bit of math here, we went ahead and determined the alpha factor for all these. I'm going to back into this a little bit later. It turns out to be about 0.32. We'll see this later. You can see that all of the transition, these are the T to R relationships that we're getting from the hyperbolics. They're all between 0.3 and 0.35 or something like that. Again, that's what we also have found in the field as well. So going back and looking at our raw data, not the model data, but the raw data, and applying these repairs to it, the only thing I don't like about this, and this was done so that the alpha fit perfectly, but this alpha is too large. Notice that the 1.3 and the 1.2, those are reasonable. They're very, very close to the model results. Give us good clean bottom, give us good transition here. But the top, I'm going to call this overcorrected. This is too much transition here. And so I do think there was a problem with the shaft here in the top. But this alpha is what was required to fit it perfectly. And we'll talk about that as we go into case studies of different, hundreds of different shafts that we've tested. There's always a question, well, is the analysis better if I do it at peak or just after peak or slightly thereafter? And the answer is, if you're within that time frame of 90% of peak on the way in and 80% of peak on the way out, then you're going to get good, reasonable results. This is the effective radius profile that you get from analyses run between 9 and 23 hours after casting. And you find that you get the exact same profile. These are average profiles from all those runs. Those are not different tubes. That's the average profile. So you see very, very little variation from that. If you're talking about just the hyperbolic T-fit and T-correct equation, it's always kind of good to have an understanding of which one of these things are very, very strong parameters and which ones you have not as much confidence in. And so this plot kind of helps play with these strong and not so strong parameters. For the most part, we don't really have any weak parameters in here. The top roll off the peak temperature, we get that straight off of it. We know exactly what's going on. The peak temperature from the bottom, we know exactly what that's going to do. If it's a mid shaft, we understand what the high and low temperatures are. So very good confidence in those values as well. T-min as well at the top, it really doesn't, it's not applicable because it's an unrealistic value. It's the other side of the hyperbolic. So it's not applicable here, but the average annual air temperature, very, very well known. That's the at depth soil temperature. No problems with that, very strong. And again, for mid-shaft corrections, a minimum is quite easy to get. So again, temperature, average air temperature, this one here is not as strong. It could be anywhere between the peak air temperature of the day before or the lowest temperature of the day before. So I wouldn't say that if you pull the average air temperature off it, it's a strong value or not. As far as where the inflection point occurs, again, pretty strong on those. When you're doing a mid-shaft correction, do you really know where it transitioned from soil into air, or where was the bottom of some kind of change in parameters? This one can be strong, but oftentimes falls under medium confidence, let's say. Then the transition length for the top, bottom, and mid shafts, they follow a square root of time function. And this student, this is Dr. Kevin Johnson, prepared this slide. He thought the typical range for the alpha factor should be between 1 and 5. I feel like it should be closer to 1 and 3 because at 5 you're way out at maybe 80 or 90 hours. But between 1 and 3 is those are reasonable values. So how do we get so much confidence with this? A bunch of tests. So what we're going to do is we're going to talk about curve fitting 400 plus shafts and seeing what were the dominant parameters that came out of Tmax, T inflection, the inflection depth, both top and bottom, and what is the best transition factor alpha that could be used for these. And then, of course, we've already seen what this looked like in theory. So we're going to take a case study in Tampa, two side-by-side projects, and very, very similar, slightly different mix designs. But again, 158 shafts from one site, 245 from another. What's interesting about the second project is that this was a 100% testing. Every single shaft on the project got tested. 15%, usually that means that you're testing only the ones the inspectors thought there was a problem with. So this 158 shafts is largely going to be populated with questionable shafts, whereas the 100% testing project, that's the population. That's just the full population. So it does help to have large populations like that. Looking at some raw data, these are the values that we're looking for. We literally empirically fit every single one of these values by exhaustion. What's the best inflection, peak, minimum temperature, alpha factor? What were the best parameters to make the red line fit onto the field black line perfectly every time, or at least with the smallest amount of error? So this algorithm was applied to all 400 shafts. And so in iterating through to get this perfect red line on top of the black line, all these parameters would be adjusted and sweep through. And I believe it turns out to be about 250,000 iterations for the top, 250,000 iterations for the bottom, and then multiply that times 400 shafts. So we calculate what the transition length was for each of these things, again, using this alpha parameter. But we know that alpha is a function of the square root of time. So we would really like to have an equation to fit these things a little bit better. And from mechanical engineering, we know that the diffusion of a cylinder into an elastic medium or a semi-infinite body gives us this relationship of alpha being equal to some constant times the square root of time. So we're looking for that value. We want to know what that constant should be for all testing here forward. So we back calculated the alpha coefficient for each of these, and we find that we get a pretty strong median value. It's not a normal distribution. It's kind of a skewed, positively skewed distribution, but we get a good confidence that both the top and the bottom alpha factors hover around the 0.4, and our standard deviation, plus or minus, is about 0.1 in both directions. So we replot that curve and we say, okay, here's our 0.4 square root of time. That's our preferred value. But if we go plus or minus 1 standard deviation up or down, if you're living inside that window, you're grabbing a large chunk of the population. But nevertheless, you do see some crazy ones out here that are way outside 2 standard deviations. And why? Well, because we were curve fitting, in many cases, shafts with bad bottoms or bad tops, something that was wrong with them. So in our population, we expect there to be bad shafts, and so there's going to be outliers in there. Looking at the inflection point temperature, I'm showing the highest and the lowest temperature in green and blue, and then the best fit inflection temperature from all the shafts. And what you're seeing here is in the winter months, the inflection temperature goes down with the temperature, and of course also concrete placement temperature is going down as well. But you're seeing that it clearly
Hello everyone. Professor Graham-Mullin's presentation about 10-15 just to keep up with our program, but we share this presentation with you through our YouTube channel. And also I like to thank Professor Graham-Mullin for his courage to send us the recording of his presentation just before the hurricane hit on Florida. That is a great thing. Otherwise, we will be connected to our program very. And if any contact Professor Graham-Mullin and contact to you. Thank you again, Professor Graham-Mullin, for your commitment. Then our next presentation will be on bridge foundation design. The Professor Emeritus, the University of Sydney, Australia. Professor Poulos doesn't need as a formality. I will read out about this brief biodata. Professor Poulos, senior consultant with Tetra Tech Coffee in Sydney, and is also emeritus professor at the University of Sydney. He has undertaken research into the analysis and design of pile foundation and offshore application. And in recent years, for high-rise buildings, he has been involved in a large number of projects, including Ignetia, for those 5-year projects in Greece, Burj Khalifa Tower in Dubai, the Dubai Tower in Doha, Qatar, and the Crown Tower in Sydney. He was elected a Fellow of Australia Academy of Science in 1988, of Australian Academy of and Engineering in 1996. He has received a number of, including Kevin Nash Gold Medal of the International Society of Soil Mechanics and Geotechnical Engineering in 2005. He was a ranking lecturer in 1989 and a Tesagi lecturer in 2004, and was selected as the Australian Civil Engineer of the Year for 2003 by the Institute of Engineers Australia. In 1993, he was made a member of the Order of Australia for his services to engineering, and in 2010, he was of the American Society of Civil Engineers. For a member of the US 2017, he received the Outstanding OPL Award for design from American Society of Civil Engineers. Most recently, he was awarded the Peter Nicol Russell for his lifetime achievements in engineering. Introduction, I would like to make this presentation.
Well, thank you very much, Chairman, and thank you very much to the Sri Lankan Geotechnical Society for inviting me to participate in your conference. And what I want to talk about today is a practical approach to bridge foundation design. And in starting this, I acknowledge the fact that this presentation is based largely on a fairly recent paper I did with your Dr. Jayanta Amaratunga, and that for anybody that's interested can be made available to you. It relates to what we think is a reasonably practical approach to bridge foundation design. What I want to talk about firstly are the design criteria, then the development of geotechnical models and the assessment of design parameters. I'll say something reasonably briefly about foundation analyses and some of the other issues that we need to consider when dealing with bridge foundations. And then I'll go briefly through one example where some of these principles have been employed on a bridge in Australia. In terms of the issues that we need to address in design, for pile foundations for bridges and indeed for any other structure, we need to look firstly at the ultimate capacity, then the settlement and differential settlement and the tilt. We need to be aware, we need to be aware of the response of the foundation system, the lateral loads and moments. We need to also be aware of the dynamic behavior and the response of the system to earthquakes. And then from a structural viewpoint, clearly the structural strength of the foundation elements needs to be adequate, as well as the durability of the foundation materials. In terms of the design process, there are three stages that I think we can use in this process. The first is a preliminary stage where we develop the concept and look at the broad choice of foundation. Then we have a detail stage where we develop and optimize the design and where we interact fairly closely with the structural engineers. And then in the final stage, we refine the analysis and the parameters and we check with alternative analyses. We use, if we have them, and hopefully we do, the results of pile load tests. And also we have our design peer reviewed. And I've got a note here that the design tools that we use should be consistent with the stage of design. So for example, in the preliminary stage where we're just getting a reasonable idea of the basic concept of the foundation, we wouldn't be wanting to use three-dimensional finite element analyses or something of that complexity. We would be using a simpler approach, whereas complex analyses may be more relevant for the final stage. In terms of design criteria, I think many places in the world, including my country and I think now the United States, adopt what is sometimes termed the LRFD, the load and resistance factor design approach. And the criterion for geotechnical design in this approach is that, putting it in simple words, that the factored down ultimate capacity of the foundation system has to be equal to or greater than the factored up design loadings. And there will generally be a significant number of load cases that will be provided to us by our structural designers. And we have to make sure that for each of those load cases, this criterion is satisfied. And that reduction factor, what we call the geotechnical reduction factor here in Australia, is selected based on assessing the risks and other factors, including construction conditions and so on. And typically in Australia, under the best conditions, that reduction factor would be probably 0.75 or less, and generally it is 0.4 or more. So that 0.4 is the lowest value that we would normally use in a design. We have a similar criterion for structural design, where again, the factored down structural strength has to be equal to or exceed the factored up loading requirements. And this is the phi S, the structural reduction factor, is generally based on code requirements in a particular country. In terms of serviceability, the criteria fairly simply are that the settlement has to be less than or equal to an allowable value, and also the lateral deflection has to be limited to an allowable value. And I've quoted here some values that perhaps are typical based on a report from the United States some years ago, which suggests that typically an allowable settlement would be about 50 millimeters. An allowable angular distortion would be 1 in 250, and an allowable lateral deflection would be about 38 millimeters, or 1.5 inches in old terms. Moving on now to what I believe is a critical aspect of any geotechnical design, the characterization of the ground and the development of a geotechnical model. I believe that ground conditions are probably the greatest source of uncertainty in many projects. And so it is firstly critical that we understand the geological history of a site, because this can often give us clues as to how the deposits on that site will behave. And we also need to understand the recent history of the site, because time zero doesn't start from when we get on the site. There may be ongoing processes. For example, there may be an old reclamation fill so that the site may still be consolidating, or there may have been groundwater lowering, and again, that may not have been completed. And we also need to ask the question whether after we've finished with our project, whether there will be changes in the ground conditions between the site investigation and the construction, and then beyond that. And I believe, and I think all geotechnical engineers would believe in this, that economizing on this phase of the project is illogical and potentially dangerous, because it is, in my mind, the greatest source of uncertainty. In terms of the ground investigations, These are as important for pile foundations as they are for shallow foundations. And so we need to extend our investigations to an adequate depth below the anticipated foundation conditions. And we need to be able to prove rock or the foundation material. And we need to particularly be aware of the possibility that there could be compressible layers below the level of the pile tips. I've shown here Tomlinson's suggestion for the depth of investigation for pile groups generally, and he's suggesting that it's something like about 1.5 times the breadth of the foundation below the effective depth of the piles. Here is another specific suggestion based on the Eurocode, and I've shown here just a typical 6-pile group of piles here. And the suggestion here is that the maximum depth below the pile tip should be the largest of the width of the pile group, 5 meters or 3 times the pile base diameter. But in all cases, what we're trying to do is to make sure that we understand what the ground conditions are at a depth of influence of the foundation system that we're going to design. Now, in many cases, in particular for preliminary and sometimes for the detailed design, we need to be able to simplify the ground profile because in many cases, that's where we start with. We have to use simplified analysis as a starting point. And a key to successful design is to try and convert the real ground profile into something that's much simpler but representative of the profile, and a profile that we can analyze using simpler methods. And so on this next slide, I've got some typical simple ground profiles. The first one on the top left is where we have a uniform semi-infinite mass with a constant parameter, and that would generally be stiffer materials, maybe even soft rock. Then you would have on the B, the right-hand top, a uniform layer with some average properties underlain by a rock. If you have a very deep layer of sand or normally consolidated clay, then you may well have a profile where the strength and stiffness increases more or less linearly with depth. And in sandy materials, that increase in depth, rather than being linear, may be more appropriately considered as parabolic. The key geotechnical parameters that we have to assess, again, with all foundations, pile foundations, the ultimate shaft friction in both compression and uplift, the ultimate end bearing, the soil stiffness or modulus for vertical loading. And we need, of course, to bear in mind that we have different values for short-term loading, where we have wind or seismic loading, and long-term loading with the dead plus live loading. And generally, the long-term stiffness is less, of course, than the short-term stiffness. We also need to estimate the ultimate lateral pressure between the piles and the soil stiffness or modulus for lateral loading. And if we're concerned about dynamic effects and perhaps earthquake response, then we need to know something about the dynamics, soil stiffness, and damping. How do we assess these geotechnical parameters? Well, we often do this in a preliminary manner by using forms of empirical correlations, particularly in the early stages of design. In later stages, ideally, we would do pile loading tests, or we would do some form of laboratory testing or in situ testing. But generally, in many projects, we are constrained to use empirical correlations. I think certainly at the present time, it's generally not practical to use very complex constitutive soil models. If you do at all, then it's in the later stage of major projects. So even then, we need to check the results with simpler methods. I've reproduced this interesting diagram, which Professor Paul Main from Georgia Tech in the United States put together recently. And on the vertical axis, he shows the relative reliance, and on the horizontal axis, the year starting from 1900. So this is, in a sense, an evolutionary history of how we assess parameters. And in the early days, we had SPTs and we had plasticity characteristics, and that was about it. And then in the age of Terzaghi, we came along and had a series of laboratory tests, odometers and triaxial tests. And we started developing cone tests and various forms of in situ testing. And as we've gone along in time, we've seen the growth of in situ testing, and in particular, the last 2 or 3 decades, the growth of geophysics. And we've seen what I think is a fairly consistent pattern of reduced reliance on laboratory testing and perhaps more reliance on numerical simulation and analytical models. And there is perhaps some also leaning towards probabilistic methods. But I think a lot of the testing and parameter assessment that we do today is down in this bottom right-hand area, in situ testing and geophysics. And so with that in mind, then, we can look at the various correlations that exist with SPT, the standard penetration and cone penetration data. And there's a lot of these correlations, and some of these are summarized in Dr. Amaratunga's book that he co-authored on correlations of soil and rock properties in geotechnical engineering. And for example, we have the ultimate bearing capacity for shallow footings, skin friction and end bearing for deep foundations, ultimate lateral pile soil pressure for deep foundations, and Young's modulus for shallow and deep foundations. So essentially, if we've got only SPT and CPT data, we still have a series of correlations which we can use for preliminary design, certainly. We also have correlations with soil strength data, and in particular, we have various methods for the ultimate bearing capacity for shallow footings based on values of cohesion and friction. We have correlations of ultimate skin friction for deep foundations based on both total stress methods, particularly for cohesive soils, the fine-grained soils, and also effective stress methods for all types of soils. We have similar correlations for end bearing for deep foundations in terms of total and effective stress, and also for lateral pile soil pressure. And also for Young's modulus for shallow and deep foundations. And we again need to bear in mind that because Young's modulus is a somewhat simplified representation of the deformation behavior of soils, we have to allow for the possibility that under vertical loading, we will have a different modulus than we have for lateral loading. And in our practice, we typically take a horizontal modulus of something of the order of maybe 2/3 to 3/4 of the value for vertical loading in the absence of any other data. And in terms of Poisson's ratio, because if we're using models based on elasticity, we have to have some estimate of Poisson's ratio, typically a value of 0.3 for drain conditions in most soils and in some rocks is reasonable. And if we have saturated soils, in particular fine-grained soils, and perhaps some rocks, impermeable rocks, then a Poisson's ratio of 0.5, looking at undrained short-term conditions, may be appropriate. I've got here specifically some correlations for deep foundations in rock, where we correlate ultimate shaft friction, end bearing, and ultimate lateral pressure with the unconfined compressive strength. And these correlations are probably fairly conservative. There are some more site-specific examples. For example, in the Middle East, we tend to use somewhat larger values of these factors here, the AS factor. But by and large, as a first attempt, these will give you ballpark figures on what skin friction, end bearing, and ultimate lateral pressure between pile and soil will be. Also, in terms of modulus, there are suggestions, and again, Tomlinson presents this, where, of course, our unconfined compressive strength is done on a sample that's fairly intact, but in reality, we may have discontinuities and defects and shear zones. And so to allow for those structural defects within the rock mass, we have reduction factors that are applied together with a correlation factor to apply to the ultimate, so the unconfined compressive strength. So these sort of correlations can be very useful for preliminary design. I just mentioned this developing approach that I think is going to be a method for the future, and that is using small strain modulus values which have been derived from in situ measurements of shear wave velocity. Because with these simple equations I've got on that on the diagram here on the slide, we can estimate the small strain shear modulus, and from elastic theory, the small strain Young's modulus. And if we want to take account, as we must, of the fact that as the strain or stress level increases, the modulus tends to decrease because soil behavior is non-linear, we find that in general, for typical factors of safety, we can factor down the small strain modulus values by a factor of 0.2. So we take 1/5 of the small strain values, and we get a reasonable assessment of the modulus, the operative modulus for our serviceability or settlement calculations. What I show here is the sort of diagram that I like to develop for a particular site when I'm doing calculations. We have on the vertical axis the depth, and then we have a little pictorial diagram showing the soil type and a description. And then in this one, we have modulus values, short-term and long-term values, Young's modulus values, and then ultimate skin friction, end bearing, ultimate lateral pressure, and the unit number. And we would also have associated with that any other parameters that we need in our design. But these are the basic parameters that I normally would use for a pile foundation design. Now, there are, of course, various forms of software which we can use in pile design and analysis. I've listed some of these here, and all of these I think are commercially available. Piglet, Randolph's program, P Group, which has probably now been overtaken by the program Repute, DefPig, which is a 40-plus-year-old program, which probably isn't really relevant anymore, but still works. LPile and Group 7, which are from the United States, and a program called LPLA, which is more for foundations than for bridge foundations, looks at vertical loading, and you can consider both pile foundations and pile rafts. Now, in general, when we're doing simple preliminary calculations, we often use an elasticity approach. And I've just summarized here for those of you who may not be fully familiar with how we use this approach. We use the theory of elasticity to get both short-term and long-term settlement values. And for the short-term estimate, immediate settlements in clays, for example, we use an undrained modulus and we use a Poisson's ratio of 0.5, and we put those into our elastic theory and get the immediate settlement. For the long-term total final settlement, ignoring creep or secondary consolidation, we use the drained Young's modulus and the drained Poisson's ratio to get the total final settlement. And the consolidation settlement then is the difference between the total final settlement and the immediate settlement. And if we're interested in the rate of settlement, then at any time t after the load has been applied, we have an immediate settlement plus some degree of consolidation settlement multiplied by this final consolidation settlement. Now, as I mentioned, there are some simple elastic based methods that can be used. And if we are, for example, looking at shallow foundations, which are probably not that frequently used for bridge piles, but for bridge foundations, but in principle they could be. You have this expression here that Paul Main and I developed some years ago. Average pressure times the size of the footing with some factors divided by a modulus value. And again, I've indicated undrained values for immediate settlement and drained values of modulus and Poisson's ratio for total final settlement. There is a basic value for the footing of IG with correction factors for the flexibility of the footing and for the rigidity, the depth of embedment of the footing. And without going too much into this, these are the graphs for the basic factor, and these are the correction factors which depend on the relative rigidity and the relative depth of embedment of our foundation. Now, if we're dealing with pile foundations, firstly with a single pile, which normally we wouldn't be dealing with a bridge foundation, but it's a starting point. Here is one of a series of graphs which we can use, which relates a settlement influence factor on the vertical axis, I subscript rho, to the length to diameter of the pile on the horizontal axis. And we have a pile that's going through soil of modulus ES and bearing on a stiffer soil of modulus EB. And so we have various curves for different values of EB on ES and for different values of the relative stiffness of the pile. And then again, you have this simple expression that once you've got a modulus here and you know the geometry and the modulus of your pile, you can very simply estimate the settlement of a single pile under the average sort of loading that you would expect in your foundation. And of course, in reality, we don't have in real soil profiles normally a constant modulus. So if we've got a layered system, such as is shown on the left-hand side, we have to convert that into an equivalent analysis that we can analyze. And this is one of the simplifications that I indicated before. So that layered system becomes a single layer with an average modulus, and you can just do it with this simple averaged modulus along the shaft. And that's bearing on a bearing stratum with an average modulus within the volume of soil influenced by the base of the pile. And so you can then treat that as an end-bearing pile. In terms then of pile groups, we recognize, of course, that if we have a group of piles, there is interaction among the piles. And so there will tend to be, for a given load per pile, a greater settlement within a group than there is for a single pile. And the simple approach that we can take to estimate the pile group settlement is that the group settlement is a settlement ratio times the average single pile settlement under the average load. And that settlement ratio, which is equal to or greater than unity, can be obtained either by tabulated values or by using an approximation that Randolph developed, which suggests that that value is the number of piles to an exponent W, which we can get from theoretical analysis. But as a rule of thumb, and probably fairly conservatively, that W can be estimated as 0.5 for floating groups in clay and 1/3 for floating groups in sand. So putting this simply, let's say you have a group of 25 piles in clay, then the settlement ratio would be 25, the number of piles in the group, to the power 0.5. In other words, the square root of 25, which is 5. So your group settlement would be 5 times the settlement of a single pile under the average load in the group. If that the 25 pile group is in sands, then you would have the cube root of the number of piles. In other words, just less than 3 times the settlement of a single pile, because in sands, we tend to have somewhat less interaction than in clays. Now, there is also, I think, a good case for checking the results of whatever calculation we do with an alternate method. And one of the simpler methods is to look at the pile group as an equivalent peer. And so you idealize the pile group as a peer that contains the piles within the group and the soil between the piles. And so you finish up then with what is a stubbier peer. And by using a chart of this nature, which shows a settlement influence factor and a length to equivalent diameter ratio here, we can estimate the group settlement very simply with this equation that's shown in red. And so again, these are simple methods that I think are very useful for both preliminary design and in particular for checking the results of more complex analyses, because I think it is critical that we don't blindly accept the results of computer analyses, which may be fairly complex and may be quite subjective for the person that's doing the analysis. They need to be checked to make sure that they are sensible. Now, of course, we interact in the design process very closely with our structural colleagues. And in general, what they ask of us is, let us know what the stiffness of your pile group is. And there are at least 3 ways that we can provide that information for them. We can model the entire pile group as a single spring with a number of degrees of freedom. So we give them a vertical spring, we give them a horizontal spring, and we give them a rotational spring. And all of these we can calculate from a pile group analysis, a simplified one, or something like Piglet or Repute. The second way is that we can do a more detailed analysis and provide them with a set of spring stiffnesses for each pile within that group. Again, vertical, lateral, and rotational springs. And again, these would come from our pile group analysis. And if they want something even more detailed, then we can provide for them values of vertical spring and horizontal spring stiffnesses along each of the piles within the group, which they may then put into their detailed structural analysis. I must confess that the way that I prefer to do it, certainly with buildings, is this second one, where we model the top of the pile, if you like, the spring stiffness at the top of the pile. And I think that gives the structural designer an adequate basis for proceeding with the design. Now, let me just say something briefly about some other issues that we need to consider in our design. Obviously, the key issue in terms of design are the structural loads and the traffic loads that are provided to us by our structural colleagues. But we must also consider other factors, one of which is scour, that very often, of course, our bridges cross rivers. And so if the bridge piers are within the riverbed, then there will be a significant potential for scour to occur over the life of the bridge. And so we need to be able to assess the depth of scour and then to allow for the absence of resistance in that scour zone. And so that will, of course, reduce the lateral and axial resistances and reduce the stiffness values as compared with the case where there is no scour. The second issue that we need to bear in mind is that there may be sources of ground movements which will affect our bridge foundations. There may be ongoing consolidation. There may be expansive soil, for example, in some cases, certainly in parts of Australia, and I believe in India as well. You may have bridges in areas where there is environmental moisture changes, and so you'll get swelling and shrinking. So that's important. In some of our bridges, particularly in urban areas, there may be tunnels that are being constructed or will be constructed near our bridge foundations. And I was certainly involved with some of these, both in Australia and in Singapore. And in that case, what happens is that as the excavation for the tunnel occurs, there will be ground movements, both vertical and horizontal, that will impact on the existing pile foundations of our bridge. And we need to make sure that the bridge foundations will be able to withstand the forces and moments that are generated because of those construction activities. And similar things will happen where we have excavations and also where we have piles near an embankment, or if we have a bridge near an unstable slope. So all of these situations are ones where you will get additional loads that are imposed not by the structure itself, but by the soil that the piles are situated within. Now, I've mentioned piles within embankments, and here this is a very common and important issue, particularly in cases where you've got soft ground and you've got embankments that have been constructed for the roadway. Here you have to allow for the effects of negative skin friction due to the settlements caused by the embankment. And the embankment, again, will also cause lateral movements, which will generate bending moments and shears in the piles. Now, there are some design charts that have been developed, and I produced some of these for a road authority in the state of New South Wales some years ago. And here's a typical set of design charts. There were various sizes of piles. These, I think, are for piles 400 millimeters in diameter. And here is the problem on the top left. We have an embankment that's being constructed on compressible clay. We have a firm bearing stratum here, and we would have piles that would go through the embankment at various locations. And this diagram on the right of that shows the pile top deflection against undrained shear strength of the clay for typical embankment depths of soil and embankment heights. This is, I think, for a 4-meter height of embankment. And then we have bending moment versus undrained shear strength, positive and negative bending moments. So these sorts of calculations we can actually do if we need to, but there are simple design charts that one can refer to see whether there is potentially a problem with those sorts of embankment-induced movements. What happens again is that we often have transitions between the bridge that is on piles and the embankment which is supporting the roadway that's coming up to the bridge. And what we want to try and do, of course, is to avoid bumps that inevitably occur when we go from the compressible unsupported embankment to the pile-supported bridge. And we can engineer a transition zone to avoid those bridge bumps. And we need to firstly estimate the length over which we need to have a transition between the soft behavior of the unsupported embankment and the stiffer behavior of the supported bridge. And so I've suggested here some very preliminary estimate of the minimum length being the allowable differential settlement divided by the differential settlement you expect divided by the allowable angular distortion. And what you can do here, you've got various strategies that you can examine. You can decrease the length of the pile away from the bridge. So the bridge, of course, is supported, but you can continue having support of the embankment as you go away from the bridge, but with piles of decreasing length. Or you can decrease the diameter of the piles away from the bridge over that transition length, or you can increase the spacing. The further away you go from the bridge, the more widely spaced that is. I've looked at this for one or two cases, and in those cases, this is a diagram showing the settlement and the distance from the bridge itself. And in this particular case, you get a much better performance if you actually, surprisingly, decrease the pile diameter away from the bridge rather than decreasing the length of the piles. You just get a smoother transition. We need to be aware, of course, of risk factors in any form of foundation system. So there are risks in relation to inadequate investigation because we can get inappropriate ground models. We can have geological imperfections, as I call them. For example, soft layers below the piles, sloping bedrock or boulders in a glacial environment. And of course, we can have construction deficiencies and imperfections. And of course, our previous lecture dealt quite significantly and in depth with identifying those sorts of construction deficiencies. Measures that we can take to reduce risks. I think it's important that we have peer review of ground investigation reports and of the foundation design, that we have independent supervision of foundation construction, that ideally we have testing of the foundation elements, whether they're piles or barrettes, and that we monitor if we are in a really a difficult situation, particularly with bridges, where we monitor settlements during construction to see and hopefully verify that the performance that we predicted is being met or being, in fact, okay. And so we treat these measures really as not as costs, but as insurance investments. And pile load testing, I believe, is very important. We now have lots of methods of testing, and top loading, of course, static testing is a preferable method and an old method, but increasingly for high capacity piles, the Osterberg cell method of testing is being used and is a very effective method of testing. What is very appealing from the point of view of bridge designers and contractors is dynamic testing, because quite often we use driven piles, and so you can, of course, use PDA testing, pile dynamic testing to examine the performance of piles, and that's fine. Bearing in mind, of course, that with any type of pile testing, the interpretation of the test results is important. So let me finish off then with a brief description of an interesting project that we undertook in Coffee, as it was then, now Tetra Tech Coffee, some years ago. This is a stretch of highway between the city of Sydney, where I live, and the city of Wollongong, about 60 or 70 kilometres south. And this particular road goes along the shores of the Pacific Ocean. And what happened with this road was that it was cut into a very steep hillside, which was relatively unstable. And this sort of problem occurred fairly frequently. There were unstable rock slides, and on occasion cars were actually damaged and in some cases destroyed by falling rocks. So clearly there was a need to improve on the alignment of the road. And here is a sort of geological section. You can see the road just down here towards the bottom. There were 300 meters of cliff and steep slopes with relatively unstable conditions here. And there were also coal measures down below here. How did we solve the problem? Rather than trying to get an improvement on land in the unstable areas, what they decided to do was to actually realign the bridge so that part of it then went over the ocean and over the water. So just in plan, I don't know whether you can see my cursor here, but this was the original alignment on land, and the new alignment has sections which actually go over the ocean itself. So we had some of the piers that were in the water. And so this is a balanced cantilever bridge that was constructed. Here you just see a couple of pictures of the bridge itself during construction. This is a geological cross-section, essentially various strata here with coal seams down here at the lower levels. And so what we did in the process of design was that there was an assessment of the design geotechnical profiles at each of the pier locations. We assigned design parameters based on unconfined compressive strength and experience of similar ground types. We evaluated various alternatives for the pier foundations in terms of the configuration and the number of piles. We looked at axial capacity of piles and pier groups, and also the lateral response, the deflections, shear forces, and bending moments. And in this job, which we did some years ago, we used the programs DefPig and Piglet. And here, again, in a similar way to before, here is one of the profiles that we examined, the material type and the depths, the depth range of each of those layers, ultimate skin friction end bearing, vertical, horizontal modulus, and ultimate lateral pressures. And these were then used in our design calculations. And in fact, interestingly, what we found was that in this particular case, because the piles were relatively long and the rock through which they went was in reasonable shape and quite strong, that in fact the design of the piles was governed by the structural strength of the piles once the piles were founded below the coal seam, rather than by the geotechnical capacity. And these dashed lines that you see here are estimated capacities. These are design capacities, so they're factored down capacities for different sizes of piles, and these are the structural capacities. So you see, once we get down below a reduced level of about -20, there's a clay seam here, then the structural strength, which are these full lines, governs the design of the piles. And here is then for the serviceability assessment, here's a typical pile group that we analysed. The bridge goes in this direction. 6-pile group, we looked at pile lengths of 15 metres in this particular case, lower one, and a 1.5 metre diameter. And those groups typically were assessed to settle less than about 10 millimetres with a similar sort of lateral movement. And here are pictures then of the pile construction. These are the board piles, generally 1.5 metres in diameter. Some of the reinforcement, the bridge pier on land here. And here is the final bridge, a very handsome looking bridge, and really one of the nice achievements of our engineering fraternity. So in conclusion then, I think we can look at 3 stages in our design: a preliminary stage to get the concept right, a detail stage, and a final stage where we put our best parts together, the best data we have, the best analysis we have, the pile load test data to get the best model we can. We have ultimate limit state and serviceability cases to look at. And as I mentioned before, parameter selection is critical. We have a lot of correlations now available for the geotechnical parameters, but I believe that there is a potential for more use of the small strain modulus values we get from shear wave velocity to get better values of stiffness of the soil or rock. And we do have lots of now software programs available, but in using those programs, we must always use and check with simpler methods to make sure that they give us sensible answers. We must cooperate with structural designers, and we need to present our geotechnical analyses to them in a form that is convenient for them. Construction supervision, of course, is very important. And of course, it's also critical that we take the sort of risk aversion measures that I mentioned before so that we try and avoid any negative consequences. So that's the end of my presentation. Thank you very much.
Thank you, Professor Poulos, for your very informative presentation. We can have we have a little bit of time till I think 12:15 in local time. We can have some questions. If the audience has questions, you can drop it to the chat box, or even you can directly ask from Professor Poulos. Just to start the discussion, may I ask a question? It is not very, very relevant to your presentation, but I would like to ask that question because it is very relevant in Sri Lankan context. We do inclined piles, rake piles in bridge foundation, especially abutments. And also we get a lot of peat soil, organic soil in these locations. What are the special things you have to consider if you go with rake piles? Of course, it will be a driven piles. What are the special things to be considered? And also there are different school of thoughts when considering rake piles, especially some people, especially in earthquake zones, they don't like rake piles. What is your opinion on those?
Well, thank you for that question. I think rake piles certainly have an advantage in terms of increasing the lateral stiffness of the foundation system. There's no doubt about that. I think if one is to use rake piles, you need to be very careful of the consequences of that if you have the tendency for the ground to settle. Because what happens then is not only do you get negative friction, but you also get a little bit of normal loading onto the piles. And that can actually put quite large pressures on the piles themselves and give you bending moments that may be a problem. So if you're using rake piles, you need to be aware of the potential problems that any ground movements, particularly vertical ground movements, may induce. I have actually seen in the United States a bridge pier foundation where the rake piles have actually been pulled out of the pile cap because of the pressures that were induced by the settling soil. So as long as you recognize these risks and design against them and check whether they are critical, I think that's fine because you know, they may work, but what they may require you to do if you have potentially settling conditions is that you may have to make the reinforcement in your piles more robust than you would otherwise to give you greater shear and moment resistance.
Thank you, Professor Poulos. Apart from the settlement, vertical settlement, that of course sometimes can happen because of the subsequent filling of that area.
Indeed.
Apart from that, Is there any other disadvantage of rake piles?
Well, yeah, look, other than potential problems in installation and alignment, again, no, I think my main concern would be, with the vertical ground movement effects. And the problem there is that where problems have occurred, I don't think that they have been recognized in design. If you recognize the problems in design, then you can take measures to address those problems. But if you don't recognize the problems, then of course they may come back to hurt you.
Thank you. Do we have any question from the audience? I'm sure you will have few questions to raise to Professor Poulos.
I see one here. Do you recommend using single tall columns on top of a pile group? Is that correct? There was one that came up.
Yeah, I can't see that in the chat box. Maybe.
Oh, I'm sorry, I've got it here, I think. Yes. There's a question. Thank you very much for your kind comments here. Are there any considerations of vertical and horizontal ground accelerations in these kind of designs? That's the first question from Jagath. And obviously, horizontal and vertical ground accelerations relate to earthquakes. And yes, we do take account of those. How we do it, I mean, ideally, our structural designers will be able to give us earthquake loadings, vertical and horizontal ones, which would be incorporated into our design. There are also potentially kinematic effects where the ground moving backwards and forwards, again, may impact on our pile foundation. So they need to be taken into account in the design. So these are all part of the design against earthquakes, which unfortunately these days no place on the planet is not potentially subject to earthquakes. And then there was another question, I think, from Jagath. Do you recommend using single tall columns on top of a group of piles in an earthquake prone zones? Are there any other alternatives? Look, I'm not sure that I'm the best person to answer that question. I do worry, I must confess, about single tall columns on top of groups of piles. I've seen these collapse, not personally, but I've seen the results of collapse of those both in San Francisco in the 1989 earthquakes, in the Kobe earthquakes, where the whole a single column supported by the piles actually collapses sideways or front and back. I don't know what alternatives you have for there other than perhaps having more of a structural frame rather than a single tall column. The problem there, of course, is that then if you try and extend the footprint of that column, then you extend the size of your pile foundation, and that may be uneconomical. So I'm not sure that I think that's probably a question that is better addressed by a structural designer rather than a geotechnical designer.
Thank you, Professor Poulos. I also want to ask a question, maybe not again directly connected with your presentation. Yes. You are very, very knowledgeable on pile raft foundations. Yes. And my question is in Sri Lankan context, we have the bedrock at very shallow depth. When I say shallow, maybe something like 20 meters in average.
Yes.
According to my opinion, doing raft pile raft foundation when the bedrock is in that depth, shallow depths, may not be very practical because of the very high stiffness provided by the piles, because it is supported on the rocks. What is your opinion on that?
I completely agree with you. I think we have to be careful piled rafts are very, very useful in certain circumstances. And in the Middle East, for example, where we have to get to real bedrock, we've got to go 200 or 300 meters there, and the ground near the surface is not that bad. I mean, it's sort of soft rock. There, a piled raft is excellent. But if you've got a situation, as you say, where you're going to put the piles inevitably on rock, the stiffness of the raft is going to do very little in terms of its effect on the settlement. The piles will take virtually 95 to 100% of the load. What the piles, of course, will still do is that they will, of course, the raft will form the basement slab, and it will connect the piles together, and that's fine. But of itself, it will really not do very much for you in terms of improving the performance. So I totally agree with you that what it may do, maybe you can save 5 or 6% of the piles there because the raft will provide you with some capacity, but that really depends very much on the configuration of the loads that you're designing for.
Thank you, Professor Poulos.
Let me ask one more question.
Okay.
Yes.
Saman.
Yeah. Thank you, Professor Poulos, for the very nice presentation. So you mentioned during your presentation a few times regarding obtaining of a reliable soil parameters.
Yes.
Now, when it comes to the parameters, the E value, that is the elastic modulus value, is very, very important. So in Sri Lanka, we carry out mostly the SPD testing,
Yes.
1 meter level, 1 meter intervals. So what is in your opinion? So you mentioned that the shear wave velocity method is will give a very good estimation about the E value. So what is your view on the use of the SPD N values for the estimation of the elastic modulus?
Well, again, thank you for the question. Look, I don't use just one method. If I have SPT and CPT and shear wave velocity, I'll use whatever correlations I can, because I think it's always wise to get more than one value. And again, this is why I'm so keen on peer review, is that, again, you have a check on what you're designing and what you're assuming. And I think that's important to try and avoid problems. Look, I use SPTs a lot, to be honest with you, because sometimes, particularly when you're working with a relatively small scale project, that may be the only data you have, or you may have cone values as well. But SPT, we've got a lot of experience with SPTs in a fairly wide range of soils, particularly, I think, in sandy soils. And so, I'm fairly confident that if we have driven piles in sand, then a modulus value is probably somewhere between 3 or 4 times SPT megapascals. Okay, so if we've got SPT 20, we've probably got 60, give or take a few megapascals in modulus. And I've generally found that gives us a reasonable ballpark figure. And what we can do after that, again, we can check if we have shear wave velocities to see what that gives us. But more importantly, if we have pile load test data, again, we see what our settlement is at our sort of design load, and we see how that relates with our calculated settlements. And that's really the major value of pile load testing, is to hopefully verify our design assumptions, which very often are based on these sorts of correlations that we inevitably have to use.
Thank you.
Welcome.
Okay. Thank you, Professor Poulos. I think the time is running.
Yeah.
I am very grateful to Professor Harry Poulos. He's very well-known geotechnical person internationally as well as in Sri Lanka. Again, thank you very much on behalf of the Sri Lankan Geotechnical Society for your presentation in our annual conference. Thank you.
Thank you. It's been a pleasure to be part of it. Thank you very much.
Thank you. Yeah, our next presentation will be on identification and rectification of defective board pile foundation by Professor Samanth Tilakasiri, Senior Professor, Faculty of Engineering, Sri Lanka Institute of Information Technology. And I don't think he needs special introduction, but it is my formal duty to introduce Professor Tilakasiri to today's audience. Professor Samanth Tilakasiri obtained his first degree from University of Moratuwa with first class honors, and later he completed a master degree from Imperial College, London, UK, with distinction and PhD from the University of South Florida, USA. After that, he has served as an academic at various capacities from 1990 at the University of Moratuwa and Sri Lanka Institute of Information Technology at Malabar. Further, he has obtained valuable experience from major educational institutes in USA, UK, and Australia as a research student, a general faculty fellow, as well as a research fellow. In parallel with his academic career, he practiced as a senior engineer and consultant in many nationally important local and foreign funded projects. He obtained the corporate membership from the Institute of Engineers Sri Lanka and became a fellow of the same institution in 2009. Presently, he is the Dean of the Faculty of Engineering Sri Lanka of the Institute of Information Technology. He is also engaged in developing collaborations with major local and international academic and professional institutes. With that brief introduction, I kindly invite Professor Samanth Tilakasiri to deliver his presentation on identification and rectification of defective board pile foundations.
Thank you very much, Mrs. Habandu, for your kind introduction. So let me share the presentation. I hope you can see the screen, right?
Yes, it is possible.
Can you see?
Yeah.
Okay. So the my topic is actually identification and rectification of board pile foundation. The presentation is kind of introduction, reasons for the defects in board piles, and detection of the defects, coring. You can use coring, PIT, that is a pile integrated testing, and CSL, then the rectification methods. So once you do, basically now in this case, I omitted the PIT because that is TIP, that is thermal integrated profiling method, because that was discussed in the morning session. So the defects in piles should be detected by carrying out necessary tests during and after installation of the piles. So that is the recipe of the installation agency. Defects that may hamper the structural integrity of the pile foundation. So that is the problem is in the load carrying capacity of the pile foundation. So that is the problem is in the geotechnical nature, that is the load carrying capacity of the piles are in jeopardy. So basically, before you carry out any of the rectification method, necessary tests should be carried out on a pile when deciding whether the pile is a defective one. So it is a best idea that you identify the defects in the piles using more than one single method. So So once you rectify the problems in the pile, basically the confirmation of that you have basically rectified the the defects should be carried out. So the confirmation testing is very much needed. So now, so that is the introduction part. And so what are the reasons for the defects in boat piles construction mainly in Sri Lanka? So in the morning session, you may have seen some of the defects that are encountered in the piles when you take out the pile, boat piles especially. So there are some reasons that the defects can happen in boat piles. So many years ago, we carried out, kind of a survey and found that about 4% of the piles are defective. So this is many years ago, and most of the defects have taken place because not proper quality controlling had been in use. Basically, now when you look at the construction of the boat piles, so the construction method is that you dig a hole and you concrete that. So in simple terms, but when you dig a hole, right? So this is what is basically on the right hand side. You can see that a lot of debris right around the piles, right around that pile location. So some of these debris can collapse into the hole and mix with the basically the concrete, rising concrete surface. So that is because of that, we provide kind of a temporary casing at the ground surface level just to prevent collapsing of the material and mixing it with rising concrete surface. So that is one reason. And so if you look at, for example, why these defects happen, right? So the not proper quality controlling test has been done, right? So the flowing of the subsoils to the pile bow, creating necking. So that is another reason. That is, this the length of this temporary casing is generally at about 6 meters maximum, right? So below that, basically it is the concrete, the side of the wall is retained using the bentonite slurry in Sri Lanka. In Sri Lankan context, like if you look at the groundwater table is fairly at a high level. So we have about 2 meter level. So we have the groundwater table in most of the situations, but of course, it can vary. So below that, basically that level, you have the sides are supported by the bentonite slurry. So if you have not investigated the ground properly and suspect that these soft clay layers are there, and then sometimes these soft clay layers can flow into the excavation and create necking. And concreting in is mostly done underwater, making it impossible to compact fresh concrete. So that is obviously that when you are compact, when you are constructing the pile foundation, you cannot compact, right? So the because if you have not designed the properly the mixed design, and it is not subjected to self compacting, so then the defects can happen. And so in most cases, the defects can happen due to improper cleaning after the pile is digged, or basically pile is drilled, right? So in that case, basically, so what happens is, at the end of the drilling, so you will have a lot of debris at the bottom of the borehole. So the pile bore will consist of a lot of debris. So you have to properly clean the piles, right? Clean the pile before concreting. So if you look at the concreting of the piles, basically, you have to, if you look at the concreting, then you need to have the hopper at the top, and then you use a trimmy pipe to reach the bottom. And then, so you have to charge this so that this trimmy pipe is fully sealed from the outside, and then it consists of only the fresh concrete. And so when you during the construction, so you make sure that you pour the fresh concrete into concrete. So therefore, that the bottom of the trimmy pipe should be immersed in the fresh concrete. So that is a must, because if you look at the top portion, so that is top portion of the fresh concrete rising concrete surface. So it is in contact with the bentonite slurry and will be subjected to some contamination. So if you, by chance, if you have not properly planned the arrival of the fresh concrete to the site, then you may have to maybe withdraw the trimmy pipe. So again, lowering that is very, very difficult, because you may have passed the initial setting time, so there may be some contamination of the concrete with the bentonite slurry surrounding that. So therefore, it is very important that you will not actually withdraw the trimmy pipe in the process of construction the piles. So the most of the defects happen because you prematurely withdraw the trimmy pipe as well. So, and also I mentioned that at the beginning, so you will have a temporary casing at the top of the pile. So if you withdraw the temporary casing quite late, after the initial setting time of concrete, then the defects can occur also. So these are some of the reasons, but other reasons can also contribute to some of the defects in the board piles. So you have to, first thing is that you have to detect the defects in board piles and then correct them, and then use that for the construction of the superstructure as well. So if you look at the detection methods, so it used to be like, you drill a hole through the pile, you core a hole through the pile and look at the core that you recover. So that is the most common type, because now there are also you have a cored hole at the end of the coring process, so that can be used as a rectification access to the defect as well. So that is the most common type, but you have to be very careful that when you do that, you have to consider the verticality of the core hole. Sometimes it can go off the pile and detect some defects which are not there. So and also, if you drill, your defect is on this side of the pile and you are drilling to the other side, and you can miss the defect as well. So these are some of the difficulties associated with the drilling of the or coring of the pile. And so if the defect is at the top level of the pile, so you may be excavating the surrounding soil. If the water table is rather below, then you may be excavating the surrounding soil and removing that, and then you can access the defect and manually you can rectify that as well. So that is another method that you can detect. So in addition to these traditional methods, what we have is basically we have the surface reflection method. That is, you can make the stress wave travel through the pile and detect any defects that are possible, right? So that is basically, so these are the direct methods, and these are the indirect methods that I talked about, right? So indirect methods are basically non-destructive testing, so NDT testing. So the one method is the surface reflection, that is, you send a stress wave. The other one is the direct transmission method, that is, you can actually transmit the wave through the tubes that you predeterminedly install in the pipe, and then see how you can lower the transmitter and the receiver in those tubes, and then you can see what is the wave velocity. So that is the direct transmission method. And of course, in the morning session, you have the thermal integrity method. So in addition to that, you have the gamma ray, detection and so on. Out of these methods, so you have to detect the pipe, detect the defects in the pipes. And in addition to that, you can use some of the data that you obtain during the installation of the process. For example, the theoretical volume versus the actual volume consumed of the of the volume of concrete consumed by these board piles construction. So, and also the strength parameters that you obtain from the basically the concrete trucks that are available that will arrive in the site. And so these are so in combination, so it is always better to use more than one method to detect the defective piles in most cases. So I will actually first touch on these surface reflection methods, right? So in this particular method, basically the surface, the monitoring is done at the surface level. So there are two types of methods, what are called small strain integrated testing method, like PIT, that is basically pile integrated testing method, right? So, and also you can have the high strain method, high strain high dynamic testing method. So there you dropped a very large hammer onto the pile. So from that you can measure the integrity of the pile. So in addition to that, you can get the capacity of the pile as well using the high strain testing. So if you look at the small strain testing, then that can be again divided into two methods, that is pulse echo method, right, and the transient dynamic response method. So that I will explain a little later. And also you can use the high strain method like PDA. So where you can use, actually you can get the integrity information about the piles as well. So I will not cover it in this particular lecture. So if you look at the pulse echo method, so there you look at actually the reflection of the wave, right? So if you look at if you consider this as the wave that is being propagated in the pile. So basically, you will send a wave through the pile to the bottom, and then observe the reflection. So until reflection, you will not see anything if it is a good pile, right? So this is the initial the stress pulse, and then so this is the one received from the toe. So this is a perfect pile. So in this case, there are no defects here, right? So what you do is basically you send a small strain wave through the pile. And so if you look at a pile with a defect, so in that case, so there's a defect here, right? So the pile will go and there will be a reflection from the defect. So this reflection will come up and will be detected at the top of the pile. So in addition to that, so you will go, the stress wave you apply will go to the bottom of the pile and will come up, right? So this is actually the detection of the stress wave. So I'm not going to go into a theory part of this, right? But generally, if you get a positive reflection, that will indicate kind of a defect. And if you get a kind of a negative reflection, that is actually bulging, right? Increase impedance. I would say that increase sectional properties, enhance sectional properties. So this kind of surface reflection method. So everything you can actually monitor from the surface. So these are, this can be, very good method of getting the initial screening of the piles, right? So in Sri Lanka, you use actually, we use 100% of the PIT testing, right? So but the PIT testing is not very conclusive sometimes, right? So for example, in this case, you can definitely say that there are no defects. But here, you will go the stress wave will go to a certain extent, certain distance in the pile, and thereafter it will die down, right? Because of the high soil resistance. So you cannot say anything about basically this portion of the pile. And so in here, basically, you have the toe reflection coming, and before the toe there's a problem in the pile. This will indicate. And also here, for example, at the toe itself, the toe reflection is coming as a positive reflection, indicating that there's a problem at the toe of the pile, right? But sometimes, you can detect this is, for example, now this is a pile where you have the bulging at the, somewhere around 9 to 10 meters, right? You have the bulging and you get actually the reflection of that, right? So the bulging is not a defect because it enhances the properties of the pile, right? But here, if you consider this one, there are actually, you get kind of a necking or reduction in the impedance. Impedance means basically, if you say that the pile section, but it is not only the pile section of the section of the pile, but the density and the elastic modulus as well. So it is a parameter that we determine from the pile integrity testing. So here actually, so the pile, there's a defect here, kind of, right? So then you might have to do something like, so you have to dig into the pile installation records, and maybe you can do additional coring, right? And see whether actually a defect is there, right? So, but it is not very simple. For example, if you have multiple defects in the pile section like this, right? So basically it will not be possible to see, right? Because it especially, so one will mask the other one, right? So if the defects are very close, then you will not be able to use that using the small strain method. And sometimes it can yield you basically inconclusive results. For example, now here in this case, you get a sinusoidal kind of a wave formation. So you cannot say anything about the integrity, because now if you look at here, basically probably you can guess that there are some kind of bulging here, that has created this kind of sinusoidal waves. But you are not certain by just one method, so you may have to investigate these piles, right? So there are some and also if there are defects here, it is very difficult to detect that, because the impact, the stress pulse will actually cover that. So there are some problems with this surface reflection method. So it is not conclusive, but you can use those piles for further testing, further investigation. So what I mentioned here is basically you look at the stress wave, the time of the reflection. Basically, you look at this axis is actually the time or the length of the pile, and this axis is the wave velocity. So not the wave velocity, but the velocity of the section, right, that you measure. So basically that is called the pulse echo method, right? So there you don't need any kind of an instrumentation of the hammer itself. But if you look at the transient dynamic response method, right? So you need actually this picture of that. You have the hammer, and this hammer is actually instrumented, right? So instrumented, and it is connected to the readout unit, right? So here you measure the pulse you apply onto the top of the pile, right? So this is the receiver that you install, and so you convert this into a frequency domain using the there are softwares where you can actually the input force can be converted into in the frequency domain, and also you can actually get the velocity also that you measure from that the surface, the accelerometer or the geophone. So velocity also you can convert into the frequency domain. So you get what is called the mobility spectrum. That is, you obtain B over F value, right? And see, they are actually, you can see any kind of a defect. So if the defects are denoted by kind of a this kind of the pulse increase, right? So here kind of a, so this can be the toe reflection or any defect, right? So if you look at here, right? So basically you get the frequency here, that is frequency difference between these two peaks, right? So and estimate the time. So and also when you estimate the time, you can estimate the length also if you know the wave velocity. So there are actually, you see whether there is any kind of a peak before you get the toe reflection. And also the first part of this curve is what is called the slope of the curve, and that can actually, that is related to the initial tangent modulus of the load displacement graph. So that was shown by Davis and done in 1974. So we also have seen that, and also here what you see are basically whether you get this kind of a peaks in the frequency mobility spectrum, right? And see whether there are any kind of a defect, right? So this one is actually the time taken, and this is the time taken to get the toe reflection as well. So if you look at the small strain integrity testing, so the advantages are no need to select piles for testing before installation like CSM, so which I am going to explain next time, next. And comparatively very low cost, because you don't have to instrument the pile, and so you can do many tests, right? Very quick, because you can do many tests per day. Within the limitations mentioned previously, this method can be used to get a very good idea about the quality of the piles at a site. So this is not conclusive sometimes, but in most cases you can get a good idea about whether it is a good site, or whether you have defective piles or not, right? PIT methods. So on addition, in compare to that, so we have some shortcomings as well. Pile that can be investigated, especially in high resistance soils, right? So I mentioned that, I showed you that, there are no reflections coming up from the, toe region of the pile. So in that case, it is restrictive to use this method for a long pile shaft. Difficulty in identifying defects near pile top or pile toe, very difficult to identify, right? So as I mentioned earlier, at the top of the pile, you will get the input pulse. So that can actually mask the defects near the top. Difficulty in identifying minor defects in the pile shaft. It is very difficult to identify the minor defects. So there can be minor defects, but those are not very major, but can have certain effect on the pile capacity. Difficulty in identifying gradual variation in the pile cross section. So if the pile cross section varies gradually, then very difficult to detect that as well. No indication of the location of the defect in the pile cross section, because if you look at the CSL, that is cross-hole logging test later, you will see that. So if you do a tomography analysis, you can actually determine the location of the defect as well. But in this method, you can get the location of the defect. So these are some of the advantages and shortcomings, but definitely it is a good way to select piles for further testing. So the next method that I'm going to explain are basically cross-hole sonic logging method, the OCSL method, right? So in this case, if you consider two tubes, so you have to, you have to install these tubes beforehand, right? So that is the costing part of this particular exercise. Through one of these tubes, you lower the transmitter, and through the other one, you lower the receiver, right? So transmitter and the receiver at the same level, right? So if there's a wave, right, ultrasonic wave that is generated from the transmitter, so it will take some time to get it to the receiver, right? So this is the time that is taken, right? So after that, you will see a continuous wave, because it is received by the receiver after that, right? So this is basically what is called the first arrival time, or the FAT time, right? So the first arrival time. So if you say the wave velocity is capital C and the distance is d, so it is d over c. But getting the wave velocity from the cross-hole sonic method is fairly sometimes very approximate. But this, if you continuous FAT diagrams like this, and you can actually combine those and obtain what is called the waterfall diagrams of the pile section, right? So the in addition to that, if there's a defect here in between the transmitter and the receiver, so if there's a defect, basically that will reduce the wave speed, right? So that can actually affect the FAT diagram as well, right? So, and also it can affect the energy of the received wave, right? So the amplitude of the received wave is actually reduced there. So that is a indication of the defect. So these are the tubes actually you install that, for example, in this case, there are 4 tubes, right? So you install actually 4 tubes in this, and you can see that, so there should not be any obstruction between these tubes, right? So if there are obstructions that between the tubes, that can affect the wave transmission, right? So because of that reason, you will tie this particular the tubes to the reinforcement cage inside that, right? So between, if there's any defect between the reinforcement cage between these the tubes, then you can use this method to detect that, right? So the other problem is sometimes you can have something like it can actually there can be a gap between the top of the concrete and the installation tube as well. So that can affect actually what we call the debonding, right? Debonding on the top of the tubes can actually affect the wave transmission between the tubes, right? So that can, to avoid that, if people say that these you can have generally you have actually, you can start with 3 access tubes, but you can have 4 access tubes, and in some cases you can have 6 access tubes depending on the diameter of the pile. Rule of the thumb is that for each normal rule of the thumb is to install 1 tube per each 300 millimeter of the pile diameter with the minimum of 4 tubes. But I have seen that we install actually 3 tubes as well, right? So the waterfall diagram. So this is the first arrival time. So this will consisting of the receive signals, large number of receive signals. So that is these are what is called the waterfall diagram, right? So this is between tube 1 and basically between tubes 1 and 2, right? Tubes 1 and 2. So in this particular pile, so tubes 1 and 2, the waterfall diagram will indicate this kind of there's no sudden change in the slope. There's no sudden change in the first arrival time. So that indicates that this is a good pile, right? So this between tubes 1 and 3, 1 and 4, right? So 1 and 2 and 3, 2 and 4, right? And 4 and 3. So there are 6 profiles. If you install actually 4 tubes, four access tubes, if you install, then you have the 6 profiles. But if you install 6 access tubes, you will have 15 profiles and so on, right? So this profile will not indicate any kind of a defect, right, of the pile, because there's no change in the first arrival time. There's no change in the first arrival time. So the first arrival time, of course, there can be some changes, but those are very gradual. There are no sudden changes, right? So the software will detect the sudden changes and will give you the delay time, right? So, and also the bottom of the piles, if you look at basically these the probes are about 6 inches in length approximately, right? So basically if you consider the middle from the transmitter and middle from the receiver, so the 3 inches diameter, 3 inches the length are not actually used for the waterfall diagram. But this kind of before that, if there's a defect, right? So this will indicate that. This will indicate any kind of a delay in the first arrival time, right? So that will indicate kind of a defect at the pile 2. So this is a perfect pile, right? So there are no first arrival time change, right? So this is consisting of 4 tubes, right? So but if you look at the next one, you can see that so this actually there are 6 profiles here, right? So that means you have installed 4 access tubes, right? In all 4, there's no wave received by the at this particular depth. There are no waves received. That means so there's a complete defect between transmitter and the receiver, right? So it is very evident from all these 6 profiles, right? So in that case, there are no problems, because you can say that there will be a defect. It is happening at the same level as well. Of course, there are ups and downs, but you can say that it is happening at the same level. So there can be a defect at that particular level. So it is conclusive in that case. But if you look at this one, for example, if your defect is between tube 1 and tube 2, so this is a pile cross section, and these are the tubes, right? So there are 4 tubes used in this case. But between if you look at tubes between tubes 4 and 5, 4 and 2, right? So between 4 and 2, it is perfect. There are no delays. But if you look at 1 and 3, right? So if you look at 1 and 3, there's a full defect in that section, right? And 1 and 4, between this, maybe there's a certain amount of 1 and 4 is this profile, right? At this level, you will see kind of an, some kind of a defect, but not fully covering the entire the path of the wave. And so 4 and 3 there are no defects, and 2 and 3 there are no defects, but the defect is in this region, right? So that is the importance of this, because if you look at the PIT will tell, okay, at this level you have a defect, but it's very difficult to determine the exact location of the defect in the pile cross section, right? So that is required to rectify the pile, right? But here you can get the exact location of the pile cross section, right? So the advantages of the CSL method are basically the location and the extent of any anomaly in the pile shaft can be determined fairly accurately using this method, right? The other main advantages of this method compared to the surface reflection methods are its ability to test the pile irrespective of the depth, because always the wave will be between the transmitter and the receiver, so it will not affect the depth, right? The independency of the test result from the soil type present along the pile shaft. Of course, there's no effect of the soil type present. Ability to identify the multiple defects along the pile shaft, so that is possible. Test can be performed even when the pile head is not accessible. For example, now if you want to do a PIT test, then you have to clean the pile top and then use that. Otherwise, there can be reflections from the clean portion and the unclean portion, right? So the visual identification of the defects, if any, right? Ability to use the access tube to grout the defects at the pile toe. So that is, it is possible to access the tube using the access tube. You can access the defect as well, right? So the main disadvantages are debonding of the access tubes may identify as a defect, because there's no bonding between the outside concrete and the access tube. Defects outside the reinforcement cages are not detected. So this was very well explained in the first part, because now you install all the access tubes inside the reinforcement cage, and that was not detected what is happening outside. So there were some examples where the CSL passed the test, but actually when you expose the pile, you find some kind of a defect at the top of the pile. If the soft toe condition is present below the reach of the transmitter or the receiver, it may not be detected, right? If not, if not properly quality control measures are adopted, access tubes may be blocked. So if your one access tube is blocked, it can affect the gathering of the information from the other access tubes as well, right? Piles should be identified before installation, and access tube should be installed. So this is the main advantage of the PIT surface reflection method. So, but this method is very popular among the local engineers, because if there are no redundant piles like bridge piers, so in that case you can use this type of testing to make sure that the piles are installed, even though the cost can be higher. So in addition to that, CSL testing can be used to identify these kind of what is called tomographic images, right? So that is a three-dimensional image of the pile being tested using the CSL method. So actually, say if you require, you can take the cross sections of the piles at different levels, and so this is using this tomographic images, you can actually detect. So this red zone shows a defect, right? So the defect is limited to this tube number, in this case 4 and 3, right? So you can actually target this area, and then you can clean the pile. You clean the whatever that debris is there, right? So that is an advantage. So these are some of the rectification methods, right? So commonly adopted. So the basically rectification of the piles, it is a difficult process, right? So you have to see what is the time frame that is available, and what you have to see what is the cost associated with that, whether it is cheaper to install a new pile, and what is the installation time and so on, right? So before rectification you have to see like whether you have other option. So these are some of the rectification method that we are using. Defects detected in the shallow depths, right? Probably above the water table, right? Defects detected at relatively shallow depth in the soil layers, probably under the water table, right? Defects detected in low carrying capacity piles. And so defect detectors is the socketed portion of the pile. So basically, in Sri Lanka, we get about at 20 meters on average the bedrock. So you can actually socket the pile into the bedrock and see like if the piles are socketed, you can actually the method that you are using for the cleaning and the grouting is quite different, right? So these are some of the methods that are possible. So I will explain this. So before that, these are the factors that you have to look at: the relative cost comparison and importance of the pile, right? Nature of the defect, whether it is possible to rectify, or time consideration. So these are some of the factors that will determine whether the pile is you can rectify them or not. Defects detected in shallow depths, probably above the water table. That is number one. So in that case, you are sure that there will be a defect, but it is above the water table, actual water table, right? Support the wall of excavation, excavate the surrounding of the pile to expose the defect, and manually correct the defect. So above the water table excavation is not that difficult, right? So you can show the sites of the excavation and reach the defect, and then probably you can actually rectify the defect as well, right? So you can probably the manual rectification. The second one is depth in the soil layers, probably under water table. So if you look at, for example, cross-hole sonic logging testing, right? So you can see a defect here. Of course, in this particular pile, there's a defect at the bottom as well, but we will concentrate on the defect here, right? So you can see there are no wave transmission through that defect, right? So if you do actually the tomographic analysis, you can see the defect here, right? So there's a defect here, right? So in that case, how do you correct that? Because now you cannot use normal grouting. Grouting before that you have to clean the pile. So if you clean that, so you have to use high pressure water, right? So this is in the soil layers, right? So if the overburden pressure is very low, right? So something little about 50 kilopascal. So then they are actually you cannot use high pressure water, because the water will find its way through the surrounding soils. So it is the normally grouting will not work here, right? So the basically the steps involved in there. Step one: remove the region of the pile using a smaller diameter core bit, right? Beyond the detected defects, at least 1.55 times the new pile diameter. So you have to core the pile below this particular defect, right? So at least about 1.5 diameter, right? Step two: design the smaller diameter pile to take the force acting on the pile. Basically, there will be the lateral forces acting. So you may have to because you are using a smaller diameter pile, right? So you have to neglect the pile above the above this particular defect, the neglect the file install above the particular defect, right? And so you are above the particular defect. So what you have is the new file diameter. I will show you in the next slide. The step 3, concrete a new file above the depth of the new file. So bottom of the new file. So you concrete the file, and so then you have to test the test whether the capacity is there. Otherwise, what will happen is you cannot do generally the PID testing, because the up to this particular defect, so you will have one diameter, the smaller diameter, and below that you will have a larger diameter. So the PIT will detect actually, there will be a defect still shown by the PIT. So maybe that you have to do a capacity testing. So in this case, for example, in this particular slide, so this is the file that is been installed, right? So this is a larger diameter file. So inside that you core a small diameter, right, into the some kind of a so if you enlarge this, you can see that there's a defect here, right? And then so you go below that, right, about 1.5 times the file diameter below that. So this is the defect, right? So you concrete this portion of the file. So the above this particular defective section, the smaller diameter file is effective, right? So the larger diameter files, you may have to neglect that. Because of that, you may have to heavily reinforce this smaller diameter file as well, right? So these are the method that you can use to correct or rectify the files, the defects in the files in soil layers. But this is highly costly, and so if you are might as well use some kind of a quality controlling measures to ensure that these defects will not happen. Otherwise, after happening the defect, then you will end up with spending a lot of money. So the I don't know whether you can see that defects detected in low carrying capacity piles. So basically the carry capacity pile of the pile is very low. So extract the pile using a crane of sufficient capacity. Neglect a percentage of the contribution from the skin friction and bearing in the region disturbed by the pile extraction, because now here you are extracting the pile. So that extraction may disturb some surrounding medium. So you have to assume a certain percentage of the skin friction, right? So that will be there, right? Carry out the drill the newly installed pile to low level at the same location, right? So you are actually drilling the pile to the lower level, and your end bearing will be untouched, right? So you can use the end bearing of the location, and the skin friction up to that particular pile extraction, you can get the skin friction, and above the extraction level, you have to get the particular percentage of the skin friction, because the full percentage, full skin friction may not be available. So carry out integrity of the capacity testing of the pile. So if the in low carrying capacity piles, so these are the method that you can use. But obviously you require a crane of sufficient capacity. Right? So the options are rectification of the pile by grouting, or removal and rebuilding of the piles, right? And installation of a new pile, or disregard the pile and distribute the loading on the other piles, right? So modification of the pile cap or the capping beam may be required in that case. because you will disregard this particular pile, but the other piles you can prove that they have sufficient capacity and distribute the loading, redesign the pile cap or the capping beam, right? So what I explain here is basically, these last two methods, right? Sorry, the method 1 and method actually 3, because removal and rebuilding of the piles I have already explained, right? So the rectification of the pile by grouting the defect, right? So in this case, rectification process depends on very much on the nature of the defects, right? Verification may be needed after rectification of the pile, right? So if you consider this particular case, which I showed you earlier, so here actually this particular region, you are sure that it is fully defective, right? So maybe there are no actually, so if you drill a hole here and hole there, maybe there are no obstructing, right? So you can clean the defect very well, right? Because there are no grouted region of the hardened grout between these tubes. So that is very, very important. Sometimes you can have some kind of hardened concrete and the water flow like this, right? So here actually you can see you pump the water through this particular one drill hole, one core hole. So you have cored a hole into the pile, and through the other core hole, right? So you are using actually two core holes here, right? So you have to use two core holes, and you have to clean the defect first. You can see the muddy color water, and then it will become cleaner later, right? So when the defect is clean, right? So you can actually use this pressurized water because the defect is in the solder region of the pile. So you can do that, and also you can use this particular core hole, and you can see that if you drill a core, right, you have a particular hole here, defect here, right? This core is not continuous over this length, right? So you have to clean the defect, and then you have to use the grout, right? So if you are using two tubes, two core holes, then that can be done like that. But you have to ensure that there's proper path between these two access tubes in through the defect. But if it is not, and if the diameter is very small, you can use a single pipe to single core hole to clean the defect as well. But in that case, it becomes rather difficult. So in this case, you have the perforated holes, and so there's a no water flow here, so it is welded here, and you can lower that through that particular single core hole, right? So either way, you have to actually clean the defect, right? So this one, some of the after cleaning, so you can clean the that particular using air jet also, right? And after that, you can actually pump the concrete. So you can by measuring the volume, right? So this concrete is also under a certain pressure, right? So you can see that this is this core hole is closed, right? Using and so you pump it, and finally it will come out from this particular hole, right? So like this. So initially there will be some debris, right? But after that, it will be clean concrete, right? So this grout, this is using a grout. So you have to specially design this grout and pressurize the grout. So that is possible only the secondary region of the pile. So the other last one is actually removal of the pile and casting a new pile. So the once the pile is cast, the removal is very, very difficult. But you can do that using some kind of a piling hammer. So you can so while keeping this reinforcement cage inside, right inside the pile booth, you concrete portion up to the bottom, and after that what you use is actually a magnet, right? So you can using a magnet, using a crane, you can actually suck out the reinforcement, remaining reinforcement, right? And construct a new pile. Explaining about of a pile at a new location, but I considered only constructing of the pile at the same location, right? So you suck out the pile, reinforcement, and construct the pile. Of course, you have to neglect a certain portion of the skin friction, and you may have to drill the pile up to below this particular toe in this case, because by this hammering it can be affected. Okay, I think that's all I have. For these are some of the methods that are available. Thank you.
Thank you, Professor Samantilakasiri, for your very valuable presentation. I'm sure our audience may have some questions to Professor. Can they raise it or can they drop it to the chat box? Yeah, I mean, I will start the discussion in the absence of any questions from the audience. Professor, the rectification of piles, that is generally, I mean, we have to do sometimes. And my experience is grouting is the most effective way of doing it, rather than any other methods. I mean, if you consider the factors of the rectification, is there any kind of method where we can keep the some kind of PVC pipes or something like that, especially for toe grouting? Now, we get a lot of defects in the toe. Soft toe conditions are very common in our Sri Lankan situation. Is there any kind of possibility of keeping some pipe, I mean, before concreting, and then later that can be used to grout the toe as well as to improve the end-bearing properties of the pile?
Actually, that is possible, right? So you can actually pressurize the grout later. For example, if you find there are no defects, if you can enhance the end bearing by pressurizing the grout as well. But that may not be needed in Sri Lankan conditions, because we have fairly strong bedrock at shallow depths. But in countries like India, or UK, so you don't have the shallow bedrock. So there may be you can use a tube to and pressurized grout to increase the end bearing capacity. So that is possible. But on the other hand, for example, if you consider the rectification, that is possible. You can have tubes, before cast in the pile. But the best method is actually you can avoid the defects. If you use some kind of a good quality colony method. I have seen some of the cases where there are, of course, there are no tubes, but there are no, you end up with no solutions in some cases. Yes, that is possible.
Yeah, actually, I asked that question just to start the discussion on that matter, because now with the construction cost today, I mean, the cement and steel prices has gone up. Piling has become very expensive exercise in the construction industry. But most of time, because of the rock condition or because of the construction methodology also, we don't use the full structural capacity of the pile. because it is governed by the geotechnical capacity. Now, I have seen in some of the countries, especially developed countries like Germany, they use a small tube. I mean, that they use to post grout the pile to increase the skin friction also. And in our case, I think it may be possible to improve the rock condition if the fracture rock is there, or even if the soft condition is actually construction defect. But normally you get that problem in most of the time because of the construction methodology. And is any opinion on that matter?
Yeah, that is possible. But sometimes what is required is if there's a defect, that defect can actually cause some kind of durable issue for the pile, because if the water and the concrete, the surrounding soil is chemically active, so that can cause some kind of a durable issue. Other than that, we can use that, right? But properly, that you have to have a proper connection between the generally we install two access tubes, right? Two access tubes, and so there should be a connection between two access tubes to clean the pipe water. So if it is not possible, then that may not be the viable solution of grouting the defect. So in that case, maybe we have to look for another solution.
Okay, any question from the audience?
There are a few questions I have received.
Yeah, you can see it, no?
I can see that.
There are many, no?
Yeah.
One from Sister Gunranda. Yeah, may I read it?
Yeah, please. Yeah.
Yeah, if we use login tubes for rectification, what method to be used to damage the tubes at defective location to enter the grout into the defect?
Yeah, that is a good question. Generally, the access tubes bottom are actually sealed using some kind of a bottom cap, right? So you may have to use a kind of a hammer or something, right, to break that cap and go out of expose the defect as well. So it is basically you have to break the cap. So the cap is a problem, and also if the defect is there at the top of the pile, for example, not at the bottom, maybe problem regarding even regarding the breaking the cap, because the cap is at the bottom, right? But the defect is at the somewhere in the pile shaft as well. So then you have to see the location of the defect and also the location of the cap as well in this case.
Yeah, we have one more question from Mr. Sadaruan. In the event of PIT gives inclusive results and core drilling is not possible, in a case of small diameter pile, something around 600 millimeter, what are the possible ways of further investigations?
Basically, they want to make sure that so they have done the PIT, right? And they have detected some kind of an anomaly at the bottom or at somewhere in the pile. So it is not possible to drill a core because it is a small diameter pile. So then the problem is little bit severe. In that case, maybe some other method, like if it is not possible to core the pile, then maybe one solution would be to extract the small diameter pile. So that is one solution that you can see. But that is for the rectification. But to ensure that the rectification is needed, you know, because you may have to code the file, right, and see what is available there at the location of the defect, in that case.
Yeah, one I think is further asking if a file has a software, but the PDA reveals that it can mobilize the design load in screen friction capacity. And if there is no other way to rectify, is it okay to accept it with the available capacity?
Yeah, I think if the PDA testing is properly interpreted, and so if you are sure that the file can take the capacity, then there's no need to have the rectification process, especially if there's no defect. The software is yeah, it can be a geotechnical capacity defect, but you have confirmed the geotechnical capacity. But if there are no defects, then the file can be accepted. But sometimes what happens is you have to ensure that there are no defects. Right? If there are defects, then you may have to do kind of a chemical analysis of the groundwater and chemical analysis of the soil, and then see whether the durability of the pile will be hampered if there's a defect.
Yeah, I think if the defect is at the top part of the pile, I think you may have to rectify it because it might affect the reinforcement, and finally it will affect the integrity of the pile actually. Even it has a geotechnical capacity at the beginning, if the defect is in between, at the middle height of the pile, then I think the rectification is required. That is my opinion.
Yeah, basically, you have to see, you have to have a strong evidence that the pile will not be affected by kind of the durability will not be will not be an issue. So you have to show that very strongly in that case. Yes.
Yeah, there's one more question from Tusita Aptanayaka. If the pile failed due to corrosion, I can't understand that. Maybe he's talking about steel pile, I don't know. For old pile, is there any method to rectify it if pile failed due to corrosion?
Corrosion of the reinforcement or the corrosion of the...
That is not mentioned. Can Mr. Susita elaborate it or send a message? Okay, we are running out of the time actually. We are not getting any reply from Susita. And in that case, we will conclude our morning session, and we will have half an hour for lunch hour because we want to have AGM also at the scheduled time. And we will meet at 2 o'clock for the afternoon session. That will be chaired by Professor Atul Kulathilaka. Thank you very much, Saman, for your presentation.
Thank you.
Yeah, Dr. Fauzi, we can start in time, no?
Ladies and gentlemen, welcome back to the afternoon session of SLGS Annual Conference 2022. And as informed, the session is to be chaired by Professor Kulatilaka. Please let me do the honors. Professor Kulatilaka graduated from the University of Molatua with first class honors in 1981 and earned his PhD from Monash University in 1990. He then became an academic staff member of the University of Molatua since 1991 and rose to the rank of a professor of civil engineering in April 2006 and also as a senior professor in 2014. His research interests are in the areas of rain-induced slope failures, rectification of slopes, characteristics of unsaturated soils in Sri Lanka, soil nailing, anchored earth, improvement of soft peat clays by preloading, deep mixing, and electroosmosis. He has to date made over 90 refereed publications in journals and conferences. He is also a corporate member of IESL, and on professional service, he has been the Honorary Secretary of the Sri Lankan Geotechnical Society from 1992 to 2004, and the President of SLGS from 2011 to 2021. And presently, Professor Kulatilaka is the immediate past President of the Sri Lankan Geotechnical Society. With that brief note, please join me in inviting Professor Kulatilaka for chairing the afternoon session of SLGS Annual Conference. The platform is now yours, sir.
Yeah. Thank you very much, Dr. Fauzi, for your kind introduction. And good afternoon, ladies and gentlemen. Now we can start the afternoon session of the Annual Conference 2022 of the Sri Lankan Geotechnical Society. In the afternoon session, there are 3 presentations on pile foundations. So the first presentation will be done by Dr. Asita Senanayake. Dr. Asita Senanayake graduated with first class honors from University of Moratuwa in 2009 and subsequently obtained his master's from Texas Tech University and the PhD from University of Texas A&M. Now, today he will be doing the presentation on recent advances in design of large diameter micropiles for offshore wind turbines. Dr. Senanayake is a senior geotechnical engineer at the Norwegian Geotechnical Institute and is based on Houston, Texas. His areas of expertise include site characterization, in-situ geotechnical testing, analysis of...
So I think your mic is muted. Please unmute your mic.
No.
No, sir. We listen very clearly.
Oh, we can hear, Atula. We can.
Yeah, it's very clear.
All right. Yeah.
It is okay.
Yeah,
It's okay.
It's okay here. In my one, it is not indicating that it is muted.
Maybe.
Yeah. So, sorry, I will continue with Dr. Senanayake's introduction. Dr. Senanayake is a senior geotechnical engineer at the Norwegian Geotechnical Institute and is based in Houston, Texas. His areas of expertise include site characterization, in-situ geotechnical testing, analysis of deep foundations, and geotechnical data management. He has been involved in many of the offshore wind farm currently being developed off the northeast coast of the United States, performing a variety of roles ranging from offshore operations to data interpretation and reporting. He is a registered professional engineer in the state of Texas and Virginia. With that brief introduction, it is over to you, Dr. Asita, for your presentation.
Thank you, Professor Kulatilaka. Can everyone hear me okay?
We can hear you.
All right. Let me share my screen and get started. All right. Well, first of all, good afternoon, everyone. It's quite a privilege to be here presenting this talk at the annual conference of the Sri Lankan Geotechnical Society. And I must thank Professor Kulatilaka and Professor Navagamu for extending this invitation. And I'm happy to be here. So my talk today will be on recent advances in the design of monopiles for offshore wind turbines. Professor Kulatilaka, is this sidebar showing? Is that better?
Yeah, slides are okay, but your voice is not very clear.
Okay, let me see if I can fix that. How about now? Is that a little bit better?
Yes, okay, you continue and see.
All right, sorry about that. Since it's very early in the morning, I'm presenting from home. So maybe that's the issue. Anyway, I'll continue and let me know if you have difficulties with the audio. I'll try to improve it. So as I was saying, this topic might seem a little far and out of context in terms of Sri Lanka, but I chose it for a couple of reasons. First is that I've obviously been working on these projects in the offshore wind industry in the US over the past 5 years. And over that time, the industry has grown rapidly, and it has seen some big developments and improvements. And several governments have realized the importance of renewable energy, and these developments are taking place rapidly in Europe, US, and East Asia. So given the current energy situation in Sri Lanka, I thought as Sri Lankans, I think we should also be interested in the renewable energy sources that are available and are in the pipeline for the future. Second, offshore wind farms present some fascinating challenges in terms of geotechnical engineering. And this has led to a lot of developments in the geotechnical practice here in the US. So as geotechnical engineers, naturally, I thought we'd be definitely very interested in learning about these new developments in the state of practice. So my talk is going to be divided into 3 major sections. In the first one, I'll try to give a quick introduction into offshore wind and show a few pictures so that you know what I'm talking about and how it's related to these structures. And in the second part, I'll dive into the geotechnical details of it, and I'll talk about some of the new design methods for axial capacity, and the focus will be on CPT-based methods. And finally, in the third section, I'll speak a little bit about the design of monopiles for lateral capacity. So you must be wondering, why offshore wind? What is the advantages, and why don't we just stick with wind farms on land? So in this map, you might get part of the answer to that question. It shows sort of a heat map of the wind potential by location all over the world. And you'll see a scale on this side of the map. It shows the wind energy potential in terms of watts per meter squared, and the warmer colors represent higher wind energy potential, and the cooler colors represent lower wind energy potential. So I'll give you a few seconds to have a look at the map and study and see if you can spot some patterns. So if you were observant, you might notice that these high energy areas, which are represented by dark reds, occur along the coasts, and it occurs in the ocean. Whilst, although there are some red areas on land, they are not as prevalent. So this is not a coincidence. The wind speeds over the ocean are much higher than on land. Therefore, there is more energy to be harnessed. And let's quickly focus over here around the UK and Northern Europe. And you'll see a lot of red in this area. And again, this is not a coincidence that this happens to be the area in which most of the wind development in offshore wind has taken place right now. So the lead has been taken by the UK, Germany, Denmark, and the Netherlands. And this area in the North Sea has a lot of wind farms right now. And in the US, you'll also see some dark reds in the East Coast, in the Northeast, and this is the area that I'm working on. And although there are no wind farms, well, there is only one wind farm there right now. It's a small one, but there are many that are being developed and actively, construction has not started, but actively permitted and regulated. There's lots of activity over there. And this map doesn't show East Asia, but there's also some very high energy potentials in and around Taiwan and Japan and South Korea. Next, we can focus on Sri Lanka, since that's the area that we are most interested in. And you'll see not so much red, which means the wind energy potential is not as high. But let's take a closer look, and you'll see that there's still some yellow and orange areas, which, according to the scale, show that the wind energy potential is above average. And as you might guess, the areas with the highest potential coincide with Hambantota in the south of Sri Lanka and around Mannar. And these are the places where onshore wind farms have been constructed right now. So this is just part of the story. The next part of the story is water depth. The water depth is important because current technology for offshore wind is limited to shallow waters. And that's mainly due to the limitations in our ability to install foundations. So it is important to see whether these high energy potential areas coincide with low water depths. And you'll see these lighter region around Sri Lanka that coincides with the continental shelf, which is much shallower than the rest of the ocean. So if you take a closer look at this bathymetry around Sri Lanka, you'll see the continental shelf is about, well, less than 100 meters in depth overall. And for current offshore wind foundations, we would like to have waters of less than 50 meters, especially for this monopile foundation that I'm talking about. And again, we're in luck, especially in and around Mannar, where the water depths tend to be around 20 to 30 meters, based on my rough research. So there is definitely much potential for us as Sri Lankans in this regard. So I think it's a topic that we should be interested in and pay attention to. Next, let's take a look at some of the different types of foundations that are available. So this is a nice illustration that shows a variety of different foundations and also how it relates to the water depth. Starting from the left-hand side, you'll see this shallow area roughly represents the continental shelf, and then you see a drop and go into deep oceans. So in shallow waters, again, typically less than 100 meters, but on average about 50 meters in depth, you'll find these monopile foundations where the tower is supported by a single pile. And this extends all the way below the ground surface or the sea floor. And this is by far the most common and widely used types of foundation right now. There are also jacket type of foundations, as you can see here. So this is a platform with usually 4 legs, and each leg is supported by a driven pile. And these can be installed in greater depths compared to monopiles, but they are hard to install and also more expensive. There are also different types of jacket structures, and you'll see a specialized kind of jacket structure over here. It's called a twisted jacket. It's a new development. It had some potential, but it hasn't actually caught on that much. It's been used, but not as much as monopiles. And as we move to deeper waters, you'll see fixed bottom structures are no longer economically viable, nor are they technologically viable. So we have to switch to floating structures, and that's what you see here. Floating structures that are moored to the seafloor using mooring lines and embedded anchors. So these are currently experimental. There is only one wind farm with floating wind structures in the world right now, and that's, I believe, the High Wind Farm in Scotland, and that is still experimental. So this is an interesting graphic from one of the wind developers, one of the major wind developers in the world, called Ørsted. And an interesting story about Ørsted is that they are formerly the national oil company of Denmark. In 2017, they rebranded and renamed themselves as Ørsted to reflect that they've now completely switched to renewable energy sources. So they are 100% renewable right now. And they're a pioneer in the field of offshore wind. Starting from the early 90s, this shows the evolution of these structures. So in the early 90s, the earliest offshore wind farms or the wind turbines were relatively small, with a capacity of about 0.4 megawatts and a hub height of about 50 meters. And within 10 years, they were at 4 times that capacity, up to 2 megawatts, and a height of 100 meters, which is double the height. Now, I say these are small, but you might, on a closer look, you will find that they are not that small, because compared to onshore wind farms and wind turbines, these are very big. And based on my research, the wind turbines that are installed in Manor in Sri Lanka are also about half a megawatt, or 600 kilowatts. So they are on this side of the spectrum. And you'll see that the offshore wind turbines have grown exponentially over the last 30 years. Until this point here in 2021, 2022, this graphic is a few years old. So over here it's at 2021 expected. So this was created before 2021, and the expected capacity of a wind turbine was about 12 megawatts with a height of 260. And I mean the height of the hub, the actual total height is quite a lot higher. And maybe you'll be surprised to find out that we've exceeded these expectations. And I believe last year, General Electric came out with a 14 megawatt wind turbine. So the actual pace of development has outpaced what was expected. And also, to give you a little bit more context on the size, if you look at the size or the height of these largest turbines, the total height of excess of 300 meters, which, if you compare it with some of the commercial buildings in Sri Lanka, that would place them only second to the Lotus Tower, which is about 350 meters. So essentially, if you were to build these in Sri Lanka, they'll be the second tallest structure in the country, which is quite amazing. All right, so let's have a look at these foundations. These are some monopile foundations from a wind farm that was constructed in Taiwan called Formosa 1. And every time I look at this, it amazes me just at the sheer scale of these foundations and structures. So if you look at the foundation and compare the size with the people on the dock, you'll see how big these are and how different they are to regular driven piles that you encounter on land. And I'm not sure how clearly that you can see the numbers on your screens, but the numbers indicate the length of the pile, and this one shows 60, which means it's about 60 meters in length, and that puts the diameter of one of these piles at approximately about 10 meters. So that's a quick and rough introduction into offshore wind, why we need it, and what kind of structures we see in these wind farms. So let's now get into a bit more technical details with axial capacity of monopiles. So here's a schematic diagram of a driven pile. I always find it helpful to start off with a refresher, sort of, before we get into a lot of the technical details. So I'll try to give a quick refresher of how we design the axial capacity of a pile. And this schematic is from Jardine et al. 2005, which provides details of one of the methods we'll discuss later. So here's a pile of length L and radius R, and it's driven into place. And at the top, you have the pile head, and at the bottom, you have the pile tip. So the simplified method we use for these deep foundation designs is a effective stress method. And you might remember or know this as a beta method, where you try to estimate the radial stress acting on the pile and multiply this with a friction factor, friction angle, and obtain the friction acting at the soil pile interface. So here's the equation that we would typically use. Tau F represents the friction at the soil pile interface, and the radial effective stress acting on the pile can be calculated as some K factor times the vertical effective stress, sigma prime V naught, times tan delta, where delta is the effective friction angle at the soil interface. And once you have this effective friction, you would sum it up along the area of the pile wall, and that will give you the shaft friction. And then you'll also add the resistance at the pile tip to get the total pile capacity. So in our simplified methods, we do not pay a lot of attention to this parameter, which is represented as H. So in some of these newer methods, the CPT-based methods, this relative depth to tip ratio has been identified as quite an important parameter that governs the radial effective stress acting at a certain depth. So I'll get into more details of how that affects capacity. And another thing that affects capacity that usually not taken into account in the simplified methods is the tip condition, whether it's a closed-ended pile, or open-ended pile, and whether it's a plugged or non-plugged or a partially plugged pile that occurs during driving. So these are all very important features of a pile that governs its capacity. Now, as I said, I'm going to focus on CPT-based methods because those are the standard of practice in offshore energy. So I thought, again, it might be good to have a quick refresher of the cone penetration test in case any of you are unaware or have forgotten the CPT test, because that plays an important role in the explanation in the following slides. So here's a very nice illustration of how a CPT is done. And this is maybe not as common in onshore land practice because CPTs tend to be a bit more expensive than, say, a standard penetration test. But this is the main test that's used in offshore engineering. And it's a given and a must. And anywhere offshore wind turbine is installed, it is mandatory to have a cone penetration test done to evaluate the ground conditions at that location. So a CPT is basically a rod with a cone at the end, which is driven, pushed into the soil. And while it is pushed, we measure several key parameters. In this inset, you'll see the cone itself at the end of the rods. So it consists of a conical cone tip, a sleeve, and a pore pressure transducer. So there are three main parameters that we measure during a CPT. The first is the soil resistance acting on the cone tip, and that's denoted by QC, as you can see here, QC. And the next is the friction acting on the sleeve of the cone, which is denoted by FS typically. And finally, the pore pressure, which is denoted by U in this case. So once we have these three parameters, there's a lot you can do with them. You can do the engineering analysis. You can infer what kind of soil it is based on available charts that derive parameters based on these fundamental quantities. And something else that's important, especially for offshore wind development, is the stiffness of the soil. And that can be measured by shear wave velocities. The CPT has the advantage of being able to make shear wave velocity measurements as well if you mount a geophone or a seismic sensor. Then you can have a source at ground level and use the sensor on the CPT to obtain shear wave velocity measurement. And this is very important. All right, so that's the CPT test. Let's move along to our CPT-based axial capacity methods. So I'm going to focus on the main standard that we use in the US, and that's called the American Petroleum Institute RP2GEO standard. And it has a simplified beta method for axial capacity analysis, but in complex geology, it also recommends these 4 CPT-based methods. So CPT-based methods are important because they are generally superior to the simplified method. They provide more accurate results and with higher reliability. So CPT-based axial capacity methods have been around for a while now, since I believe the early 80s, but they really got wider acceptance in the mid 2000s, especially with these 4 publications. And you'll see that they're all from 2005, and that's not a coincidence. It actually coincides with a very important conference, an offshore engineering conference that was held in Western Australia. And that's where these 4 methods, even though they existed before that, were formally published and gained a lot of wider attention. And it ended up into the API standards in 2011. So the first method is called the ICP method. This was developed in the UK at Imperial College by Professor Jardine and his team. Second one is called the UWA method, which stands for University of Western Australia. So these are 2 methods that came from academia. And the next 2 methods are from the industry. The FUBRO method is from FUBRO, which is one of the world's largest geotechnical surveying and design companies, with headquartered in the Netherlands. And finally, the NGI method, which came from the Norwegian Geotechnical Institute. So in 2014, there was this joint industry project that was funded primarily by the offshore wind developers, and was done in collaboration with several geotechnical consultancies and universities, trying to come up with a way to measure the reliability of these methods. Because although CPT methods were known to be superior, each method had been calibrated on its own database of pilot tests. So there was no single pilot test database to evaluate and compare between these methods. So based on this joint industry project, a team of experts was assembled, and they worked for about 3 years looking at a large number of pilot tests. up to 600, I believe, and they had a stringent list of criteria to select the best out of these. And from them, they selected 71 pile tests in sand and 49 in clay, and put together what is known as the Unified Pile Test Database, which was published by Lehan et al. In 2017. So based on this pile database, we can now evaluate the performance of each method. And in this plot, I'm showing the ratio between the measured axial capacity, which is QM, and the calculated capacity, which is QC. So a ratio of 1 would mean your measured capacity is equal to your calculated capacity, which is the ideal case. A higher value would mean that the method is underestimating the capacity, and a value lower than 1 would mean that you're overestimating. So your measured is lower than your calculated, which is not desirable, because that leads to unconservative designs. So a comparison was published recently, in fact this year, a few months ago, where the results of this study was presented. And you'll see the first one is the simplified beta method that's provided in the ABI guidelines. And you'll see the mean measured to calculated ratio is 1.66 compared to the rest of the methods, the CPT-based methods, which have mean values of very close to 1, which is what we want if we want an efficient and optimized design. So this clearly shows that the 4 CPT-based methods are superior and have better performance, are more realistically estimate the axial pile capacity. And we also take a look at the reliability and the variation in these calculations, because even though the method is the same, when you try to apply these methods, there are variations due to a variety of factors. So these black lines represent the variability in each method. And the numbers are presented in the table, and you'll see the highest variability is in the simplified beta method, whereas the CPT-based methods have much lower variability, which is what we want. All right, so moving on. The industry was still not quite satisfied with the 4 CPT-based methods, because there were in fact 4 different methods, and there were issues about which method to select. So another joint industry project was initiated in 2000, right after the unified database was created, to come up with a unified method that combines all 4 different methods into a single method. And this is now called the unified CPT method. And I'm only going to show the one in sand because of the limitation in time. And this was published by Lehan et al. In 2020. And it was presented a few months ago in Austin, Texas, at a conference. So this is still relatively new information. So let's take a look at some of the details. I'm not going to delve too much in each part, but I'll try to give you the basic overview of what this entails. So as I discussed before, the capacity comes in 2 components. One, the shaft friction. So the shaft friction can be represented by the integral of the friction acting on the pile wall. So you have the frictional stress, tau F, integrated over the pile length times the pile perimeter. And now the main crux of this method is how to determine the friction, and that's related to the radial stress and a friction angle, just as the Beer method would. But the key here is that the radial stress is correlated to the CPT tip resistance QC. It also has two more components. The first one over here is called the area ratio, which represents the state of the pile tip, whether it's a closed pile or open pile. So that's accounted for. And there's also this H over D term, which represents the depth of a solid element relative to the pile depth. So this is in effect a measure of how much shear displacement a solid element has been subjected to. And the more shear displacement a solid is subjected to, the more fatigue or more frictional degradation it will endure, so lower the capacity. So a very profound realization of this is that driving the pile deeper may not necessarily give you higher capacity. Next, we have another component which takes into account the pile diameter. And it also takes into account the length of plugging, if that's a concern in the case of an open-ended pile. Next, we have the base resistance or the tip resistance. Again, the tip resistance is correlated to the CPT tip resistance, and in this case, it's represented by QP, which is defined as the average tip resistance over a length of plus or minus 1.5 pile diameters above and below the pile tip. So let's go back to a plot of comparing the methods. And now I have included the unified method as well to see how it compares. And once again, you'll see that the mean value is very close to 1. In fact, it's 1.05, which is very good. And you'll also see that the coefficient of variation has dropped, albeit slightly. It's still an improvement. So it's comparable to the 4 original CPT-based methods, and it improves slightly on the reliability. So going forward, this has not been codified yet, to my knowledge, but going forward, this is going to be the de facto method that will be used in offshore geotechnical engineering. All right, so that brings us to the next section, which is the lateral capacity of monopiles. So this is quite close to the research that I've done, because all of the research that I was involved was on the lateral capacity of monopile foundations in clay. And this is actually arguably more important than the axial capacity for offshore wind turbines in particular, because since monopile foundations are so large, they tend to have more than enough axial capacity to support the weight of a wind turbine structure. However, given that the primary purpose of the wind turbine is to harness the wind energy, it's subject to a lot of lateral loads. And you'll also realize that since the turbine itself is at a very great height above the ground surface or the sea floor, the lever arm or the moment eccentricity is extremely high in these structures. So you'll have very high moments acting on the pile. So here's a schematic diagram once again, showing the loads acting on a pile. So Q is the axial load, H is the lateral load, and M is the pile head moment. And it turns out that you can get all the information that you want for design of this pile if you can solve this fourth order differential equation, where EI is the flexural stiffness, Y is the lateral displacement, and Z is the depth below the ground surface. And finally, P is the soil resistance acting on the pile. So the mathematics is a bit more complicated than an axial capacity design, but it's still not too bad because you can solve this fourth order differential equation if this value of P is simple enough. But as it turns out, nothing is quite as simple as it seems, and especially in the case of soil. So it turns out that the soil resistance is a non-linear function of both the variable y, that's a lateral displacement, and the depth, which makes this equation almost impossible to solve analytically. So we have to resort to numerical methods instead. And the method that we primarily use is called the PY method. And that's based on a simplified assumption called the Winkler assumption, where we simplify this into a series of soil layers. And the Winkler assumption says that we can assume that each layer behaves independently from each other. So this is the method that we use. So each layer can be represented by a soil spring, which in this case happens to be a PY curve. And these PY curves can be obtained by correlating with more readily measurable geotechnical parameters such as underend shear strength or friction angle. Just realized that we might be very close to running out of time. I got, well, 15 minutes, so I'm going to speed up a little bit. So here are a couple of examples of PY curves. These are from, once again, the code that we use here in the US, which is the American Petroleum Institute code, referred to as the API code. And this presents the soil resistance, P, in a normalized fashion, divided by the ultimate capacity. So it goes from 0 to 1. And in the displacement, the horizontal axis, it represents a normalized displacement, which has the pile diameter incorporated into it. And this is a typical static or monotonic loading curve. And you have cyclic curves as well, which account for degradation due to cycling and also cycling degradation versus depth, as you can see here. So we have two main questions when trying to use the available standards for design of foundations for offshore wind turbine monopiles. The first is the ultimate limit state. So our question is, can we use the current standards to predict the ultimate limit state, especially since these standards were developed for long, slender piles, whereas the monopiles have very large diameters and very low length to diameter ratios. And second is the serviceability limit ratio, the serviceability limit state. Wind turbine structures have two specific serviceability limit states. One is the accumulated displacement, because they are very sensitive to tilt, and the other is the natural frequency, which I'll touch on a bit later. So the first answer is the pile diameter effect. So we've done a finite element modeling, and this shows some results from Abacus models with a variety of pile diameters ranging from 36 inches to 144. So that's about 3 feet in diameter all the way to 12 feet in diameter. So these results were normalized by pile diameter and the ultimate capacity, as is usually done in the PY method. So here's a plot showing these normalized PY curves from the finite element models. So this shows the curves from a depth of 1 pi diameter for all 3 different sizes, and you'll see all of them fall into almost a single line. And we've also looked at another depth, and again, it falls onto a single line, which indicates that this method of normalization correctly accounts for diameter effects. We've also done laboratory testing to verify the numerical results. So here's a picture of a laboratory test that was done at the University of Texas at Austin. And once again, the results from these tests indicate that if you normalize the loads as you should, then the pi diameter effect is accounted for. So our conclusion is that the lateral displacement normalized by pi diameter and the lateral soil resistance normalized by the ultimate resistance appropriately captures the effect of pi diameter. So we can, in fact, use the current guidelines to large diameter piles. The next is whether the capacity is correctly modeled. So we've done some analyses on field tests. So this shows the comparison between a field test and a PY analysis using the API method. And you'll see that it underestimates this capacity by quite a bit. And here's a newer method, which came out in 2009, which does a much better job of it. So these shaded areas represent variations in the parameters, which still does not account for the underestimation of the load. Okay, I'm going to have to speed up a little bit more. So this is another pile test. This is actually the original pile test on which the test was based. But once again, you'll see that the API method tends to underestimate these results. Also, some laboratory tests, which verifies the field results, which shows that the API-PY method underestimates. So our conclusion is that the current guidelines consistently overestimate the lateral displacement, or in other words, consistently underestimates the pile capacity. So there were several publications that came in the past few years which recommended higher lateral bearing capacity factors to account for this. And the next release of the ISO API guidelines are expected to have these higher capacity factors and improve the design methods. So it's something that we look forward to. Next is something called the gapping effect. This is a little bit more detailed, and due to the limitation of time, I'm not going to spend a lot of time on explaining the details of this. But basically, what it means is that the current guidelines consider only one component of resistance, whereas there are 2 components to calculation of the resistance at shallow depth. So we found out that this effect of gapping and taking both into account is quite important, which is not done right now in the current guidelines. However, it is being incorporated into the next guidelines, again, which are expected to be released later this year or early next year. I will skip this section on cyclic lateral loading because it's also quite time consuming and quite detailed, and move on to the final part, which is natural frequency. So as I mentioned before, the natural frequency is a very unique feature of offshore wind turbine design. And in this case, the governing factor is the soil stiffness. So this shows 3 different curves. And what we're interested in is in this area over here at small displacement and the stiffness. And the thing to note here is that the guidelines, the current guidelines, has the lowest stiffness. And we found that this tends to underestimate the natural frequency by quite a bit. And this was shown in a study using a reference wind turbine that was published by the National Renewable Energy Laboratory here in the US. And this is the model that we used. And it's a model that was in 20 meters of water and installed in a clay soil profile and had a diameter of 6 meters. So this shows a diagram of how we would typically select the natural frequency range for a wind turbine. Again, I'm going to skip on the details, and suffice to say that we try to aim to get into this region called a soft stiff region, where we try to keep the natural frequency of the structure between a very tight band of frequencies in order to avoid resonance between the structure and the rotor that is moving. So here are some results that was published in 2017 showing the various fundamental vibration modes based on this model and the results. And it shows how using different models will give you different answers, different estimates of the fundamental frequency and how they compare with a benchmark of a fixed base. And the takeaway point from this is that if you use the API guidelines, your fundamental frequency will be too low for this particular wind turbine, even though the more modern methods say that it's fine. So this shows the variations of the fundamental frequencies relative to the PY methods that's used. So quite a bit of variation there. Basically, the newer methods are more accurate. So the takeaway is that the fundamental frequency of a structure estimated from the API method is significantly lower because of their underestimation of the initial stiffness. However, the next set of guidelines will address this issue and will have more realistic estimates and PY curves. So to finish off, I'm going to present a little bit about one slide about this PISA framework, because without it, this presentation is incomplete. And this is very new. This was again funded by a joint industry project during the past several years. It was carried out in Europe, primarily through several universities in the UK. All the papers of this PISA method are available in a special issue of Geotechnic in 2020. And I'm happy to say they are all open access. So all of you can, if you're interested, go online and get these papers, download them and read them. So the main takeaways from this is that the PISA method is an improvement on the existing PY method. But the main improvements that they suggest are, first, since these wind turbine monopiles are very large, it's important to take into account any shear stress and shear moment that mobilizes at the pile tip. And it's also important to use a Timoshenko beam elements as opposed to Euler-Bernoulli beam elements that are typically used in a conventional PY analysis. And finally, and most importantly, they found out that the shear stresses acting the wall also play an important role in the behavior of the pile. So they've introduced these moment rotation springs in addition to the lateral springs that we use in a typical PY analysis. And of course, the details are provided for both sand and clay, and they can be found in these two papers by Professor Byrne and Professor Bird. So that brings me to the conclusion. I think that's right on the dot at 1 hour. I hope I haven't gone over time, and I'll hand it back to Professor Kulatilaka. Professor Kulatilaka.
Yeah, Dr. Sena. Can I ask a question? Doctor.
Yes, yes. Feel free to ask questions.
Yeah, I think Professor Kulatilaka may have a technical issue, I suppose.
Right.
When you have this large diameter pile, you mentioned something like 6 meters. How do you sink it to, is it a caisson type of pile? So what is the kind of construction method you adopt?
So these are primarily steel pipe piles, and 6 meters, even though it was large several years ago, now it's up to 10 meters. And they're driven into place by hammers as a conventional driven pile would be. So these are very large hammers that are used offshore. And one of the concerns as the diameters keep on increasing is, do we have hammers that can drive these into place? So it's sort of an arms race between the pile size and the hammer manufacturers. So,
Are you
yeah.
using a single hammer, or what is the kind of mechanism? You have single hammer to drive it into the soil?
So as far as I know, there are single hammers capable of installing these. Unfortunately, this is not my area of expertise because I haven't done any installations myself. Hopefully in the coming years, as construction takes place in the US waters, I'll be able to get that experience. But from the literature and from the secondhand information that I've gotten, yes, there are single hammers that can drive these large diameter piles.
So it is basically a hollow file.
Yes, yes, sir. The open-ended steel pipe piles.
The analytical method is basically very similar to the normal pile, I mean normal diameter pile, according to your presentation. And now it may be different from clay and soil. Now you may indicated the gap created by in clay soil, but sandy soil it may not be the case, no?
Correct, correct. For sandy soil, that may not be the case. In fact, I only touched on the clay soils for the lateral capacity presentation, again due to constraints in time. But the methods are very similar. I think the main concern is whether they've been verified for these large diameter piles, and that's been done as more field tests are available.
Yeah, the other question I want to ask is when the seabed is not level, how it will affect, and what are the rectification you can do to seat it on the bedrock, or whether it is considered as a friction pile throughout?
It's considered a friction pile. Refusal is a very big concern. So if and we've come across situations like that here in the northeast of the US in a lot of the site investigations due to the presence of boulders, sand waves, scour. So I think you bring up a good point about the seabed not being level. However, that can be fixed during installation by dredging and preparing the seabed. However, the changes to the seabed over the lifetime is something that we account for. We have to account for in the installation itself. And also, the other question is whether they are friction piles or fixed-ended piles. They are friction piles. The depth to bedrock in a lot of these locations are quite deep, and that's the way we prefer them. If it's a shallow bedrock, then there might be other foundation types that are considered, like suction caissons, for instance, which are shallower.
The main failure mechanism of these cylinders, large cylinders, may be buckling, local buckling of the steel. What is the kind of thickness or any you use, or any stiffness you use inside of the cylinders?
So as far as I'm aware of, a wall thickness to diameter ratio of about 50 is what I've seen.
50 millimeter.
a ratio of 50. So it depends on the diameter of the pile. So it can be for a 6 meter diameter pile divided by 50. It could be over, let's see how much that's 6,000 millimeters divided by 100, about 60 millimeters. So that's over 2 inches. So that's a rough rule of thumb for me, about ratio of about 50. And yes, buckling is a concern. So we do drivability analysis to ensure that the stresses developed at the pile tip are within expected, within reasonable ranges.
This is something outside of your topic. What kind of corrosion protection you do for this kind of steel in deep in the sea?
I think that's a very important question. It's not my area of expertise, but I've been to conferences where this has been discussed. So there are active and passive methods to control corrosion, and most recently, I was involved in some laboratory testing for a new wind farm here in the US, where they were doing sulfate bacteria tests to control corrosion, where the concern was the presence of these microorganisms in the soil can induce corrosion. So they test for that as well and try to come up with mitigation mechanisms if that's the case. So I'm not quite sure exactly how it's controlled. I know one of the methods is to have thicknesses more than necessary, but that's a debatable method because I've heard both sides of the story where some people don't like that as much, while some others say, okay, you can have a sacrificial thickness. However, there is no guarantee that corrosion will happen at a uniform rate throughout the pile. So I think active methods are also used.
So if there are no further questions, shall we move to the next one?
I think it's better, Abdullah, no? I mean, the time is fine.
So thank you very much, Dr. Asita Senanayaka, for your very interesting presentation on a topic quite new to all of us here. So with that, we will move to the next presentation. The next presentation is by Dr. Upul Atukorala and it is on the title Quality Control Aspects of Rock Supported Pile Construction, a Canadian Case History. Dr. Upul Atukorala is a Senior Principal Geotechnical Engineer in the WSP Gold Vancouver office with 35 years of consulting experience. Dr. Upul Atukorala is an industry-recognized specialist on ground response analysis and seismic design of earth structures, soil structure interaction analysis under static and dynamic loads, design and construction of deep foundations, and ground improvement methods to mitigate liquefaction. He has extensive experience in the design of foundations in liquefiable soils, soil foundation structure response analysis, and the design and implementation of effective and optimized ground improvement measures. Dr. Upul Atukorala graduated from University of Peradeniya in 1980. He's a recipient of the EOE Pereira Gold Medal in 1980. Subsequently, he has won the President's Award for Technical Innovation at Golders in 2005 and Vancouver Geotechnical Society's Lifetime Achievements Award in 2017. Dr. Upul Atukorala has authored and co-authored a number of technical papers on geotechnical design of foundations in liquefiable soils, including a chapter in the book entitled Ground Improvement Case Histories. So the paper is co-authored by Dr. Roberto Oliveira of Golders WSP Vancouver. So it is over to you now, Dr. Atukorala.
Atula, can you see my screen?
Yes, yes,
Okay, thank you. Okay, all right. So, and you can hear me well, right?
yes.
Yeah. Good afternoon, everyone. It's about 2:30 in the morning in Vancouver right now. So thankfully, Srilal woke me up about half an hour ago. Today, I'm going to share with you a project that that my colleague, Dr. Roberto Oliveira, and I have been working for the past 10 plus years. And I'll be focusing on construction and quality control aspects of rock-socketed piles. And it's a Canadian project, as you all know. And the title is a little different from what I gave initially to the organizing committee, but I think it's the content is very much the same. The project is located in southwestern British Columbia, Canada, in a place called Esquimalt. It is about 10 kilometers west of Victoria, which is the capital of British Columbia. For those of you know Vancouver is about 60 kilometers directly north of the project site. And this area of the country of Canada is subjected to earthquake loading. It's a high seismic risk area, as well as because being on the west coast, we also subjected to tsunami. So this particular structure that I'm talking about today is a marine jetty. It was designed for both the tsunami and the seismic loads, but just a project background. The presentation, I have about sort of 8 separate sections. I'll go through very quickly. Project background and subsurface conditions at the site, and also why we decided to select rock-socketed foundations, factors affecting the load carrying capacity of rock-socketed foundations, and then the measures we actually implemented during the design and investigation phases to make sure we had the right submittals from the contractors, and we had the right equipment used to construct these foundations. And I'll touch on the typical equipment that was used for these socket construction, and then I'll show you some field data on socket inspections we carried out, and can conclude that with a short summary. So project background, the project involved design of and construction of some 273 rock-socketed piles. These foundations were to support about a 300-meter long new marine terminal at this location I talked to you about. And the overburden soils at this site consist of soft marine sediments of varying thickness, overlying a very high plastic clay deposit that also varies in thickness depending on from onshore to from the shoreline to the north, the deep end of the terminal. The clay deposit is underlain by very strong and stiff granitic bedrock over majority of the footprint of this marine terminal. In some areas, particularly at the north end, there is about 200 millimeters to about little excess of 1 meter thick zone of glacial till that is sandwiched between these bedrock and clay. Now, when we say glacial till, it consists of sort of clay, sand, and gravel. It's been compressed by glaciers that existed at some time. So it's reasonably dense, but it's sandwiched between the clay, the upper clay, and the bedrock. The clay is more recent, and that is why it is sitting on top of all these materials. This is the soil profile or soil stratigraphy. Onto your left-hand side is the near shore part of the terminal, and onto the right-hand side is the deeper part of the terminal, deep in water. It's got about 10 meters of water, but not a lot of water. But I think the soil deposit, as you can see at the very north end, has about 75 meters of soil over it, and the marine sediments are shown in yellow, and the orange colors are the clay deposit I talked to you about, and below that is the granitic bedrock. And as you can see, near the shoreline, we essentially have very little to nothing, no sediments, and sometimes even exposed bedrock. And at the deep end, we have close to 75 meters of soil at this particular location, and the rock slopes down at about 2 horizontal to 1 vertical. So roughly. So it's a sloping bedrock conditions, soft sediments overlying bedrock, and of varying thickness. So those are the sort of the key factors of this key features of this soil profile. What you see here is the pile configuration that was finally decided. And you can't read anything in the text because it is flipped to accommodate the right orientation of the bedrock profile and the stratigraphy. And you can see on the left-hand side, you have a series of piles that have fairly long sockets indicated in there. And then we have on the north side, we have piles that are spaced at about anywhere between 5 and 15 meters, but with reasonably shallow sockets or shorter sockets. Because of seismic design considerations, there was some really key considerations because of the longer pile. We have a combination of longer piles and shorter piles. The longer piles, as you all know, are fairly flexible for lateral loading, and the shorter piles are very stiff and therefore attracts a lot of the load. They have a short period. And in this particular project, the structural consultant ended up extending the piles on the left-hand side to some depths to get some additional cantilever lever arm. So that we have actually we have a longer freestanding length of the pile as opposed to just to make sure that the loads are distributed evenly or as much as possible evenly across the entire jetty. Okay. So why did we go with rock sockets? First of all, the most important one is that the overburden soils are fairly weak and also compressible, and this is clay. So if you have very large settlements occurring over long periods, the heavy loads of the pile foundations, I mean, they varied between 4 and 10 meganewtons per pile, and these conditions required the foundations to be taken down to bedrock. Now, the bedrock was also not very soft. It's very hard granitic bedrock, and with the UCS values upwards of 125 MPa, and also the rock was sloping to the north at about 2 horizontal to 1. So we could take the piles to bedrock, but we didn't want to drive the piles to bedrock because we were worried about toe failure. You can have the loads applied onto one section of the pile, and very easily you can have toe damage to the pile. So these are the primary reasons. So our decision was made to to take the piles to rock, drill the piles into rock, and then socket the piles into bedrock to carry the heavy loads and to make sure that the foundations are not overloaded on one side because of the sloping bedrock conditions. If the rock was weaker, like a sandstone or even a shale, we could have attempted driving the piles into bedrock, but for this particular site, we could not do that. Some snapshots of the bedrock that we see. The bedrock conditions were highly variable. They varied. Essentially, it was granodiorite bedrock with some andesite intrusions. As I said, the strengths were upwards of 125 MPa. And we had multiple zones of fractures, joints, and also shear zones. There was some faulting that were detected, that was detected during the field investigation program. So this is just to give you an idea of what kind of material that we were dealing with when you, in terms of supporting the foundations and at depth. Of course, depending on the quality of the rock and the condition of rock, I mean the strength, the fracturing, and the shear zones, the rock socket lengths varied from one end to the other end because we were using different parameters for design of these sockets. We had essentially two different types of piles. We call one type is called type A piles. These type A piles and the type they had a slightly different socket arrangement, as you can see on the left-hand side of the figure. Essentially, the pile diameter for the entire project was the same. We maintained the same 1067 millimeter piles. Some of the piles had were a bit thicker, had thicker wall thicknesses. Some of them had about 35 millimeters, and some of them had 25 millimeters. The majority of the piles had about 25 millimeters or 1-inch wall thickness. The piles on the very shallow end, where the bedrock was almost at surface, were placed inside what we call an oversized hole, and a zone outside that pile was grouted and concreted, and that's what we call the socket, as you can see by the yellow color on the left-hand figure. The pile itself was completely filled with concrete, and the reason for that is, we, by doing that and doing this big oversized hole that is about 1.5 meters in diameter, just outside the 1067 millimeter diameter pile, we could have a longer freestanding length of the pile, so that the pile was a bit more flexible than if you had the pile installed and grouted all the way up to the top. Another complication we had was the client or the owner of the jetty wanted to place some riprap material in there. So there was some risk of the riprap material falling into the cavity between the two, the oversized hole, the 1.5 meter diameter hole, and the pile. Therefore, we ended up actually placing another casing on top of it, a short casing just standing about 1 meter above the riprap to protect any debris falling in and actually compromising the freestanding length. And these casings were about 2 meters in diameter, and they were also drilled into bedrock and sealed into bedrock. On the other side, we had what we call type B piles. And there were two types, but one, they're essentially of similar construction. You take the pile casing, 1067 millimeter pile, and you actually drill the pile into a certain distance into bedrock, and then you do the rock socket construction from that point onwards. The sockets in general vary from about 2 meters up to about 5-6 meters, depending on the load capacity. The difference between these two diagrams is that one had a longer embedment into bedrock than the other. For fixity reasons, the structural engineer wanted pile fixity at bedrock, so they were taken down a minimum distance of 2.5 meters into bedrock. Whereas on the extreme right-hand side is a very typical pile. You see the sloping bedrock, and the requirement for construction was that the pile be taken down a minimum distance of 0.5 meter below the low side of rock, which translated to about 1 to 1.2 meters of embedment into bedrock from the high side or the first point of contact of bedrock. Why am I talking about all these things, the rock conditions, the overburden soils, the equipment and everything? Because all these contribute to the load carrying capacity of rock sockets. And first of all, the condition of bedrock. Now, the fracturing in the rock and the joints in the rock, whether you have shear zones or whether you don't have shear zones, and also the intact strength of rock are important in deciding what load carrying capacity you have in these piles. Some of the piles were, I forgot to mention that some of the piles were loaded, were subjected to also tension loads, particularly the two rows on the two edges of the marine terminal. So they had both tension loads as well as high compression loads to deal with. So the rock conditions play a fairly important role. And the socket construction procedure and equipment used, these play a tremendous or very important role in deciding what capacities you can actually develop. One of the biggest difficulties, or the most difficulties we have with rock socket construction is if you don't get the pile a sufficient distance into bedrock and seal it within bedrock, there's a potential for material to slough into the socket, and it can contaminate both the shaft area of the socket as well as the bottom, the base of the socket. In which case, I mean, in this particular project, we were dealing with clay soil, so that had very a negative impact on the load carrying capacity. So it was very important to, try and minimize the material that flows in there, slough into the socket. And then, as geotechnical engineers, we had to approve each and every pile that was drilled. So having a method of inspecting the sockets, and also the timelines followed by the contractor for concreting the sockets, they were also important. Because if the visibility is poor, then you cannot use any optical equipment to inspect the piles. So you had to rely on something like sonar techniques to inspect the pile. If you have too much time elapsed between your inspections and the time you concrete it, you can have still some debris flowing through into the socket through the side walls, between the contact between the casing and the rock. So these factors were fairly important in this particular project, in making sure that we had the capacities we were looking for in the design, and also confirming that we had those capacities on site while doing construction. The bottom line is that if you construct the sockets properly and in good quality rock, they can carry very high loads, both in compression and tension. So what did we do to make sure that we get the proper construction tools and equipment and methods to make sure that we will achieve the design capacities during construction? So obviously, carrying out fairly detailed geotechnical investigations was a very important aspect. And not only the overburden soils, we ended up coring rock to depths of 15 to 25 meters, and taking samples and testing, doing a lot of testing and logging the rock conditions, the joints, the faults. They were all part of the initial investigation phase or the design phase. We also did, in each of the holes, we did borehole geophysics to map in greater detail the jointing and the fracturing. Because once you take core samples, you have a tendency to disturb the samples by the time they arrive at that surface. The borehole geophysics will give you a lot more information in situ. And another very important aspect that we implemented was when preparing the technical specifications for tendering, we actually specified to the extent practicable. I mean, we could not literally name the equipment, but we put in measures there to force the contractor to do the construction of the sockets in a certain way, to make sure that we have what we want. It is common practice in pile installation or piling contractors to start driving the piles into, or try to drive the piles into bedrock. We said, no, you can't do that. You do have to drill the piles and seed them into bedrock. So that needed specific equipment. And it also needed special sacrificial shoes to be attached to the piles so that you can drill into hard bedrock. We prohibited the contract from using impact hammers when you're close to bedrock, and churn drilling was not permitted. Those are things that we did include in the tender specifications and also during the tendering process to make sure that the contractor was aware that these aspects need to be looked into, because later on we didn't want to run into a lot of difficulties. We also wrote in the specifications, cleaning and inspecting of sockets using both optical and sonar techniques. Now, the reason for using the sonar was because we were worried about the turbidity levels in the water. Doesn't matter how much effort you take to seed the piles, there was some risk of sedimentation coming into the socket and making the water turbid. So, and especially when you're in a marine environment and when you're dealing with about 60, 70 meters of clays and sills, the marine sediments that I talked to you about, and also that till that I also mentioned in the beginning, right above the bedrock surface, these materials have a tendency to fall into or seep into the socket and make the water turbid. So we specified both optical and sonar techniques, and we wanted them all done in real time. It was so we could actually be part of the inspection process and approve each and every pile. So it's real time surveys were enforced. On top of all these, we also allowed some testing of piles. We picked 2 piles to be load tested using bidirectional load cells like the Osterberg cell. The number of tests were limited because it's a marine terminal and it's very expensive to do testing. But nevertheless, we did 2 tests, and the 2 tests have already been done at the project, and they were successful installations. So these are some excerpts from the technical specifications, as I was mentioning, like, so the pile, pile tips had to be provided with special sacrificial, shoes so they could go down there. Impact hammers were not permitted when installing piles into bedrock. Churn drilling was not specified, and then some of the video equipment capabilities, they were they were included in the technical specification that both the sonar and radar, sonar and video inspections, optical video inspections, should be carried out. How are you doing so far? Can you am I going too fast? Can you hear me well? Everything's okay at your end?
Yes, it's fine. Go on.
Okay, all right, thanks. So now I'm getting into what equipment we used for construction of piles. So as I said, there were two kinds of piles: Type A piles and Type B piles, and the 2-meter diameter casings were installed using a combination of what you call a 1.83 meter diameter core barrel. You see, so the core barrel is essentially you drill the rock into it with a 1.83 meter diameter core barrel, and then you follow it up with the 2-meter diameter casing installed using a rotator with special shoes attached to the casing bottom. The three pictures you see are the pictures of the core barrel, and it's got essentially a cluster drills around the perimeter. And you drill a annulus in the rock of about 6-7 inches, about like 200 millimeters in thickness, and then the rock is taken out, and it comes out in sort of almost like a coarse gravel, as you can see in the center picture. So this is the core barrel when it's being installed. It's got two parts, and the rock goes from the inside of this one into the top chamber of the core barrel. And then once you take the barrel out, you take the upper part out, and you can see this is the rock crushed into so almost like gravel, and you unload it, and then you put it back in there. So this is the first part of the process, and the casing follows this. This is the center picture is a casing that we used. You can see the special cutting shoe, the sacrificial shoe we had, and these are essentially carbide bits with sort of buttons in it, and it can cut through granitic rock and install down a certain distance into rock, so that you actually can see the piles. The casings were installed using a casing rotator, which is seen on the left-hand figure, sort of set up on a pile, and you can see the casing being installed in that one. And then once it is done, the 1.5 meter diameter rock hole was done using a cluster drill, which is a picture of it is seen on the right-hand side. It had, I believe, about 13 clusters in there, and you essentially crush the rock into almost like coarse sand, and then suck it through the centers and then bring it to the surface. So this is the sort of the approach you took to drill the holes and seed the casings for the Type A piles. The type, so at the end of construction, so once you do the rock hole, the 1.5 meter diameter hole, and then you bring the casing in, essentially you place it, you don't drive or do anything with the casing. You just place it to the bottom, but clean the socket, and then you place the pile in there, and then you concrete a certain section outside the annulus between the pile and the 1.5 meter diameter rock hole, and then grout concrete the whole pile all the way to the top. So that's a sort of in a sort of a step form the construction procedure for Type A piles. Type B piles are a lot simpler. It's sort of more like a standard pile. The only difference was that the piles were also the casing, the 1067 millimeter casings were provided with special sacrificial casing shoes that you actually install using a rotator and all the way down to the required minimum distance you want from into bedrock. And the casing rotator we used was a Boomer CR 2001. It's a very effective, very powerful unit to get the casings down. This was done for both the 2 meter diameter casings and the 1067 piles. The same rotator was used. Halfway through, contractor decided to use a different drill bit, and some of the piles were used, constructed using a Worth drill bit, essentially almost like having a series of sort of tricone type units. At the bottom, you crunch the rock through. What you see on the left-hand side is a drill bit from a picture of the drill bit itself. It was a slow process to do this in granitic rock, but nevertheless, it was contractor's methods and means choice. And then it was mounted on a top drive pile rig. And then again, midway to achieve some efficiencies, what they did was they also changed the Worth drill rig to have an under-reamer unit, which is shown on the right hand side. So the bottom part is a Worth drill rig, and you just mounted the under-reamer. This is slightly bigger than the casing, so that it can actually, it's about like 5 millimeters bigger than the casing on either side. So you can actually take the casing down and then support it in rock in the hole that is drilled in bedrock. Okay, so this is the type, and then once you do that, you clean the pile inside, and then you place the rebar cage and concrete it, and you also concrete the socket at the same time. But all this was done after the sockets were inspected using both optical and sonar techniques and approved for placement and concreting. The last bit of the pile was actually vibrated down. So once the socket has been done, the under-reaming hole has been done. The last about 200 millimeters or so was vibrated in, so that you have a good contact at the bottom of the socket with the casing. The socket cleaning was done using a rock auger and essentially a 10-inch airlift. And also a series of submersible pumps, because the material that comes into the socket had to be cleaned and before the inspections were done. We used two different tools the underwater camera that we used is called a deep tracker. And it's a D-top, I think, camera, and it's got what you see on the left-hand side is a camera itself, and then what is the silver color one is a camera. It's actually got 360-degree view, so you can actually rotate around a vertical axis, and also you can rotate the camera remotely around a horizontal axis. And the system that is used to lower the casing, lower the camera is on the sort of extreme left-hand side. The sonar inspections were done using a multi-frequency profiling sonar device. Essentially, what you see in the middle is the sonar device is ImageNex model 881A. And what you do is you take horizontal slices of the socket at prescribed depth intervals. Initially, we were thinking of doing it at a very short spacing, but once we've done a few sockets, we were able to relax the spacing to about every quarter meter, and because the conditions were fairly uniform. The sonar scanning or profiling will actually give you the socket configuration from top to bottom, rather bottom to top. We start from the bottom and come up on the top. Essentially lowered through a system through the pile, sort of towards the center of the pile. You are lowering it using a pulley system, and then you raise it up or down depending on where you want to see more detail. So the in terms of field data collection process, so once the socket has been constructed, once the socket has been cleaned, when the contractor has told that yeah, the socket is ready for inspection, we first did the video inspections to see what is there at the bottom, and this involved looking at the bottom of the socket, the base of the socket, as well as the walls of the socket, to see whether the condition of rock, and also whether there are open fractures and joints and shear zones in there. And also, most importantly, to make sure that there are no sediments that have sloughed into the pile. And then one of the critical aspects of the whole process was to look at the interface between the rock and the casing, for looking for overbreaks and things like that. And then the sonar inspection was carried out after that, and they were all carried out using a Microsoft Teams link, so you could do it in real time. We didn't have to be on site for that. We could do it remotely from your office or home, and then we had established with the contractor specific timelines for placing and concreting the rebar. Placing the rebar and concrete in the socket. Typical video shots, you can see this top left-hand figure. That's a casing rock contact. You can see the video quality of it, just absolute superb video quality on this using the deep tracker underwater camera. On the top right hand, you see the bottom of the socket. You can see the rock conditions out there. And on the very bottom figure, you see the edge of the socket between the vertical wall and the base of the socket. You can see some material has fallen in. This is actually the clay that was actually attached to the casing when they were drilling the pipe, to the casing that has fallen in. So if you see something like that, we actually ask them to sometimes leave it depending on the amount of material. And if it is significant, we actually ask them to re-clean and re-inspect and before we place the rebar and concrete the pipe. A typical sonar clip, you can see this is in the rock hole. This is probably about like 1.5 meters in diameter, this particular pile. And by looking at the digital data, you can actually find out the overbreak, what you see at the bottom. In this case, we had overbreak about like of the order of maximum of about like 50 millimeters, but generally within about like 15 to 25 millimeters. Some of the drill cuttings that were coming out, we were collecting samples every quarter of a meter for detailed analysis, and this will dictate what type of rock we are in. And also, if you see some discoloration in rock, that means we were in some weathered or fractured rock. So this was quite important for quality control purposes. There were other information that I don't have time to present them. We were monitoring the casing advancement rates or drill rates, and then same with the socket drilling rates. Any cross communication that was happening between the sockets when you're doing adjacent piles. And then we were correlating the drill cuttings with the boreholes and also the video sonar observations. We were also looking at the verticality of the piles. And also it was put on to us to monitor the detailed tracking of the various work activities, including downtime, etc. So in conclusion, as a summary, and rock socketed foundations can in this particular project were required to support the heavily loaded piles of this marine terminal. As I mentioned at the very beginning, the loads were varied between about like 4 to about 10 meganewtons. And the site was underlain by very soft clay materials, followed by strong bedrock. So this required the piles to be socketed. We had one of the very important things was to do extensive geotechnical and geophysical investigations to properly characterize the site soils and also underlying bedrock. The equipment selected by the contractor to install the piles, timelines followed for concreting was important, and also making sure that we have a good quality socket as per the design. Technical specifications it was important to tailor them to your needs, which is the way normally it is done. But in this particular case, we went to some extent to make sure that we had the right people with the right equipment bidding on the job. The most important one was the client agreed to pay for the sockets on a unit rate basis. So with the provision to add, delete if required. So it was up to us to make a decision based on all the inspections, whether to extend the socket a certain distance more or to leave it as it is. And so that was a big factor in success of the installation of the piles. So as of end of August, we had installed about 85% of the type A piles and 75% of the type B piles. The plan is to try and get everything installed by December, or maybe it could be January, February, depending on how the progress is with the piling work. And that's that's all I have for presentation today, and I'm open for questions if you have any.
Thank you, Upul. So it is up. The paper is up for discussion. So you can post any questions you have.
So should I go to the chat line? Is that what I should do? Or?
Yeah, yes, Upul. Yes.
Can I ask? Chairman, can I ask a direct question?
Yes. Please go ahead.
I have two questions, Upul. One is about the sequence of grouting and the concreting.
Yeah.
Are you done in one operation or you are done in two operations?
So the type B piles was easier. They were done in one operation. The type A piles, it was a little tricky because we had to do the outside and the inside. So they were done at the same time, but slightly different times. Because we didn't want to put too much grout in the center piles, worrying that it might seep out and then increase the socket length. So they were done. The inside was done first. The outside was done second to a certain height, and then we went back inside again and did the full pile.
And you had done grouting by pumping the grout into the
trimming it.
My next question is, now you mentioned these piles are heavily loaded, but it is also loaded in lateral direction.
Yes.
When you analyze the piles for the lateral forces, have you considered the soil structure interaction?
Yes. I think I didn't. I know there were two questions about what software was used to model and all these things. I didn't include any of the analysis we had done. We had modeled the piles using sort of as individual piles using various programs. We have the L-pile program, lateral loader pile program, and also we end up doing a multitude of soil structure interaction models to look at the interaction between the soil and the rock, and for the various for static loading conditions, the dynamic or seismic loading conditions, and also the tsunami loads. Tsunami loads actually control the design in this particular for this particular project. It's not the tsunami, the wave forces. It was the fact that we would have vessels berthed on either side of the terminal. So the tsunami would come, the wave would come, and it'll hit the vessel, and the vessel will actually go and impact the terminal. So those loads were very high, and this is the only terminal that I have worked on that has been designed for both seismic and tsunami. So there was a question on, can you give a brief description, explanation about the modeling, and we did the modeling using, we had done actually both 2D and 3D modeling. Because there's such a variation in pile length from one end to the other end, it was not simply possible to do individual analysis. So you had to look at the full model together to look at the soil structure response. We did ourselves 2D dynamic analysis, and then the structural engineer who was on the project did a soil structure model with our input in complete 3D. And I was told that it takes about like a week or so to run each run. That's how complicated the model was. And the software, I asked a question about what were the software I used to the analysis. So we used FLAC was a platform we used. I think the structural concern used SAP 2000, I think, in their models.
I would like to ask another question, Paul. You are not considered any kind of movement joint just to avoid this long and short pile situation?
No, I think so. There was no provision for an expansion joint in that. It was one full one composite structure. It's a 300 meter long structure, right? But there was, however, as part of this is only the first phase of this marine terminal development. This is this is a finger jetty, essentially 300 meters long, about 30 meters wide. There was another jetty that is to be built adjacent to that was almost perpendicular to this jetty, and that's called. So we had to, as part of the project, we had to develop a certain portion of that terminal as well, and design and construct a certain portion. There was a construction joint or an expansion joint between the two structures, but each structure was on its own.
Because I asked that question, you get a soft story effect with the earthquake loading or tsunami loading in this area.
Yeah, I mean, you can appreciate, Srilal. I think at the deep end, the piles were 85-90 meters long, right? And on the other side, we had shallow bedrock. Literally, we had bedrock at surface. We had to blast the rock to get down to the elevations we want. So you have a very stiff structure at the south end and a very soft structure at the deep end, and the torsional effects were huge when you have a lateral load on the pier terminal. So when you have vessels berthed on the two sides, the tsunami comes almost perpendicular. The tsunami waves come almost perpendicular to the terminal, and it gets hit when the wave comes in. So put a inserts very large lateral loads, and when the wave goes back, it gets hit from the other side. So it's got what I call a double whammy on the loads from both sides, because of the orientation of the terminal, and also because of the orientation of the tsunami wave that was coming in. So the structural engineer struggled a lot. I think if you had an expansion joint in the middle, it would actually make the two structures move quite differently. And there are cranes on top, so there are other requirements. To service this was for the Canadian Forces Base. It's a military naval terminal, the naval forces here in Canada. You have to supply with steam lines, high voltage power lines, and there was also 2 cranes on top that operate. So they could not tolerate any lateral or vertical or differential displacements. So they're all factored in, and I haven't talked about any of those aspects in this presentation.
So the structural design has to take into account all those effects.
Yes, yes. It was, Athula, this project started in 2009. And we had about multiple cycles. And finally, construction started in 2017. So 8 years of design work went in there. During that period, the design codes changed. Actually, there were 2 cycles of code revisions. So every time a code revision happened, seismic loads particularly went up. So we had to go back and redo the design.
Right. So then
There is a question in the chat box.
I can't see. I can't see. Maybe people can see. I can't see that.
Yeah, I can see it. Yeah. So what was the geographical modeling software? I'm not sure what you mean by geographical modeling. So we had the strata all modeled in FLAC in the 2D and the 3D models. The other geotechnical. Okay, sorry. Yeah. So the geotechnical software was FLAC, and the structural software was SAP 2000, as I said, but they were able to account for the soil effects because we provided them with the soil springs for the assessment. Can I know how the pile capacity was verified by testing? Yes, we had done 2 pile load tests, one for a type A pile and one for a type B pile. And they were tested using Osterberg cells, but the loading, the test loads were only done for vertical compression loads and tension loads. We didn't do any lateral load tests. We had to rely on the analysis for the lateral capacity.
What was the allowable lateral deformation you will?
So it varied. So at the deep end, the modeling was it was I think the design values were somewhere around 400 millimeters or 450 millimeters as a maximum. That was the peak transient displacement when the tsunami hits it. For seismic loading, I think the deformations were less than that. They were probably about like 100 millimeters, but then again, they were transient loads, right? So yeah, so and at the deep end, sorry, at the shallow end and near the shoreline, there were hardly any displacements. So that's why the loads are very, very high.
So if there are no further questions, so we will bring it to a close then. Thank you very much, Upul, for the very interesting information presentation. And we will, with that, we'll move to the next presentation. That will be by Dr. M. Yogendra Kumar with the title Full-Scale Static Load Test on Large Diameter Driven Steel Pipe, Canadian Case History. Dr. Yogendra Kumar is a Senior Principal Geotechnical Engineer at the Vancouver office of the WSP Golders, and he has over 25 years of industry experience in a variety of geotechnical and multidisciplinary projects throughout Canada and internationally. Yogi had been involved in and responsible for investigations, design recommendations, and construction advice for large number of bridges, port and marine projects, including for LNG and other export facilities in Canada, Alaska, Caribbean, and worldwide. He has particular expertise in the design and construction of large diameter piles, and he is familiar with the latest dynamic testing equipment and has carried out dynamic load testing of piles using pile driving analyzer PDA units for projects in Canada and North America. With this brief introduction, it is over to you, Dr. Yogendra Kumar.
Thank you, sir. Can everybody hear me?
Yes, we can see.
Can you hear me at the screen?
Yeah, we can see the screen. We can see the screen and hear you well.
All right. Thank you very much. Good evening, everybody. It's almost 3:35 early in the morning in beautiful Vancouver. This is the first time in my life at a time like 3:30 in the early morning, I have a jacket and a tie. And of course, trouser, not sarang. So anyway, let's get on to this presentation. Today, I'm going to present case history or a project that I have worked on for the Ministry of Transportation and Infrastructure. And it is a full-scale static load test on a large diameter driven steel pipe valve. So my presentation today will have different topics. First, I will give you a background and the objectives of this comprehensive pipe load test. Then I'll get into some aspects of the comprehensive monitoring program that was carried out. And then I will get into the instrumentation of the test pile, and then some installation details of the test pile and the reaction piles. Then in order to do a comprehensive load test, you should have a load frame. We'll talk a little bit about the load frame and the hydraulic jacks and the other assemblies. Then I will get into the summary results. And then lastly, I will provide you some opportunity to ask questions, and hopefully I can answer them to the best of my knowledge. So this project is called the George Massey Tunnel Replacement Project. It's in British Columbia, Canada, and it's in the area called Greater Vancouver. So the diagram you have, or the pictures you have, will tell you exactly where it is. It is on the Fraser River. The Fraser River crosses, and it's in between a city called Richmond, where I live, and a city called Delta. And through the Fraser River, there is this major highway, which is called the Highway 99, which runs from the US border all the way north to the beautiful Whistler Resort. And it is often called the Sea to Sky Highway, but in numerical terms, it's called Highway 99. So when it crosses the Fraser River at between Richmond and Delta, it has a 4-lane highway. So in the year 2015, 2016, around that time, our Ministry of Transportation and Infrastructure wanted to replace this 4-lane highway, or the 4-lane tunnel under the Fraser River with a new 10-lane bridge over the Fraser River. So they also wanted to deliver this one using what is known as the design build delivery method. Whenever you have a design build delivery method, the owners have had to develop what is known as a reference concept design, which is basically a design that tells everybody that such a design is feasible. And also it allows the government or the owner to have an idea as to how much it will cost, so that you can go to the Treasury Board and get the money you wanted. And sometimes, depending on the complexity, you will do some additional work in addition to the reference concept design to optimize the pricing and so on, particularly when there is a lot of uncertainty involved. So in this case, the ministry said we wanted to do a full-scale load test because we wanted to optimize the foundation design to some extent and come up with some realistic pricing, so that when the design bid builder give you the price, you will have some realistic comparison. So there was a RFP that came out, and then Golder, whom I am part of, was chosen to carry out this comprehensive pilot test for the ministry. Fundamentally, it involves a fully instrumented 2-meter diameter test pile and also 4 2-meter diameter reaction piles. And all of these are driven open-ended and driven to a depth of about 67 meters below surface. These all specified. This is how it shall be done. So when you do a test pile, and when you do a test pile near existing tunnel, you need to be careful what the test pile insulation will do to your critical infrastructure, including the tunnels and things like that. So to give an idea of what we are looking at, this is the tunnel entrance at the Delta, city of Delta side. And the picture on your left is the tunnel entrance. You are looking south towards US. And then on the right is Highway 99 with vehicles entering the tunnel. So it is looking north towards Vancouver. The reason I saw this picture is because when we have monitoring points and so on, this becomes very important. So this is the Delta side, and it is on an island called Dees Island. And the Highway 99 you could see, and the George Massey Tunnel you can see. And just the blue square is the test pile locations with the center test pile and the 4 reaction piles, and see how close they are to the east wall of the tunnel entrance. So they are very concerned not only of the east entrance, but also the tunnel itself. So there were lots of monitoring that needs to be done when you do the test pile program. Before I get into the details, I need to tell you what was the primary objectives of this comprehensive pile load test. First and foremost, to obtain specific measurement data on the effects of pile driving on adjacent structures and residents. So that involves a lot of survey monitoring, vibration monitoring, noise monitoring, settlement monitoring, and so on. And secondly, most importantly too, measurement data on pile load response, displacement, and load transfer, etc. In order to do that, you have to have a fully instrumented pile, which I will talk about later. All these things are done ultimately to reduce the uncertainties and risk for the future design build contract. So far, everything is good. Everybody is hearing everything okay? Can somebody say yes?
Yes, everything is fine.
Okay. So we will talk about the monitoring program. So this is again the tunnel entrance. So there was so many monitoring points. Before I go into that one, let's talk about the test pile location. TP1 is the central test pile, and RP1 to 4 are the reaction piles. And you see the green dots. Green dots are deep settlement gauges adjacent to the reaction piles. This is to make sure to understand what is happening to the foundation of the entrance, because they are supported on ground. They are not pile supported or anything. And then the purple one are some pneumatic pour pressure measurements and things like that. And the red ones, which is termed settlement monitoring east that means east wall, a series of settlement monitoring points on the east wall, and also on the west wall, which is termed as settlement monitoring point W01, 02, and so on. And then we do have vibration monitors, which are in blue, VS 1 to 6. And we have joint meter readouts, J1-1, J1-2. And within the tunnel itself, there is a lot of survey points which are remotely measured in real time. And there were tolerances set so that in any events, some huge displacement happens, it automatically sends a warning to certain people, including the project manager from our side, project manager from the ministry side. There were a couple of false alarms too, but nevertheless, it worked. And then there were about 5 robotic survey monuments. Those are numbered as 2,000 total station, 4,000 total station, 5,000 total station, and so on. And when you do a test pile program, it's important to characterize the subsurface conditions. So there was a lot of con-penetration tests done, including sample boreholes to depths in the order of 100 meters and so on. Because when you are driving piles to 67 meters, you need to have information well beyond the anticipated tip of the pile. So we have data as deep as 100 meters or more. Now, the noise meter is not necessarily at the site. It's at also at other locations, including the residential areas and so on. So on this one, the Dees Island, you can clearly see there were 3 noise monitors in the Dees Island. And on the Delta side, near the nearby residential complex, there were lots of noise monitoring. And in the Richmond side, there were a couple of noise meters that were installed. Now, I talked about the subsurface conditions. I am not going to show you each and every CPT and borehole. CPT 15-06 is a good representative subsurface conditions. This is 100 meter, the plot on the left-hand side is for the first 50 meters, and the plot on the right-hand side is for the next 50 meters. So a total of 100 meters. So essentially, the subsurface conditions at the test piles site can be characterized as some loose overburden superficial fill, followed by extensive deposit of the Fraser Delta sand up to 30 meters, followed by marine silts. And then there's another layer of compact to dense sand between depth 55 to 70 or 72 meters. And after that, there is again, you are into this stiff marine silt and so on. So ministry, when they did the reference concept design, they asked us, they calculated some capacities for a pile that's driven through the first 50 meters and some distance, some 67 meters into this thing. And they had an idea what the capacity base should be. So based on that one, they told us what should be the capacity of the load frame that you should design, and what should be your load cells capacity should be during the static load test. And I believe they never tell us exactly what their calculation was, but we had a hunch it was about somewhere between 35 to 40 meganewtons. Whether they were right or wrong, we'll get to know later. So pile instrumentation and installation. So the test pile was instrumented with, first of all, the easy one, 2 telltales diagonally opposite. If you see this diagram, if you see my cursor, there is TT1 and TT2, which is basically a square tubing that was welded onto the exterior of the 2-meter diameter pipe. And then it has 8 levels of strain gauges, starting at the bottom level, level 1, level 2, level 3, level 4, level 5, level 6, level 7, level 8. And the strain gauges were mounted on the exterior, and they were protected by angles welded to it. And at each level, the RFP required 4 gauges 4 strain gauges to be installed. But the condition is that after installing this one, at least 2 should be in working condition. So we took added safety, and we often at lower levels, we installed about 6 gauges, strain gauges per level, so that there is a lot of redundancy. So you never know how the strain gauges will behave when you drive it to such distances and so on. So we took extra care by installing additional strain gauges to add redundancy to the system. The pile installation, basically, as in industry practice, any large diameter piles, you don't directly impact them right from the beginning. You can vibrate the first segment usually to get an alignment and so on. Here you can see some of the frame, the frames or guide frames that were constructed for this one, and through the guide frame, the first section, which is about 11-meter piece, is vibrated down, and then subsequent pieces will be stacked and spliced and driven. So the subsequent pieces were driven initially by a diesel hammer, AP138, with a rated energy of 465 kilojoules, and followed by a larger hammer, which is AP180, with a rated energy of 605 kilojoules. And to get the blessing of the ministry, we had to do drivability analysis and tell them that these hammers are suitable to install them to the depth they wanted, and also to do PDA testing so that it can at least sufficiently mobilize the pile to give some idea of the capacity. But the actual capacity will be determined by the test that we will conduct later. Now, the central pile, which is the test pile we call, needs some extra attention, which is the instrumented pile, of course. So it is a 2-meter diameter steel pipe pile. It came in six basically a 12-meter sections and one 3.6-meter section. The thickness of the steel pipe pile is 32 millimeters. As opposed to this, the reaction piles had the same diameter, but the wall thickness is only 25. And as I said previously, there were 8 levels at which strain gauges were installed. So we installed, the requirement is to have 4 strain gauges, but we installed anywhere from 6 to 8. And then the other requirement is before the full-scale load test can be conducted, the first 20 meters has to be, the soil has to be taken out and filled with concrete to some level. So this is, I just wanted to give you some idea as to how these strain gauges, they are very finicky ones, so you have to pay a lot of attention. So this is at level 3 at one side. There are 2 strain gauges installed here. These are vibrating wire strain gauges, and they had to be pre-tensioned, and then they had to be tensioned so that it's within the usable range and things like that. I believe these things can hold up to a load in the order of 60 meganewtons or so. So what you do is you have these triangular steel angles welded, and then you have these new strain gauges installed, checked, and the cables run through, and then you have to wrap these things in a particular material so that when you weld the protective piece over it, it doesn't get affected by the temperature and so on. So it's very finicky things. We had to pay real attention to install them. So on your left, you see the strain gauges and the cables, all the cables from the eight levels coming out. And you will also see the telltale on one side also. And all these cables are eventually fed into a system. It's an automatic data acquisition system so that you can look at it in real time. Now, as I mentioned, there is this concrete infill for the first 20 meters. So this is a photo showing that the concrete is being trimmed. So that part, so far I have told you about the pile itself, and all the piles are instrumented, driven, how it was driven and things like that. Now the testing, before we start the test, we need to have the load frame and the other assemblies. So the next series of slides will give you some idea about the load frame and the other assemblies. So this is the part of the load frame being installed on the reaction piles. It's a heavy piece of equipment handled with cranes and things like that, and a lot of welding. And this is the completed test reaction frame. Apparently it weighs over 100 tons. And the idea behind the ministry's idea behind this load frame, which can handle load up to 55 meganewtons, is to use this one in future for every major projects that they have lined up. So they are paying upfront for this, and after that they will have it in their yard. And for their major projects, you can borrow the load frame and do the tests. Apparently, Caltrans had one many years ago, and our ministry is following their suit, which is a good idea, though. And already there is a major project that's going on right now. It's called the Patalo Bridge Replacement Project. That is also a design build delivery mechanism, and the design build contractor has used this frame to carry out load tests there. So it's being utilized. Now, whenever you have the load test, you should have a mechanism to apply the load to the. So this is synchronized 12 load cells and hydraulic jacks. And if the load cell have about 5 meganewton capacity, so 12 times 5, you can load up to 60 meganewtons if you want. The the other thing that is important here is the hydraulic jacks have a travel of about a usable travel about 5 inches or 5.5 inches, say 140 millimeters or so. So when the pile settles more than that, you have to have a mechanism to continue to use this setup. So you have to have shim plates and so on. Here you have a shim plates about 6 inches and so on. So what you do is you utilize the first 6 hydraulic jacks and load cell, and then shim it and use the next 6 to continue to load your parts. And if you see at the bottom, there is a load cell. Now you don't see the load cell because it's being covered by material to protect it from thermal effects and so on, which is very important. Those are minor things, but we have to pay attention. And so I have now described to you how the load was applied. Now you should have a way to measure the pile head deflection, and the contract or the RFP said you had to use it using a liquid level gauges. So this is the process that liquid level gauges are being installed. And on the right hand side, once it's installed, you have to protect it with for thermal effects and so on by putting a layer on top. And on top of the H pile is survey equipment. So there's a lot of ways to measure deflections. So there are a lot of redundancies were built in. So far, I'm coming to the last 10 slides, I guess. So I hope everything is going well before I go into the more serious stuff, which is the summary results. Time-wise, I think I'm only halfway through, so we should be fine. So summary results. So this is the displacement or the monitoring point of the SM04, which is on the east wall, point number 4. If you want to know where it is, it's a big red circle. I have put it here. That's where this point is. So this tells you the summary of what has happened. So let's look at the activities first. So everything started somewhere around March 1st week, March 16th, and the pile installation ended up somewhere in the second week of June. In between March and June, there's a lot of things happened. We started with the guide pile, and then we vibrated the segment in mid-March, and then there was a gap, and then we brought in the D138 and drove several sections of the piles until May 2nd or so, and in which case we brought the D180 hammer and drove it all the way to the designated termination depth. So that's the time frame, and at that time, at this point, we were measuring the XYZ. In other words, all 3 directions, what has happened. So for example, if you are interested in settlement or vertical deformation, that's the purple, I guess, and you can see what has happened for various activities. Basically, it settled about 4 millimeters or so. And the blue is the cumulative thing. Sometimes it doesn't matter that much for us, but if you look at the 3 components, you can say in any direction, nothing moved more than 4 to 6 millimeters, which is a good sign. And the ministry was happy with it. We didn't do any damage to their wall. And this is one aspect. Second summary results I'm going to show you is the crack meter or joint meter J1-1, which is circled here. Again, it measures all in all 3 directions. And if you are particularly interested in the vertical deformation, if you look at the purple, it goes up and down, and then I think it was -2 millimeters and so on. And if you look at any other thing, nothing moved more than, at the end, more than 2 to 4 millimeters, which is again a good sign. The next one I'm going to show is the vibration monitoring. What we have done here, this is only during the installation of reaction pile number 4, which is the closest to the walls and the vibration monitoring thing. To put it in very summary form, what I have done is there are 7 segments that was driven for the reaction piles, and all these segments are colored differently or numbered differently. And while that segment is being driven or vibrated or impacted, within that one we will get a maximum vertical peak particle velocity, and I have plotted that one there. So, for example, there are if you look at VS1, which is strangely on the other side, on the west side, and if that is the one that has shown highest reading, probably because when you dry the piles and when it passes beyond the foundation of this terminal, this access or entry, something happened, and that's when it VS1 showed us the highest peak particle velocity, which is not as huge. It's only 13 or 14 millimeter per second, which is in terms of damage, we are nowhere close to potential damage. So that's the story on the vibration monitors. Oops. And then this is the deep, I told you there was deep settlement gauges that was installed. And this is again the absolute vertical displacement at DSG2, which is directly west of reaction pile number 4. So when you look at this one, again, when the piles was vibrated, and to some extent when it was driven by D38, nothing happened, and all of a sudden probably because when the terminal or the tip was near this deep settlement gauge, it started to settle, and then it was when it continues to settle as more piles were driven, and then when the large hammer was put on, it also continued, and at the end it settled about an inch, maybe 25 millimeters. I think the others also showed the similar trend, but the magnitude may not be as high as 25 millimeters. So overall, everything went well in terms of the critical structure adjacent to the piles. Now, when we did the load test, we were using the ASTM 1143 standard, and we were using what is known as the procedure A, which is called the quick test. Basically, it says you have to apply 2% of your anticipated load in increments, and then hold it for up to 15 minutes before you put the next increment, and you go on until failure is observed. And when you want to unload it, you unload in 5 equal decrements. So that's basically we followed. While the test is going on in real time, we had the graph displayed. This is for phase 3. I'll explain what phase 3 means. There were 3 phases of tests that we did. I'll explain later, but this is for phase 3. Basically, it plots the load using the load cells and then the displacements using the LVDTs. And at this time, we have loaded the pile up to 26 meganewtons, I believe, and it has already showing a displacement of 100 millimeters, and it's on the flat line. It's almost starting to fail. So that's the real-time thing. Now I have put together here the load deflection curve using the load cell data and the LV and the liquid level gauge readings. There are 3 phases to this test. I want you to pay attention to the first one, which is the blue one, phase 1. So on phase 1, we followed the ASTM 1143 quick test, and everything was going well until you hit about 18 meganewton load. Then it started to deflect more and more, and every time you do the increments, it went, and our requirement is to move the piles close to 300 millimeters. So we achieved that 300 millimeters, and then we unloaded the pile. And then the ministry said, you shall repeat the test. So we started repeating the test, which is phase 2, which is the red one, but we didn't technically zero the deformation. So we continue to plot from where we left previously. So the red curve is another one that, and it's basically following the same thing. So a total displacement of 425 millimeters, and then we downloaded it, right? But if you want to see them, you can zero this for the red curve, you can zero it and say that it displaced maybe another foot or so, another 300 millimeters. So ministry was not at all happy with the results, because they were expecting, although they wouldn't tell us, they were expecting the pile to fail around 35 meganewtons, but we from the driving records, well before the pile load tests were carried out, we said, well, it's not going to, our calculation says you'll get somewhere close to 25, and they never believed, and we asked them whether we could use 6 gauges or 8 load cells. They said, no, your contract says you had to use 12 load cells, so we had to go back and do the 12, but we proved it to be correct. So ministry wasn't happy about the thing. So what they said was, guys, we want you to top up the concrete to the underside of the base plate, and then and repeat the test, which is phase 3, the green. So it took another month or so, and then we started again, and the green I have plotted here. The green, again, we took it to about 200 millimeters or so, and it stood up to, say, 28 meganewtons, so thereby. So that's the story of the 3 phases of the test results. Now, I wanted to show you the strain gauges because they are, so this is the strain gauge at level, my screen is being blocked, at level 1, which is the lowest level. They are these strain gauges have seen the most blows than any other strain gauges at the other levels. So this is, we had 6 strain gauges. Apparently we are plotting only 1, 2, 3, 4. So out of the 6, only 4 were working. So we lost 2 of them. So if you look at the kings here, the first one is associated with the first phase 1 test, which happened on August 17th or 18th, and next one is phase 2, and third one happened somewhere in September, I believe, early September or late August. So those are the 3, but you can zoom into them and get the nice readings and convert them to forces and so on, right? So that's what we did here. This is phase 1, August 18th. This is the plot of the load distribution using the strain readings. And you can see we incremented it at every 2 meganewtons, I believe. So that means ministry says every 2 meganewtons, that means 40 meganewton was their anticipated load, I believe, if you infer it. But anyway, regardless of this one, so every load increment based on the strain readings, you can convert them, which is a big process. And of course, this is without the residual load. So this gives you some idea of the load distribution within these 67 meters of pile. And that's the whole idea of doing the strain gauges. So that brings to the end of my conclusion. If the project has gone ahead, we would have seen a bridge similar to this one. But unfortunately, the government changed, the priorities changed, so this project was never materialized after spending so much money and so on. So with that one, I will answer your questions right now. I don't know, do I have to see the chat line? No. All right.
Yes,
So
yes,
before, go ahead.
Yes, there were 3 questions in the chat line.
All right. Yeah. What was the strain measurement intervals? I'm not 100% sure what he means by strain level. These are all automated, so I don't know. Are you talking about microsecond or milliseconds? I'm not 100% sure, but
There's a question, is there any special reason to install strain gauges outside of the casing?
well, these okay. These are open-ended pile, large diameter pile. So when you drive an open-ended pile, the soil will come inside, right? So yeah, that's number one. Therefore, we don't want to install gauges on the inside. The other thing is it's easy to install them outside because there's a lot of welding, a lot of cable things that needs to be
but outside
put through.
But outside also it is interacting with the soil surface, no?
Yeah, but you have a 2 meter diameter pile with a small angle, so the interference will not be that much though on a large scale, right? So you have a small angle only, so it is that is to protect the strain gauges. It's not a huge angle or anything, right? So.
And there was another question. What was the strain gauge measurement in strain measurement interval? What was the strain measurement interval? Question comes from RM Abhisu.
That's what I tried to answer by saying, I don't know, this is all automated thing. So I don't know whether it was said to take every milliseconds, or I'm not 100% sure. So
Questioning about the time interval. It's asking about the time interval.
when you say time interval, when you do
Strain measurement interval, the time interval.
yeah, you do it whenever the load is being applied, right? So you measure it every I don't know, every second or millisecond to get the whole picture, right? I'm not 100% sure what the question is. At the same time, I'm not 100% sure what the time interval was set to read the strain gauges. I'm pretty sure it's very small interval, right? So that you won't miss out any of the maximums and so on. There was a question, what was the maximum allowed for peak particle velocity? I had to go. Yeah, I think initially it was set to 10 millimeter per second, and then we convinced the ministry to make it to after the first few segments of piles were driven, they allowed us to go up to 25 millimeter per second. But typically in the pile insulation business, half an inch per second or 12.7 millimeter per second is the we normally say maximum allowed peak particle velocity.
Chairman, I also have a small question. Yogi, when you do this kind of pile testing using the tensile piles, what is the kind of maximum distance you must allow between the test pile and the reaction pile?
Well, if we have to go by the ASTM standard, the clear distance between the reaction piles and the test pile is, I believe it's 4D, I believe, or 5D. I'm not one of those. Although there are finite different studies that were done to say lesser distance may not affect the results. But ASTM says if you don't meet their requirements, then there must be a numerical analysis carried out to see whether there is a reduction factor that should be applied to your test and so on. So, but there was a case in BC where Upul helped me with some finite difference method and so on to prove, although the clear distance was not met according to the ASTM standard, but the distance that was provided for the actual case did not impact the results that much. Therefore, no reduction in load, no reduction factor was applied to the load.
And these reaction piles also driven piles, no?
Yeah, they were the same diameter, same, only difference is its thickness is 25 millimeters. They all were driven to the same depth.
And it is not to the rock, no? It is maybe...
No, this is all Fraser River sand and gravels, yeah.
You have not considered any kind of cables instead of piles as for the reaction piles?
No,
Anchors, ground anchors.
because sometimes we have done it for small diameter piles, but for large diameter piles, usually what happens is some design build contractors will do it on the actual pile caps. So what they will do is they will select piles such a way that they will do the test on the actual production piles, and then they will tell the ministry this is the results. Usually in that case, the reaction piles and the test piles, everything is the same diameter, same thickness, same depth driven almost, and so on, right? So, and ministry's intention to have a load frame made was to encourage people or the contractors to do the confirmatory pile load test using the system of 4 reaction piles and one test pile.
When you do this kind of pile testing, do you measure the deformation of the reaction pile also? Because
oh yes, we do everything. We do PDA test on this one. Actually, I forgot to mention there was one level of strain gauges above the ground was installed in all reaction piles. And then for the reaction piles, we will be monitoring how much it's coming up during the test pile program. There's tons of data that we generate in a test pile program, right? So, because if reaction piles fails, and then the test pile won't be able to be loaded to the load that you want, right? So we take extra care in every one of them, the reaction piles and so on. The only time we use anchors and so on with reaction pile is if you are driving into bedrock or glacial till, because you may not have enough tension capacity to load the test pile in compression to the full extent. Therefore, sometimes we had to increase the tension capacity of the reaction piles. We may put additional anchors in the middle of the reaction piles to increase the tension capacity. I wanted to take this time to answer this question from somebody. How did you evaluate excess force acting on adjacent tunnel structure and displacement and vibration? To be honest, I don't know, but we were told to measure the displacement and vibration and give it to them. The idea here is if it doesn't settle, if it doesn't displace so much, then everything is good. Did I answer all the questions?
I think so, because I can't see some of the questions, but you can see all of them. Yeah.
Okay, I think one last question was for Upul. I don't want to answer, but yeah, all those questions, I can see all the chat line, and I would say I'm sure I did answer all of them.
Right. If there are no further questions, we can bring it to a close. Sahabandhu,
yeah, I think our next item is the vote of thanks by Professor Udayani Amagam.
yeah, so in that case, so I will close this presentation Dr. Yogendra Kumar, thank you very much for your very informative and interesting presentation. And especially thank you for getting up very early in the morning and doing this presentation for us. So thank you very much. So
Thank you. Thank you.
so we'll close the presentation and then it is for the vote of thanks now.
Udeni, අතල උදේනි නැද්ද? අතුල
Okay, right. Thank you very much, Mr. Chairman, our most valued invited speakers today, ladies and gentlemen. It's my privilege to have been asked to propose the vote of thanks on this occasion as the Honorary Secretary of the Sri Lankan Geotechnical Society. First and foremost, I would like to acknowledge the voluntary contributions made by the invited resource persons today. Professor Gray Mullings, he is now facing a worst hurricane in Florida. Despite his facing this severe hazard, he sent the voice-embedded presentations before the evacuation. Thanks a lot, Professor Gray Mullings, for your presentations on thermal integrity profiling of board piles. Professor Emeritus Harry Poulos of the University of Sydney is to be mentioned with a word of gratitude. A very senior, world-renowned geotechnical engineer, a very humble gentleman, presented a very important presentation on bridge foundation design. Professor Saman Tilakasiri, who made a presentation on identification and rectification of defective board pile foundations, must be thanked not only for his contributions, but also connecting Professor Gray Mullings with the SLGS. Dr. Asita Senanayaka from the NGI discussed his experience in offshore piling. Dr. Upul Atukorala shared the Canadian experience on quality control aspects of rock-socketed piling. Another Canadian experience was shared by Dr. Yogendra Kumar on full-scale load test on large diameter driven steel piles. 6 experts contributed to our theme today on pile foundation designs, construction, and testing. On behalf of the SLGS and the participants, let's appreciate them using our traditional manner. Thank you very much, all the presenters. We must thank Dr. Fauci for being the Master of Ceremony, and Engineer KLS Sabandu and Professor Attula Kulatilaka for chairing the 2 sessions. There are a few others who were instrumental in organizing the event, especially communicating with the possible resource persons. Dr. Jayanta Amaratunga from Australia, Professor Tilakasiri, and Engineer Sabandu. Engineer Vatsala Galhena, our Assistant Secretary, played a major role in organizing the conference, and Engineer Janaka Priyantha assisted her. The exco, including the Treasurer, Assistant Treasurer, the past presidents, and the members are always acknowledged for their voluntary contributions when the need arises. Thanks are extended to the NBRO, RDA, CCB, Irrigation Department for encouraging their members to participate in this conference. Without your participation, this would not be possible. Thanks a lot for a great participation. Once I saw it was more than 115. Mr. Kapila Bandara for handling the Zoom sessions from Kandy must be acknowledged. If I miss anybody, I beg your pardon. For those who participate in the AGM, the members of SLGS, I would like to request, please stay with us. Thank you all and have a pleasant evening. Thank you very much.
Thank you.
Thank you guys for organizing this.
Thank you, Pul.
Mrs. Abandu, now we have to start the AGM, and then we have to request those who are not members, they can leave the session now.
Yeah, now they can hear you, no? I mean,
yes, that's what I informed. Yes.
Shall we start immediately?
Yes. Better we start the.
Okay. Good evening, everyone. This is the 25th General Meeting of Sri Lankan Geotechnical Society. The first item of the agenda is reading the notice convening the meeting. I invite Honorary Secretary to read the notice.
Yeah, thank you, Mr. President. This is the notice convening the meeting. The 26th Annual General Meeting of SLGS is now open. Yeah, Mr. President, that is.
Thank you, Udeni. The next item is the presentation of the minutes of the previous general meeting and its adoption. I will invite the Honorary Secretary to read the minutes of the previous general meeting.
Yeah, I will share it now. So this is the minutes of the SLGS AGM number 25 held on 27th October 2021 virtual platform. So the 25th General Meeting of the Sri Lankan Geotechnical Society was conducted via virtual platform on 27th October 2021. The meeting commenced at 5:15 p.m. and the President, Professor S.A.S. Kulatilaka, chaired the proceedings. Minutes of the last general meeting, Assistant Secretary Engineer M.S. Musair presented the minutes of the 24th Annual General Meeting held on 23rd December 2020. Engineer K.L. Sabandu pointed out that the minute on the proposed act after finalization to appear in the newspapers need not be included since there might not be such a mandatory requirement. The membership agreed with the suggestion and Engineer Sabandu proposed adoption of the minutes subject to the correction, and it was then seconded by Professor U.P. Nawagamo. Statement of accounts. Assistant Treasurer Engineer R.M. Ratnasiri presented the audited accounts of the SLGS for the year ended 31st March 2021. Dr. Asiri Karunavardhana proposed adoption of the accounts, which was seconded by Dr. Nalindi Silva. Secretary's report. The Assistant Secretary then presented the report on activities of the Society since the last general meeting. Engineer Kirti Senanayaka suggested that the notice on the AGM had not been noticed this time due to the reminders on AGM notice went along with the project day notice and hence the poor participation of members. It was decided to send separate notice of the AGM from next year onwards. It was suggested to consider the life honorary membership fellowship category for those who have contributed their time for many decades for the betterment of SLGS and also for upliftment of geotechnical engineering. Engineer Sabandu stated that this could be done in the proposed Parliament Act and the bylaws published after passing the Act in the Parliament. Number 4, adoption of resolutions. No resolutions were received as of the stipulated deadline. Address by the President. President Professor S.A.S. Kulatilaka opened his address with the activities related to the postponed third International Conference on Geotechnical Engineering, Colombo 2020, due to the pandemic situations. He briefly explained the arrangements and the status of the conference. He further explained activities conducted during the last year and the present status of the Parliament Act. During the subsequent discussions, it was decided to request for sponsorship for ICGE 2020 conference. Professor Samanthi Lakasari inquired on the benefits that the sponsors would get for sponsoring in the conference. Engineer Sabandu explained that in many ways we can provide time for the sponsors' promotional material before and during the conference time, as usually done in other similar conferences. A detailed discussion was proposed to have on this in the next EXCO meeting. Number 6, election of office bearers. The next item in the agenda was the election of office bearers. Professor Atula Kulatilaka thanked the membership for supporting him during his tenure and requested to appoint a new president and the other positions in the executive committee following were appointed. So I will not go through the details. The President, Engineer KLS Sabandu, Vice President, Dr. Asiri Karunawardhan, Honorary Secretary, Professor UP Navagamo, Assistant Secretary, Engineer Ms. Vatsala Galhen, Treasurer, Engineer W. Bandara, Assistant Treasurer, Engineer Mahinda Ratnasiri, Editor Journal, Dr. Nadij Priyankara, Editor Newsletter, Dr. Sampath Hewage. EXCO members are Dr. Jason Fauci, Professor Samanthi Lakasari, Dr. Nalindi Silva, Dr. SK Navaratna Raja, and Engineer Janaka Priyanto. Engineer Kirti Senanayake and Professor Atula Tilaka will serve as past president in the executive committee. Engineer KLS Sabandu thanked for the trust and confidence that the membership had on him for the appointment as the president of SLGS for the year 21-22. He stated that he had joined the SLGS in mid-1980s with the persuasion by the founding president of SLGS, late Professor A. Thurai Raja. Engineer Sabandu further stated that he had been serving the SLGS as a committee member, treasurer, honorary secretary, and the vice president for many years, continuously since early 90s. He had given an assurance that he would try his maximum capacity to establish and improve the recognition and acceptance of the society and the geotechnical engineering discipline in the Sri Lankan society, industry, and in the regulatory establishment. He pointed out the need of completing the procedures related to the Parliamentary Act, Act of SLGS. Also, he emphasized the need of encouraging the university students and young graduates to further their attitude towards the outgoing president, Professor Kulatilaka, for his untiringly efforts to develop the SLGS for many years as the president as well as EXCO member. He requested Professor Kulatilaka to assist the new committee to take forward the development of SLGS. Dr. Asiri Karunawardhan thanked the outgoing president, Professor Atula Kulatilaka, Honorary Secretary, Dr. Jason Fauci, and his assistant engineer, MSM Usair. Appointing of company secretary and auditor, Mrs. SP Corporate Consultants Private Limited and Ponnam Perumal Company were proposed as company secretary and auditor respectively by Engineer Mahinda Ratnasri and seconded by Engineer KLS Sabandu. The meeting was adjourned at 6:45 p.m. with the induction of the new committee, who decided to fix their first meeting on the 3rd November 21 at 7 p.m. Signed by Professor UP Navagam, Honorary Secretary, Sri Lankan Geotechnical Society. Mr. Sabandu.
Sorry, I was muted.
Yes.
It is a time for the comments of the minutes read by Professor Navagamua, or adapt it as the correct minute of the last annual general meeting. Any comments?
The minutes be adopted.
Yeah.
Pardon,
yeah, Professor Tilakasiri proposed it.
Yeah.
Yeah, the confirmation of minutes.
I second it.
Okay.
Nalindi Silla, I think Udayan you have to write it.
Yeah, I am writing. Professor Tilakasiri confirmed and Dr. Nalin seconded.
Okay. Then our next item is the presentation of the report of SLGS activities for the period from 27th October 2029 to 29 September 2022. I invite Honorary Secretary to present the report.
Thank you, Mr. President. Now I am sharing this the Secretary's report. I will brief the activities of SLGS during the tenure of the Executive Committee from 27th October 2021 to 29 September 2022. So 25th Annual General Meeting and Executive Committee for the tenure during 27th October to 29 September 22 was held on 27th October 2021. And I have already reported the members, the team. And the SLGS newsletter, during the last tenure, SLGS was able to make 3 issues of the SLGS newsletters in December 21, March 22, and August 22, which were numbered as 21 December, number 21, number 22, and number 23. And geotechnical forum and workshops. The society was successful in organizing 7 virtual geotechnical forums and 1 workshop with the contributions from eminent personalities on contemporary topics as follows. Geotechnical Forum on Geotechnical Design and Construction Challenges, a Canadian jetty reconstruction project on 26th January 2020 by Dr. Upul Atukorala, Principal Engineer, Gold Associates Limited, Vancouver, British Columbia. Series of Geotechnical Forum on Deep Foundation Best Practices on 23rd February 22 and 30th March 22 by Dr. Nalindi Silva, Senior Lecturer, Department of Civil Engineering, University of Moratuwa. And Geotechnical Forum and Introduction to Eurocode 7 on 27th April 22 by Professor Saman Tilaksiri, Dean, Faculty of Engineering and Senior Professor, Sri Lanka Institute of Information Technology. Geotechnical Forum on Ground Improvement Techniques on 8th June 22 by Dr. Nadish Priyankar, Senior Lecturer, Department of Civil and Environmental Engineering, Faculty of Engineering, University of Pune. Geotechnical Forum on Evaluation of Alternative Earth Retaining Wall Designs to Identify the Optimum Wall System on 29 June 22 by Dr. Priyanta Jayavikrama, Associate Professor and Associate Chair, Department of Civil and Environmental and Construction Engineering, Texas Tech University, Lubbock, Texas, USA. Geotechnical Forum on Ground Improvement Techniques used in the Al Raha Beach Development Reclamation in Abu Dhabi on 27 July 22 by Dr. Suraj De Silva, Technical Executive, WSP, Australia. Geotechnical Forum on Case Study on Agate Creek Slope Stabilization and Bridge Renewal, Prince George, British Columbia, Canada on 31st August 22 by Dr. M. Yogendra Kumar, Principal Engineer, Gold Associates Limited, British Columbia. And then we had 1 workshop. That workshop was held, workshop on Eurocode 7 for Geotechnical Design was successfully conducted on 16 June 22 via virtual platform. Resource persons were Professor Atula Kulathilaka, Professor Samanthi Lakasri, Dr. Nalindi Silva, and Dr. S.K. Navaratna Raja. SLGS Journal. The SLGS Journal, Volume 8, Number 1, December 2021 was published and was available online through the SLGS website. Journal included 4 journal papers under following topics: development of compacted clay liners for solid waste landfill using locally available expansive soils by N.H. Priyankara, M.A.G.P. Pereira, and A.M.N. Alagivan. Evaluation of slope stability of municipal solid waste dump site using probabilistic approach, VRS De Silva, N.H. Priyankara, and A.M.N. Alagivan. A comparative study of use of different facing types of soil nailing in Sri Lanka, B.I. Kumarage and S.S. Kulathilaka. Modeling of hydromechanical alterations in fractured coal caused by stepwise CO2 injection, KHSM Sampath and MSA Pereira. SLGS website, which included new facet with all modern day functionalities, has been launched in June 2022. Further minor adjustments works on payment gateway and member portal has been initiated by the assigned web developer. Sri Lankan Geotechnical Society Incorporation Act draft bill for the above is ready in all 3 languages, Sinhala, Tamil and English. for forward action through the Parliament. Third, ICGE Colombo 2020. ICG Colombo 2020, the third international conference, was concluded successfully on 6th and 7th December 21 on a virtual platform, and that was zoomed in by over 250 participants. The conference was staged under the theme of geotechnics in a challenging environment. The inaugural session of the conference was graced by the President of the International Society of Soil Mechanics and Geotechnical Engineering. The 5 keynote addresses by prominent geotechnical engineers over the 2 days were one of the key attractions of the conference. The details of keynote addresses are as follows. Unsaturated soil mechanics and bioengineered soil soaps with a focus on hydrological effects by Professor Charles Neng, Hong Kong University of Science and Technology. Ground improvements for rail and road infrastructure by distinguished Professor Buddhima Indraratna, University of Technology, Sydney. Lessons learned from failures of embedded retaining walls by Dr. Brian Simpson, Arup Fellow Principal of Arup Geotechnics and Honorary Professor at the University of Nottingham, UK. Foundation Investigation, Analysis and Design for High-Rise Buildings by Dr. Chris Herberfield, Principal Gold Associates, Australia. Modeling coupled dynamic processes in landfills, holistic long-term performance management to improve sustainability by Professor Krishna Reddy, University of Illinois at Chicago. This conference was conducted with 3 parallel sessions on day 1 and 2 parallel sessions on day 2. 96 peer-reviewed technical papers were presented by the researchers and practitioners from all over the globe. So the report prepared by Professor U.P. Navagam, Honorary Secretary, and presented on 29 September 2022.
Thank you, Professor Navagam. It is time to discuss the report. Any comments or any improvements? You can present here. Any comments? Atula, you want to tell something?
Mr. Sabant, we can report the progress of the Parliament Act that you can report it to the membership.
I will talk about in my president
Okay.
address on that.
Okay.
Okay, if there is no comment.
We had a very successful year, so we should make it a point to continue the same good work in the coming year as well.
Yeah, actually, we have done a lot of things with the help of all the members of the executive committee. I mean, thank you for that, for the cooperation and working together as a team. That was the main reason. We have success a lot of things during this year.
Yes. Mrs. Abantu, you can request somebody to press propose and second. Somebody has to propose and second.
No, this is not necessary.
Not necessary, right? Okay.
Yeah. The next item will be the presentation of statement of accounts and its adoption. Our Assistant Treasurer, Mr. Mahinda Ranasiri, can you present the financial statement of the society?
Yeah. So I can share. No?
Yeah, you can share.
So this one I have circulated to the executive committee earlier. So this year we have membership and membership related income. 5 million.
Can you enlarge a little bit?
Yeah, okay.
Or you can do it from the top. There is a plus and minus.
Yeah, just increase it to 100% or 110 like that.
At the moment, it is 75%.
75, yeah, that's why we can't read it.
Okay, no?
So even 110?
110, yeah.
125.
Okay, good.
Okay.
And you present mind from the.
Yeah. This year we have membership and membership related income 5,330,439. Then other income, this is the interest from the fixed deposits. We have 622,977 rupees. Then the expenditure for this year is 1,685,968. Then the net income before taxation is 4,267,247. Income tax for this year we have to pay 149,514. Then we'll go over the details. Current assets we have fixed deposits 13,577,788. That is up to 31st March this year. In current assets 3,992,531. These are the details: membership and membership related income. Membership fees 10,000, and event registration and conference income 5,320,439 rupees. In interest on deposits 622,977. These are the details of the expenditure: audit fee, bank charges, depreciation, printing and postage, stationery, professional fees, secretariat fees, membership fees paid. This is the ISSMG membership. Then event expenses, traveling, advertising, web development. These are the main expenditure this year. Total expenditure is 1,685,968 rupees. These are the fixed deposits we have. NSB we had of course 2 FDs. Then Sampat Bank we had 5 FDs. These fixed deposits were up to 31st March. Recently, this month because you can see here that previously you must have seen that the interest rate was very small, even less than the last year. The interest amount was less than last year. So you can see here net cash flow used in the investment activities. Interest. Last year it was 1.3 million. This year 622,000. So what we did was we redeposited these fixed depositors this month. We closed all these accounts and opened new accounts to new fixed FD rates. Then People's Bank, we have a small amount 14,272. 73. People's Bank savings account 43,762. Then Sampath Bank, this current account, this one also we use for the fixed deposit, 3,227,570. This was in current account. This also has been transferred to FD now. Commercial Bank, we have 574,339. Then cash in hand is up to 31st this year, 132,587. Then other creditors and accruals, secretary fee 39,858, and payable 80,000. This already has been paid. This is for printing expenditure. This has already been done after 31st March. Audit fees 30,000. Then income tax previous year this March 183,872, and provision for this year 149,514. This one we have to pay by tomorrow. I have already paid the check, sorry, written the check and sent for this amount. And this is how the income tax has been calculated. Yeah, this is the end of report. If there is anything to clarify, I'm willing to answer.
I just want to add to the treasurer statement, because of the sudden increase of the interest rate, the committee has decided to close down the fixed deposit, because those things we had about average 5%, 6% interest rate, and we have opened new accounts at NSB, I think at the rate of 25% interest rate, and at Sampath Bank, I think it was 24% interest rate. Both are very special interest rate because we got it after negotiating with the management of the relevant bank. And also we left only 1 million in the current account. Now we basically have 10 million in Sampath Bank and 5 million in NSB and 1 million in our current account approximately. I mean, those are the values. Any more comment from the audience or membership? If there's no comment, could you please, somebody can propose and second that accounts are in order?
I will propose that the accounts are in order.
I second it.
Thank you.
Okay, thank you. Then next item was next item is adoption of resolution. We don't have any resolution, and because of that, we cannot take that matter for the discussion. The next item will be the address by the president. Dear members of SLGS, good evening to you all. It has indeed been an honor and privilege to serve as the president of the prestigious Sri Lankan Geotechnical Society for the first term, started in October 2021. I am humble and deeply grateful to the membership for having faith and electing me and providing me with the great opportunity held by our illustrious past presidents over the last quarter century. I consider it as my duty in this evening to recollect and gratefully acknowledge the significant contribution of our past presidents, whose dedication and commitment helped us to build and advance the professional status of SLGS to what it is today. Late Professor A. Ture Raja, our founding president, for his visionary leadership in forming the society in 1986. Professor B.L. Tennakoon and Engineer D.P. Mallavarachi for their untiring efforts, especially in getting recognition for the society in the industry and other international forums. Engineer Kirti Sri Senanayaka and Professor Atula Kulatilaka on evolving trained practitioner academia interaction in advancing industry-relevant geotechnical engineering, best practices and knowledge in Sri Lanka. With my newly elected executive committee, we were engaged in strategic planning to contemplate our society's future. Our priorities have been to strengthen the society and serve our members and our community as best we can while maintaining their present status and activities. Please allow me to list out some of these. The committee took efforts to conduct conferences, geoforums, and workshops of international standards to facilitate knowledge transfer to our members. And general public. In the connection of last executive committee, conducted the following programs during their tenure. A. Organizing international conference. As organized by previous executive committee, ICG Colombo 2020, the third international conference was concluded successfully on 6 December 2021 on a virtual platform, which was zoomed in by over 250 participants. The conference was staged under the theme of geotechnics in challenging environment. The inaugural session of the conference was graced by the president of the International Society of Soil Mechanics and Geotechnical Engineering, ISSMG. The conference was conducted with 3 parallel sessions on day 1 and 2 parallel sessions on day 2. 96 peer-reviewed technical papers were presented by the researchers and practitioners from all over the globe. Annual conference. This year, the executive committee was able to organize the annual conference, which was concluded a little while ago with the participation of the world-renowned geotechnical professionals as resource persons. Geotechnical Forum. In support of the professionals of our membership and the engineers who are involved in geotechnical practices, by affording them professional dialogue, this year too, Society conducted the monthly Geoforum uninterrupted. The Society was successful in organizing 7 virtual geotechnical forums and with the contribution of eminent professionals from Sri Lanka and overseas on contemporary topics. These events were well attended by the engineers who are involved in the field of geotechnical engineering. Workshop. Towards making the Europe code more familiar in Sri Lanka, a workshop on Euro Code 7 for geotechnical design was successfully conducted on 16 June 2022 via virtual platform. Over 100 participants attended on this workshop. SLGS newsletter. During the last tenure, SLGS was able to make 3 issues of SLGS newsletters. This number of publications should be increased to 4 for an year. That will be the target of the coming committee. Keeping up with the technology and new media communication, the Society now has a Facebook page and we are working on being present in all other outlets like LinkedIn, etc. Please follow us and send us your feedback. Due to the present economic crisis of the country and effect of COVID pandemic, in Sri Lanka, construction industry has got affected very badly. I believe our members are also affected due to these factors, which are beyond our control. Hope this situation will gradually improve in coming years. I have missed one page here. Gaining industrial recognition, including increased awareness among policymakers and the political leadership to achieve prime responsibility status and lead role for geotechnical engineers in the development, design, and implementation of mega-scale national engineering projects. In this connection, establishment of society under Parliament Act is very important. The proposed Parliament Act has been finalized, including translation in Sinhala and Tamil versions. Subsequent tasks would be making it appear in the newspaper and in the government gazette for observation of the public. Engineer Ajit Manamperuma, Member of Parliament, given his consent to forward this in the Parliament as a private member motion. Hope we will have an uninterrupted Parliament session to accomplish this goal. Because last year we couldn't do it because of the discontinuation of the Parliament during that tenure. In addition, the incoming committee shall positively consider gaining membership at Organization of Professional Association, OPA, and Chamber of Construction Industry, CCI, which is considered as the apex representative body of the construction industry after SLGS being established under the Parliament Act. In addition, SLGS will try to gain recognition at Construction Industry Development Authority, which is authorized to publish qualified person in construction industry. That we have to do because unless we are listed at CEDA, we can't call we as qualified person in construction industry. Publications. During last year, SLGS positioned to relaunch their website with many new features, such as society history, membership publications, events, ISSMG time capsule, and contact details. It is necessary to improve and maintain the website which will reflect the society status. SLGS Journal. The Executive Committee managed to publish one volume during their tenure. Now SLG Journal is available online. The next committee should try to increase number of volumes published in a year to get required recognition. Before I wind up, I am grateful to my fellow colleagues in the Executive Committee as well as the membership for being with me throughout my first term. And I am hopeful that you all would continue to do so in future as well. Thank you very much. Do you have any comments or any suggestions?
I think it's a year of activities. We had a lot of activities last year.
Yeah, actually, we had to concentrate this year to get the Parliament recognition. I mean, I think Professor Samantilaka is working on that. He has already contacted this batchmate engineer Ajit Manamperuma, and he has basically agreed to forward it to the Parliament. But we had to go and meet him actually because we had to brief him about the society details, and also we had to follow it up with the legal department of the Parliament. That is a normal practice. But only thing is if something happened to Parliament, I mean, if it is dissolved or something happened, again we have to start the process from the beginning. Last year, luckily we didn't do it because Parliament was prorogated. Now this year, I hope it will not happen. And we have to, I think few members of the committee, senior members of the committee should go with Professor Tilakasiri and meet Mr. Ajit Mahanam and persuade this matter. And this year we must get this the act passed in the Parliament, because without that we can't get the CEDA recognition also, and also maybe Engineering Council recognition also. We may need that actually, and I think we have to concentrate on that. And I'm sure that our executive members will work towards it. And also about the website, we have improved the website, but I think there are a lot of rooms, a lot of ways it can be improved further. I think one area is that we have to establish the members directory. I think with their contact numbers and so on, that I think we can easily do it. And also the upgrading part, we have a little bit of slow movement there. I think in this year, I think we can catch it up and we can do the update promptly. And anything else on the website? Any suggestion on the website? And also, I think we have a YouTube channel. Some of our presentations, maybe we can publish in the YouTube with the consent of the authors. Some authors they don't like because they have not got the required permission to publish their projects, and because of that, there was a little bit of problem, especially from foreign people, because they are very strict on publishing their project details. And apart from that, I think if the presenter agrees, we can publish in our YouTube, and then we can have a link to our main website.
And then now the proceedings of the today's conference, I suppose we can upload to the website, right?
Yeah, I think so. I don't think there is a...
That can be done. We have already shared it with the participants.
Yeah, so now I mean we have a location in the website to upload it now. So
yeah, yes, sir. The soft copy is now available, so we can do it.
So we can do it.
And what else? Any suggestion about journal? Of course, I don't know. That is a very difficult task. I mean, we at the moment we are publishing only one copy, one volume of journal per year. If we can increase at least to 2, I think it's a great achievement. And also, I don't know whether this journal is accepted by the universities. So they are, I mean, you have some kind of, the acceptance criteria for publishing work. Atula, do you know anything about it?
This is now these are refereed publications, no? Right?
Yeah.
We have evidence to say that the paper published in the journal is refereed, right? So therefore, it is considered as a refereed publication. So then there are various other things like the Scopus index and so forth. So we haven't received that, right? In the recognition, there are different levels of recognition. So this is recognized as a refereed publication. We have proof for that. But then other thing to achieve is things like Scopus index. So that is bit difficult to achieve. So you have to have a certain number of publications per year And
I think we need 4, I think, for that.
yeah. So that's bit tough. So we should try to achieve that eventually. But at least it is considered as a refereed publication. So we are, as we are sort of sticking to this process, the process of refereeing the papers.
No, because
the problem is the problem is the finding the number of papers. So this year, still we are searching the papers.
No,
Last year, fortunately, we got 4 papers, but this year, still we couldn't find any paper. That is the main problem.
Yeah, that is the problem that we had all the time. That was the problem that we had.
The problem is like now if we don't have the recognition, especially the research people, academic people, they will not publish in our journal because they will publish in somewhere else because they can get some marks in their promotional route in the universities. And then that is the if we have to solve it, I think we have to at least publish 4 journals, maybe at least with 3 papers in one journal basis. At least if you can publish, I think we will get better response from the authors. But it is a difficult task. I mean, we can talk, but implementation may be very, very difficult. But we do that in the structural society, but I don't say it is a real type of journal. But we couldn't get any recognition also there yet. I mean, that is a problem we are facing at the moment. And most of people, even local, they prefer to publish in ISL because of that point. Anything from Saman?
Sorry, I was muted here. Now, I think we have to work towards getting I know it is difficult task, but we have to work towards getting the indexing. Otherwise, the research culture will not be there. For example, we need to have the foreign referees and so on. So if you want to get the indexing of the journal, now we may not get it immediately, but we have to work towards that, I think.
Yeah, I also agree on that, because without that, we can't improve the journal. I mean, if there is no recognition. And also our people publish, I think, enough papers. If we can attract to our journal by getting the required recognition. I think the people who are in the universities should work towards that, actually, because it is not difficult for the people who are in the industry to work on this. But if we can get 12 papers per year, I think that will be enough way to go with 4 publications. But I am sure, I mean, at least now, when I say academy, in university people, but also industry, I know, I mean, now when we do the international conference, we get about 10 papers from the industry. I mean, if we can promote that, now NBRO, CCB, RDA may have some kind of papers. I mean, maybe we need a little bit of improved versions. We can go for this 12 number. Maybe not in this year, at least we can try. I think Atula can, Atula can lead that, actually.
We'll try. We have been trying that over the years. So.
Okay, then,
can we ask our members to submit papers? I mean, initially.
Yeah, we must start with our
because we are planning for 2 volumes, so at least the 8 papers. So shall we ask SLGS members to submit the papers?
I think minimum we need four volumes per year. That was Professor 1 meter second told me.
2 volumes are enough, right?
Two.
We say at least 2 volumes per year.
Yeah, I think.
Okay. Then that is easy, no? Then we can get some papers from outside also, like people like Professor Jaivikrama. That is okay, no?
No, Mr. Avanto, everybody thinks about the recognition, right? So if they can send it to a better journal, the recognition is high.
I know, but I don't want to tell the exact reason, but because they are quite mature people, maybe they can do something on that.
No, but
young people may not be not like that.
No, they write papers with their students, no. So,
Yeah.
I mean, their first intention is to write it to a more recognized journal, submit the paper to a more recognized journal. So it will be practically difficult to get papers from outside. So we'll have to try and generate it inside within our community.
Shall we try this year?
It is an egg and the chicken situation, because we will, without the recognition, we will not get that required papers, and with the required papers, we will not get the recognition.
That's what I'm telling, because we were talking about journal every time, but without the recognition, people are reluctant to say. It is same with the Society of Structural Engineers.
So what Atul says is correct, because now if you look at a student, right? So you will look at the recognition for the student, even though you will not require that. Basically, then you will.
I agree with Atul's point. But we have to keep something, because the journal is a very important document for the society. If we can improve it, if it is 2 journals per year, I think we can achieve that. Now we have so many universities also in Sri Lanka, engineering faculties. At least if we can.
Shall we try this way? I mean, from the project day, we can select a few papers and ask them to submit for the journal.
Improve it and submit.
Submit to journal.
That is possible. And also we have a lot of MSc students now. Undergraduate students, they may not have sufficient material to write a journal paper, but MSc student, of course, they can, because they do a project for 1 year, no?
At State, actually, what we did was we started the conference. So from the conference, good papers will go for the journal, and the other papers will go for the conference proceedings. So that way, that you have kind of set of papers to work with. Can we do that way?
Yeah, I think with the MSc students, we can do something actually. That's what I feel. Maybe some of the papers are not good enough to accept in international level, no, and we may get something in between to publish in our journal. But we have to start somewhere, no?
Yeah, we have been trying that, and anyway, so we'll have to keep trying. So there's no other way.
Okay, then we will move to the next website. We talk with Parliament text to discuss. The forum, actually, we did very successfully this year. We had 7 presentations. We will try to do the same thing in coming year, because what I did was I contracted my batchmates mostly, and they agreed to present in the forum, and also later they presented in the annual conference. And we can adapt the same principle with other. You may have connections with your people, and I'm sure that we can get some sufficient presenters for the forum. At least we must make sure that we have each month we have the forum as a regular item. That was there about 5-6 years back. But I mean, at one time, we couldn't maintain that actually. And with the Zoom, that is one advantage. We can get overseas people without much problem, any problem. Because then we don't have to 100% depend on local people. There's no difference between the local and foreign when it comes to the Zoom platform. Okay, then workshop is a very successful item in this year. I must be thankful to especially Samanthi Lekasiri and also the old resource people for conducting that. SLG newsletter, any suggestions? At the moment it is going on, but that also if we had 3 last year, if we can increase to 4, I think there is a little bit of regularity on that. That we can do it. There is not an issue on that.
Yeah, that we can do because we have, I mean, we should have 4 issues per year. Dr. Sampath is looking after it. I think we can do it.
Only thing what we can do is we can improve it to a total online version rather than making a PDF.
We can put a PDF and
no, it is not the PDF. Like we can click the newsletter and then click the topics and then read it, right? Like that. That is the online version. This is just we are posting it in the as a PDF.
Yeah, can be, yeah. But that for that I think web has to be updated.
No, web is now anyway that I think they have the know-how, right? So we can go.
Okay.
Yeah, we can.
Yeah, then who will undertake to do it?
I think that same people. I think the yeah. Editor newsletter can do.
Right. Now the next item is the election of office bearers. Now, who is going to have the president? I mean, somebody has to depending on that.
So,
shall we start? Do we need somebody else to share the?
Just for at least for the president post, I think Professor Kulatilaka can be the pro tem chair and then call for nominations.
Yeah, Professor Kulatilaka.
Okay, so then please propose someone for the post of the president of the SLGS for the next year.
I propose engineers.
I second.
Matula, can you hear me?
Yes. Yes, so Engineer Sahabandhu's name was proposed by Professor Samanthi Lekasiri and seconded by Mr. Mahinda Ratnasiri. So we will take it that Engineer Sahabandhu has been elected as the president of the SLGS for the next term. Thank you. And then over to you, Engineer Sahabandhu, so you can take over the rest of it.
Okay. Thank you very much for the confidence you have with me. I will try my best to improve the society level and also to increase the activities what society does. Actually, we had the problem last year with the COVID problem as well as this economical situation of the country. I think we have to live with that, and we will try our best to do something for the SLGS. Then we will go to the next item, that is to elect the vice president of the SLGS. Can somebody propose and second?
Who is the present vice president?
Present vice president is Dr. Asiri Karunamar. Can somebody propose?
Okay, I would like to propose Dr. Asiri Karunamar as the vice president.
No, excuse me. Thank you very much. But I think with this present situation and the schedule, I won't be able to, fully committed for that one. So I propose somebody else. I think it's much better. So of course we will help that one, but in the capacity of member. But better you propose somebody. I really appreciate that.
Asiri, can you propose somebody?
May I propose Professor Ramantrik is here, the vice president?
I second it.
Actually, I also have the same problem. I will give my
for 1 year. I think he can serve at least for 1 year.
No, I think everybody has problems. I mean, especially at this age, people are bearing, I think, Asiri as well as someone both have a lot of work in their workplaces. But somebody has to take this responsibility. And also, I mean, the society has moved with that spirit actually. I think someone, you have no objection, no?
I can, I will give my full support, but I don't know whether that is enough.
No,
This year you gave a lot of support, so we'll.
No, actually, someone has done a lot of things during last tenure. I mean, he did. I really appreciate what he did for the EC7. I mean, the 0 code 7. I initiated it and we had a very successful workshop. And because of that, I think you had a capacity. I don't know. I mean, if you have commitment, you can fulfill that.
I will do my best. That's
Okay. Yes, agreed on that. Then I will declare that Professor Samanth Tilakasiri will serve as the Vice President of the Sri Lankan Geotechnical Society for 22-23. Then we have to select Honorary Secretary.
I propose Professor Uddin Navagam.
I second it.
Yeah, thank you, Saman and Asiri. Then Professor Uddin Navagama will be elected as a secretary, honorary secretary of SLGS. And you have to note down all these proposals and.
Yes. Yeah, I am.
Okay. Right. Then we have the important position, treasurer. At the moment, it is Mr. Bandara. But Mr. Bandara has mentioned several times, even last time, that he is too busy to work on this position. And
yeah, I think he mentioned me also. So if someone from MBR or CECP can bear this post of treasurer and assistant treasurer, I think it's much better.
No, there is no rule like that, CCB or NBR or something like that. Who can volunteer? Who can volunteer for that decision?
Yeah, Mr. Abanto, there is a warning that this one is live casting. Can we stop this live casting?
Okay. I can't do it.
We don't need others to see this now.
Yeah.
Yeah.